Hello there, and welcome back to Science to Fall Asleep. Tonight, there is nowhere you need to go. You don't need to solve anything. You don't need to understand everything. You can simply let your thoughts become quieter as we travel together toward one of the most distant, mysterious, and peaceful places on Earth. Imagine yourself standing beneath a sky so enormous that it seems to have no edge. Around you stretches a landscape of white and blue, extending farther than your eyes can follow. There are no busy streets here, no crowded buildings, no traffic, no familiar sounds of everyday life. Only the soft movement of wind across snow, the distant cracking of ancient ice, and the quiet rhythm of a continent that has been frozen for millions of years. This is Antarctica, the coldest continent on our planet, the driest continent, the windiest continent, and one of the most fascinating places that science has ever explored. Tonight, we'll slowly wander across this frozen world. We'll move over enormous ice shelves, beneath pale polar skies, toward mountains hidden beneath glaciers, and across landscapes where the boundary between land, ocean, atmosphere, and ice becomes difficult to separate. We'll discover how Antarctica was once warm enough to support forests. We'll learn why its ice contains pieces of Earth's ancient atmosphere. We'll drift beneath the Southern Ocean and discover creatures that survive in water cold enough to challenge the limits of biology. We'll explore enormous glaciers, hidden lakes, strange winds, sleeping volcanoes, ancient fossils, mysterious mountains, and skies that can glow with colors almost impossible to imagine. And as we travel, there is no need to remember everything. You don't have to follow every detail. You can simply listen. Let the information pass gently through your thoughts. And if sleep arrives somewhere along the way, you can allow the journey to continue without you. So, wherever you are tonight, become comfortable. Let your breathing slow. Let the room around you become quieter. And now, very gently, imagine that the lights of the familiar world are beginning to disappear. Ahead of you is Antarctica, a continent of ice, a continent of silence, a continent that has been keeping secrets beneath its frozen surface for longer than human civilization has existed. And our journey begins. Antarctica is often described simply as a continent covered in ice, but that description doesn't quite capture how extraordinary it really is. Beneath the enormous white surface is an actual continent. There are mountains, valleys, plains, deep basins, volcanoes, lakes, and geological structures hidden beneath kilometers of frozen water. In many places, if you were standing on the surface, you would have no idea what was underneath your feet. The landscape beneath Antarctica is almost like another world buried beneath the visible one. A layer of ice conceals enormous portions of the continent. That ice is not simply a thin frozen blanket. In some places, it is several kilometers thick. Imagine taking a mountain and slowly covering it with snow, then continuing to add snow. Year after year, century after century, millennium after millennium, the weight of the accumulated snow would compress the layers below. Eventually, the snow would become dense ice. More snow would fall. More ice would accumulate, and over incredibly long periods of time, the frozen material would become a massive structure capable of flowing slowly across the landscape. This is essentially how much of Antarctica's great ice sheet developed. The Antarctic ice sheet is one of the largest physical structures on Earth. It contains an extraordinary amount of frozen fresh water. If all of the Antarctic ice sheet were somehow melted, global sea levels would rise dramatically. The number is difficult to imagine. The potential increase is roughly 58 meters. That is far taller than most buildings. It would completely transform coastlines around the planet. But Antarctica isn't melting away overnight. Its ice contains a history measured not in years or centuries, but in hundreds of thousands of years. And that history can be read by scientists through something remarkably simple. Ice cores. Imagine drilling deep into the Antarctic ice. The deeper the drill travels, the older the ice can become. Layer by layer, the ice preserves traces of the atmosphere that existed when each layer formed. Tiny bubbles become trapped inside. Those bubbles contain ancient air, and within that air are gases that once surrounded Earth. Scientists can analyze these microscopic pockets and learn about atmospheric conditions from the distant past. In a sense, Antarctic ice is a frozen archive of Earth's atmosphere. The continent has been quietly storing pieces of ancient air beneath its surface. Some of that air was trapped long before modern civilization existed, long before written history, long before cities, long before agriculture transformed human societies. And when scientists examine those tiny bubbles, they are effectively listening to fragments of the ancient atmosphere. The ice becomes a kind of time capsule, a silent library, every layer carrying information from a different moment in Earth's history. The deeper the journey goes, the farther back in time we can sometimes travel. This makes Antarctica valuable not only because of what exists there today, but because of what has been preserved there from Earth's past. The continent is a natural archive, and it has been writing its records without ink. Snow has been the paper, cold has been the preservation method, and time has been the author. Antarctica is also unusual because it is considered the driest continent on Earth. At first, this may sound strange. How could the world's largest frozen wilderness also be the driest continent? The answer lies in the difference between ice and precipitation. Antarctica contains an enormous quantity of water, but most of that water is locked away as ice. Very little new precipitation reaches many parts of the interior. The air is extremely cold. Cold air cannot hold as much water vapor as warm air. As a result, the interior of Antarctica can receive remarkably little snowfall. Some regions are so dry that they are classified as polar deserts. The word desert usually makes people imagine sand, but a desert is not necessarily a place covered in sand. A desert is fundamentally a place where precipitation is extremely limited, and Antarctica fits that definition remarkably well. There are regions where snowfall is so scarce that the landscape can remain almost unchanged for long periods. The Antarctic interior can therefore feel strangely still. White stretches toward the horizon. The sky seems enormous, and the landscape can become so uniform that distance itself becomes difficult to judge. A small ridge may appear close while actually being many kilometers away. A distant mountain may look almost unreal against the pale horizon. There may be no trees to provide scale, no houses, no roads, no familiar objects, just ice, rock, sky, and distance. This lack of visual reference creates a landscape unlike almost anywhere else on Earth. And beneath that seemingly empty surface, enormous processes are taking place. Ice is slowly moving. Mountains are being shaped. Wind is carrying tiny particles across the surface. Snow is accumulating. Glaciers are flowing. The ocean is moving beneath and around floating ice. Even when Antarctica appears completely motionless, it is not truly still. It is simply moving at a pace that is difficult for human senses to notice. One of the most remarkable features of Antarctica is its enormous ice sheet. The Antarctic ice sheet covers almost the entire continent. From above, it looks like an endless white landscape. But the ice is not identical everywhere. Different areas contain different textures, structures, ages, and movements. Some ice is relatively young. Some has existed for immense periods of time. Some regions are thick and slowly flowing. Others are shaped by strong winds. Some areas contain deep crevasses. Others appear almost perfectly smooth. And beneath all of this frozen material, the underlying continent continues to influence how the ice behaves. Gravity pulls the ice downward. The ice slowly deforms under its own enormous weight. It flows outward from higher regions toward lower areas. This movement is incredibly slow compared with rivers that we see in warmer climates. But glaciers are still flowing bodies of ice. A glacier can move only a few centimeters a day in some places. Elsewhere, ice can move much faster. Certain Antarctic glaciers are among the fastest-moving glaciers on the continent. Their movement can be measured through satellites and other instruments. From space, scientists can watch the surface of Antarctica change. They can measure how ice moves. They can observe changes in ice shelves. They can identify crevasses. They can monitor areas where ice is thinning or thickening. Satellites have therefore transformed our understanding of Antarctica. From the ground, a glacier can appear almost completely motionless. From space, its movement becomes easier to see. The continent reveals its slow motion when observed over long enough periods. And then there are Antarctica's ice shelves. An ice shelf is a huge floating platform of ice connected to land. It forms when glaciers flow from the continent toward the ocean and eventually extend outward over seawater. The ice remains connected to the land while floating on the ocean. Some ice shelves are enormous. They can cover areas larger than countries. The Ross Ice Shelf is particularly vast. It occupies a huge portion of the Ross Sea and represents one of the great frozen landscapes on Earth. Imagine standing at its edge. You might see what appears to be a wall of ice stretching across the horizon. But beneath the floating shelf is ocean water. The ice is enormous, yet it floats. This is possible because solid ice is less dense than liquid water. The same basic physical principle that allows a small ice cube to float in a glass also operates here, on a scale so enormous that the comparison almost feels absurd. A tiny cube of ice floats quietly in a drink. An Antarctic ice shelf floats quietly on an ocean. The physics is the same, only the scale has changed. Antarctica also contains mountains that are almost completely hidden by ice. The Transantarctic Mountains divide the continent into major geographic regions. They stretch for thousands of kilometers. In some places, their peaks rise dramatically above the surrounding ice. In others, mountains and valleys disappear beneath the enormous ice sheet. One of the most fascinating discoveries beneath Antarctica has been the existence of mountain ranges hidden under the ice. Radar instruments carried by aircraft and satellites can penetrate portions of the ice and reveal the terrain below. Scientists can create maps of landscapes they cannot physically see. They can identify valleys, ridges, mountains, basins, and other geological structures buried beneath the frozen surface. It is almost like discovering an entire continent underneath a continent. The surface tells one story. The hidden bedrock tells another. And together they reveal that Antarctica is far more complex than its white appearance suggests. There are also lakes beneath the Antarctic ice. These are not ordinary lakes surrounded by visible shorelines. They are hidden beneath kilometers of ice. Known as subglacial lakes, They exist because geothermal heat from Earth's interior can warm the base of the ice sheet, while the enormous pressure from the ice above affects the melting point of water. One of the most famous is Lake Vostok. It lies beneath the East Antarctic ice sheet and is buried beneath several kilometers of ice. The lake is enormous. For an environment hidden beneath such a thick layer of frozen material, the idea of liquid water existing there can seem almost impossible. Yet Earth's internal heat continues to flow outward from the planet. The ice above acts as an insulating layer. Pressure and temperature interact, and in certain places, liquid water can persist beneath the frozen surface. These hidden lakes are part of a much larger subglacial environment. Water can move beneath the ice. It can influence how glaciers slide. It can connect different parts of the hidden landscape. The bottom of Antarctica, therefore, isn't simply a frozen floor. It can contain a dynamic system of water moving through darkness beneath the ice. There is no sunlight there, no open sky, no trees, no visible horizon. Yet liquid water can exist in the darkness. And scientists continue to investigate what kinds of life, if any, may exist in some of these extreme environments. Antarctica is also home to one of Earth's most unusual mountain ranges. The Adverts Mountains are buried beneath the East Antarctic ice sheet. They are comparable in scale to major mountain systems elsewhere on Earth, yet they are hidden beneath kilometers of ice. From the surface, you would not necessarily know that a huge mountain landscape exists below. The ice smooths everything into a seemingly continuous white world. But beneath it are peaks and valleys. The discovery of these hidden mountains changed how scientists understood the interior of Antarctica. The continent was not simply a vast flat block of frozen material. Its hidden foundation contains dramatic topography. Some of these mountains may have existed for hundreds of millions of years. They have endured geological changes, shifting climates, and enormous transformations of Earth's surface. And now they rest beneath a frozen layer that can be kilometers thick. If you could somehow remove the ice while leaving the underlying continent untouched, Antarctica would look completely different. There would be mountains, deep valleys, rocky landscapes, basins, and geological structures that have been hidden from ordinary human sight for incredibly long periods. The Antarctica we see is therefore only the uppermost layer of the story. The continent also has volcanoes. One of the most famous is Mount Erebus. Rising on Ross Island, Mount Erebus is one of the world's southernmost active volcanoes. Its presence is a reminder that Antarctica is not geologically dead. Beneath the frozen landscape, Earth remains active. Magma moves deep underground. Heat rises. Volcanic gases escape. And in certain places, molten rock can exist beneath a landscape dominated by ice. Mount Erebus is especially remarkable because it has maintained a persistent lava lake within its crater for long periods. Imagine looking across a frozen Antarctic landscape and finding a place where liquid rock glows deep inside a volcano. The contrast is extraordinary. Outside, temperatures can be brutally cold. Inside the volcano, temperatures are hot enough to keep rock molten. Ice and fire exist within the same Antarctic landscape. Cold air moves across the slopes. Snow surrounds the mountain. And beneath the summit, Earth's interior continues its ancient work. The Antarctic atmosphere can also produce extraordinary optical phenomena. When sunlight interacts with ice crystals suspended in the atmosphere, light can be refracted and reflected in unusual ways. The result can be halos around the sun or moon. Bright arcs can appear in the sky, Columns of light may seem to rise upward. The frozen atmosphere becomes a kind of natural optical laboratory. In ordinary conditions, we might see the sky as simply blue during the day and dark at night. But polar environments can reveal more complicated patterns. Ice crystals can bend sunlight. They can scatter it. They can produce halos that seem almost like enormous rings suspended in the sky. And because Antarctica contains so much ice and extremely cold air, the conditions can be ideal for observing certain atmospheric effects. The sky itself becomes part of the landscape. Then there are the winds. Antarctica is famously windy, particularly in regions where cold, dense air flows downhill from the high interior toward the coast. These are called katabatic winds. The word sounds almost gentle, but the winds themselves can be powerful. Cold air becomes dense. Gravity pulls it downward. As it moves from elevated regions toward lower elevations, it can accelerate. The result is a wind that can sweep across the ice with enormous force. In some areas, katabatic winds can persist for long periods. They can transport snow. They can reshape the surface. They can create strange patterns in the ice. And they can make already extreme temperatures feel even more severe. A landscape that looks calm from a distance may become dramatically different once the wind begins to move. Snow can blow across the surface like smoke. Visibility can fall. The horizon can disappear. The sky and ground can merge into a single pale field. For Antarctic researchers, understanding these winds is essential. For the sleeping traveler in our imagination, however, we can simply listen to them from somewhere warm and safe. The wind remains outside. The room remains quiet. And Antarctica continues its ancient movement beneath the stars. There are places in Antarctica where almost nothing grows. The extreme cold, dryness, strong winds, and limited sunlight create conditions that are difficult for most organisms. Yet life still finds ways to survive. Tiny microorganisms can live in places where larger organisms could not. Certain algae can survive in ice. Microbes can inhabit soil. Some organisms can endure long periods of darkness. This is one of the most important lessons Antarctica offers scientists. Life does not always require comfortable conditions. It can adapt. It can become microscopic. It can slow its metabolism. It can occupy tiny protected spaces. It can survive around the edges of what we normally consider habitable. Some Antarctic organisms are so specialized that they could not easily survive outside their extreme environment. Their biology has been shaped by cold. Their survival strategies have evolved around scarcity. There is little liquid water. There is little warmth. There can be long periods without sunlight. Yet life persists. Quietly, slowly, almost invisibly. Near the coast, the Antarctic world changes dramatically. The Southern Ocean surrounds the continent, connecting Antarctica with the world's other great oceans. The ocean around Antarctica is not merely a border. It is a major part of the Antarctic climate system. Cold water moves. Deep water rises. Winds influence ocean currents. Sea ice forms and disappears with the seasons. Nutrients move through the ecosystem, and marine organisms gather around the edges of this frozen continent. One of the most important creatures in this ecosystem is tiny krill. Antarctic krill are small crustaceans that form enormous populations in the Southern Ocean. They may look insignificant individually, but collectively, they are one of the foundations of the Antarctic marine ecosystem. They feed on microscopic organisms, including phytoplankton. Then they become food for larger animals. Fish consume them. Seabirds consume them. Seals consume them. and whales can consume enormous quantities of them. A creature only a few centimeters long can therefore connect microscopic life with some of the largest animals ever to live. The Antarctic ecosystem is built from these connections. Tiny organisms support larger organisms. Larger organisms support predators. And the energy ultimately traces back to sunlight captured by microscopic life near the surface of the ocean. Even in one of Earth's coldest environments, the fundamental story is still about energy moving through life. Antarctica's penguins have become some of the continent's most recognizable inhabitants. But not every penguin lives in the same environment. Different species have different relationships with ice, ocean, temperature, and food. Emperor penguins are perhaps the most famous. They are the largest living penguin species. Their lives are closely connected with Antarctic sea ice. During the breeding season, emperor penguins endure conditions that would be almost unimaginable to humans without specialized clothing, shelter, and technology. The temperatures can fall extremely low. Winds can become intense. Darkness can dominate the landscape for long periods. Yet the penguins remain. They huddle together. Their bodies become part of a moving mass that helps conserve heat. Individuals on the outside gradually move inward. Those in the warmer center eventually move outward. The group constantly shifts. No single penguin remains in the coldest position forever. It is an elegant example of collective behavior. Each individual contributes to the survival of the group. And in the darkness of the Antarctic winter, thousands of penguins can stand together on the sea ice while the wind moves around them. It is one of the most remarkable scenes in the natural world. Emperor penguin chicks begin life in an environment that seems almost completely unsuitable for survival. Yet their parents provide extraordinary care. The male emperor penguin is especially important during the early stages of development. After the female lays a single egg, she transfers it carefully to the male. The egg must not remain exposed directly to the freezing surface. The male balances it on his feet and covers it with a fold of warm skin called a brood pouch. Then he remains with the egg while the female travels toward the ocean to feed. For weeks, the male may remain without eating. He depends on stored body fat. His body is adapted to endure the harsh winter. Around him, other males form dense groups. The colony moves slowly. The penguins rotate positions. They conserve warmth. And beneath the dark Antarctic sky, the eggs remain protected. Eventually, the chicks hatch. The female returns with food. The parents then begin a new stage of cooperation. The tiny chick, covered in soft down, will gradually grow stronger. Eventually, it will develop the feathers and body structure needed for life in the cold ocean. The transformation is slow, but Antarctica rewards patience. Almost everything here happens according to a different clock. The Antarctic winter is especially remarkable because of darkness. At the South Pole, the sun does not rise above the horizon for approximately 6 months. Then, after the long winter darkness, the sun gradually returns. This creates one of the most dramatic seasonal cycles on Earth. Imagine living through an environment where the concept of day and night changes completely. For months, there is no normal sunrise, no ordinary afternoon, no sunset every evening. Instead, there is a prolonged period of darkness. Then the sun returns and remains above the horizon for months. The geometry of Earth is responsible. Our planet is tilted on its axis. As Earth travels around the sun, the poles alternate between facing toward and away from sunlight. At the South Pole, Winter brings a long period without direct sunlight. Summer brings the opposite. The sun can remain visible above the horizon for months. It circles the sky rather than rising and setting in the familiar way. For people accustomed to a daily sunrise and sunset, this rhythm can feel almost dreamlike. But for Antarctica, it is simply the natural movement of the planet. Earth turns. Earth orbits. The poles experience the consequences, and Antarctica moves through its immense seasonal cycle. During the Antarctic summer, sunlight can remain present for extraordinarily long periods. The sun may hover low above the horizon. Even when it never becomes particularly high in the sky, it can remain visible for hours upon hours. This creates a strange landscape of endless daylight. Snow reflects the sunlight. Ice glows. Shadows stretch across the surface, and the boundary between afternoon and evening begins to disappear. At the South Pole, summer sunlight can continue around the clock. There is no conventional night. Instead, the sun slowly circles the horizon. It is a reminder that our ordinary experience of time is partly a consequence of where we live on Earth. Move toward the poles, and the familiar rhythm begins to change. Move all the way to the South Pole, and the year itself becomes divided into an almost impossibly long day and an almost impossibly long night. Antarctica's location also gives scientists an extraordinary opportunity to study the stars. The interior is extremely dry. There is very little atmospheric moisture. There are no large cities producing light pollution. The air can be exceptionally clear, and during the long polar night, the sky can remain dark for extended periods. For astronomers, these conditions can be valuable. Telescopes placed in Antarctica can observe the universe under conditions that are difficult to reproduce elsewhere. The cold environment creates challenges for humans and equipment, but it can also provide scientific advantages. The high plateau of Antarctica is particularly interesting. At great elevation, the atmosphere is thinner. The extremely cold and dry conditions reduce certain forms of atmospheric interference. When the wind is calm and the sky is clear, the stars can appear extraordinarily sharp. Imagine standing outside in complete darkness. The ground beneath you is white. The horizon is almost invisible. Above you is a sky filled with stars. There are no city lights, no traffic, no buildings, only the faint glow of the distant universe. For a moment, the continent itself almost disappears. You are simply standing beneath space, and Antarctica becomes a bridge between Earth and the cosmos. The southern lights can also appear above Antarctica, known as the aurora australis. They occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. The result can be curtains of light dancing across the polar sky. They may appear green. They can sometimes contain red, purple, or other colors. The shapes can stretch across enormous portions of the sky. They can shimmer. They can shift. They can appear almost stationary before suddenly changing form. The process begins far away on the sun. Streams of charged particles travel through space. Earth's magnetic field guides some of these particles toward the polar regions. When they encounter gases in the upper atmosphere, energy is released as light. The result is an aurora. A phenomenon that begins with activity on the sun can therefore produce glowing patterns above a frozen continent millions of kilometers away. And while the science is fascinating, there is something wonderfully peaceful about imagining it. You are lying somewhere warm. Your eyes are closed. And above an Antarctic research station, far away from the noise of cities, green curtains of light slowly move across the night. The ice reflects a faint glow. The wind passes over the snow, and the stars remain quietly visible behind the aurora. Antarctica also holds some of Earth's oldest rocks. Because the continent has experienced enormous geological stability in certain regions, ancient rocks have remained preserved. Some rocks formed hundreds of millions, and in certain cases billions, of years ago. They contain evidence of ancient geological environments. Long before Antarctica looked the way it does today, the land was part of larger continental systems. It moved. Oceans opened and closed. Mountains formed. Climate changed. Life evolved. Continents collided. And Antarctica traveled through these transformations. Today, the frozen landscape can make the continent seem timeless. But Antarctica has not always been at the bottom of the world as a frozen wilderness. Its geological history is much more dynamic. It has been connected to other continents. It has participated in ancient supercontinents. It has experienced climates very different from today's. The ice is only the latest chapter. The rocks beneath it tell a much older story. Long ago, Antarctica was part of Gondwana. Gondwana was an enormous southern supercontinent that included land masses that eventually became South America, Africa, Australia, India, Antarctica, and other regions. Imagine looking at a map of the modern world and then slowly pushing the continents together. South America would move toward Antarctica. Africa would approach. India would be positioned differently. Australia would connect. Eventually, many of today's separate continents would form a much larger landmass. Antarctica occupied a central position within this ancient configuration. Over immense spans of geological time, the pieces separated. Continents drifted. Oceans expanded. New coastlines appeared. And Antarctica gradually moved toward its present position. This means that the frozen continent beneath the southern lights was once connected to places that today seem incredibly distant. The rocks of Antarctica share geological clues with rocks found on other continents. The planet's surface is not permanent. It moves, very slowly, so slowly that an individual human life cannot feel it. But across millions of years, those movements reshape the entire map of Earth. Antarctica was also once covered by forests. This is one of the most surprising facts about the continent. Today, the idea of trees growing across Antarctica seems almost impossible. But Earth's climate has changed dramatically over geological time. When Antarctica occupied different positions and global temperatures were much warmer, forests could exist there. Fossils of ancient plants have been discovered in Antarctic rocks. They reveal a continent that looked nothing like the frozen world we know today. There were trees. There were vegetation-rich environments. There were ecosystems adapted to conditions that included long periods of darkness, but also long periods of sunlight. At high latitudes, plants would have experienced unusual seasonal patterns. Imagine a forest where the sun remains above the horizon for a very long time during summer. Then imagine the same forest entering a prolonged winter darkness. Plants and ecosystems evolved under conditions unlike those found in most modern forests. The fossil record allows scientists to reconstruct pieces of this ancient world. Antarctica's ice therefore hides not only geological landscapes. It also conceals the memory of a warmer planet. The existence of ancient Antarctic forests is a powerful reminder that climate is not fixed. Earth has experienced periods far warmer than the present. It has also experienced periods much colder. Ice sheets have expanded. They have retreated. Oceans have changed. Atmospheric gases have changed. Continents have moved. And life has adapted to these transformations. The Antarctic landscape we see today is therefore not a permanent state. It is one moment in a much longer planetary story. If you could travel backward through time, Antarctica would gradually change. The ice would disappear. Vegetation would appear. Different animals would move across the land. The coastline would look different. The surrounding oceans would have different temperatures and currents. And eventually, the continent would become part of ancient ecosystems that are now preserved only in stone. Today, the frozen surface hides much of this history, but the rocks remember. Some of Antarctica's fossils are remarkably important because they help scientists understand the history of life. Fossilized leaves, wood, pollen, and other remains have been found in Antarctic sediments. These remains reveal that plants once lived there. Animal fossils have also been discovered. Among the most fascinating are dinosaur fossils. Antarctica was not always an isolated frozen wilderness. During the time when dinosaurs lived, parts of the continent had much warmer conditions. Dinosaurs lived on land that is now buried beneath ice or exposed only in certain rocky regions. Finding dinosaur fossils in Antarctica can therefore feel like discovering evidence from another planet. But these animals were not aliens. They were inhabitants of ancient Earth. Their bones became buried. Sediments accumulated. Geological processes continued. The continent changed. And millions of years later, scientists found traces of these ancient animals within the rocks. The fossil record allows Antarctica to speak across time. It tells us that the frozen continent once supported ecosystems very different from today's. The Antarctic Peninsula is one of the most geographically distinctive parts of the continent. It stretches northward towards South America. Compared with much of the interior, it has a relatively mild climate. Its mountains rise dramatically from the surrounding waters. Glaciers flow between them. Icebergs drift offshore, and wildlife gathers along the coast. The peninsula is also one of the most accessible parts of Antarctica for research and tourism because of its relative proximity to South America. Its landscape can look almost surreal. Dark mountains rise from white snowfields. Blue glaciers reach toward the sea. Icebergs float in quiet bays. Penguins gather along rocky shorelines. And clouds move rapidly through the mountains. It is Antarctica, but it is a different Antarctica from the vast interior. The continent is not one uniform environment. Its climate, geography, and ecosystems vary considerably from region to region. The interior is dominated by enormous expanses of ice. The coastal regions can contain exposed rock, wildlife, and open water. The peninsula has rugged mountains and relatively milder conditions. Each area reveals a different expression of the frozen continent. Icebergs are another important part of the Antarctic landscape. They form when pieces of glaciers or ice shelves break away and enter the ocean. This process is called calving. Sometimes the event is small. Sometimes an enormous piece of ice breaks away. The resulting iceberg may drift through the Southern Ocean for months or years. Only a portion of an iceberg is visible above water. Most of its mass remains below the surface. This is why an iceberg can appear deceptively small when viewed from a distance. The hidden underwater structure can extend much farther downward. Some icebergs are enormous enough to become floating landscapes of their own. They can have cliffs, caves, ridges, blue walls, and deep cracks. Their surfaces can be shaped by wind, melting, refreezing, and waves. The brilliant blue color, sometimes visible within Antarctic ice, is especially beautiful. Dense ice absorbs much of the red portion of visible light while allowing more blue light to escape. Ancient compressed ice can therefore appear intensely blue. An iceberg may look white from one angle and deep blue from another. It is not simply frozen water. It is a record of pressure and time. The blue color of Antarctic ice can become especially vivid inside glacier caves. When light enters dense ice, much of the red light is absorbed. The remaining light can appear blue. Inside a glacier, the effect can become extraordinary. Walls can glow in shades of blue. The ice can appear almost transparent. The surface may contain bubbles trapped from ancient snowfall. Tiny cracks can refract the light, and the entire environment can feel like a frozen cathedral. But glacier caves are not permanent. They change constantly. Warmth, pressure, flowing water, and movement within the glacier alter their shape. A cave that exists today may be different tomorrow. Some passages collapse, others open. Water flows through new channels. The glacier continues to move. This is another reminder that Antarctica's apparent stillness can be deceptive. The continent is always changing, just slowly. There are also Antarctic lakes that exist directly on the surface during warmer periods. Meltwater can collect in depressions on ice shelves. These ponds can become vividly blue. From above, they may look almost like tropical lagoons surrounded by an endless white landscape. But they are temporary. As temperatures change, the ponds can freeze again. Their water may also drain through cracks. Sometimes large amounts of meltwater can disappear rapidly when fractures allow water to travel downward through the ice. Scientists study these processes carefully because surface water can influence the stability of certain ice shelves. Water is heavy. When it collects in cracks, it can contribute to fractures spreading through ice. This process can sometimes accelerate the breakup of floating ice. The relationship between water and ice is therefore more complicated than simply freezing and melting. Water can reshape ice. Ice can redirect water. And the geometry of the frozen landscape determines where that water can travel. Antarctica's coastline is constantly changing with the seasons. During winter, sea ice expands outward from the continent. The Southern Ocean becomes surrounded by a broad ring of seasonal ice. During summer, much of that sea ice melts and retreats. This annual expansion and contraction is one of the largest seasonal changes occurring anywhere on Earth. Sea ice is different from the enormous ice sheet covering the continent. Sea ice forms when ocean water freezes. The Antarctic ice sheet consists primarily of accumulated snow that has been compressed into ice on land. The distinction is important. One begins in the ocean, the other begins on land. Yet both interact with the atmosphere and ocean. Sea ice affects how much sunlight is reflected. It influences the exchange of heat between ocean and atmosphere. It provides habitat for animals, and it can affect ocean circulation. The seasonal rhythm of Antarctic sea ice therefore has consequences far beyond the edge of the continent. The surface of Antarctic sea ice can become a temporary home for microorganisms. Algae can grow within and beneath the ice. These microscopic organisms become part of the food web. When the ice begins to melt, nutrients and organisms can enter the surrounding ocean. This connects frozen surfaces with marine ecosystems. Even a seemingly lifeless sheet of ice can contain biological activity. Under a microscope, the Antarctic environment becomes much more crowded than it appears from a distance. Tiny organisms move through water. Algae capture sunlight. Krill feed on microscopic life. Fish feed on krill. Penguins feed on fish and krill. Seals feed on fish and other animals. Whales consume enormous quantities of krill. The Antarctic food web is built upon countless small interactions. Nothing exists completely alone. Even the largest animals depend on organisms so small that humans cannot easily see them. Among Antarctica's most impressive marine animals are whales. Several whale species visit Antarctic waters, particularly during the summer months when food becomes abundant. The reason is simple. The Southern Ocean can become extraordinarily productive. Long days of sunlight encourage phytoplankton growth. Phytoplankton support krill. Krill support whales. The result is a seasonal explosion of biological activity. Some whales travel enormous distances to reach Antarctic feeding grounds. They may spend warmer months feeding intensively before migrating to other regions. Their journeys can span thousands of kilometers. Imagine traveling from one end of a continent to another simply to find food. Now imagine doing it through an ocean. Whales have evolved to make these journeys repeatedly. Their migrations connect ecosystems separated by vast distances. A whale feeding in Antarctic waters may later travel to warmer regions where it reproduces. Its life therefore crosses multiple climate zones. Antarctica is not isolated from the rest of the planet. Its ecosystems are connected through migration, ocean currents, atmospheric circulation, and global climate systems. One of the most fascinating Antarctic whales is the blue whale. The blue whale is the largest known animal to have ever lived on Earth. Its enormous size is difficult to visualize. Its heart alone can be comparable in scale to a small vehicle. Its body can extend for more than 25 meters, depending on the individual. Yet despite this extraordinary size, blue whales feed largely on tiny organisms. During feeding seasons, they can consume enormous quantities of krill. This is one of nature's most beautiful contradictions. The largest animal on Earth depends on creatures that are only a few centimeters long. The giant and the tiny are connected. The whale does not need to hunt enormous prey. Instead, it filters huge quantities of water through its baleen, trapping small organisms. The Antarctic Ocean can therefore support one of Earth's largest animals because it contains immense concentrations of very small life. The ecosystem becomes a story of scale. Tiny phytoplankton, small krill, huge whales, and everything connected through energy moving from sunlight into living organisms. Seals are another major part of the Antarctic ecosystem. Several species live around the continent. Some are highly specialized for Antarctic conditions. The Weddell seal, for example, is famous for its ability to live beneath sea ice. It can dive beneath the frozen surface and search for food in the dark ocean. To survive in this environment, it has developed remarkable physiological adaptations. Its body stores oxygen efficiently. Its blood and muscles can support long dives. It can slow certain physiological processes while underwater, and it can return to breathing holes maintained in the sea ice. A Weddell seal may rest quietly on the ice, looking almost peaceful. Then it can disappear into the freezing water. Below the surface is another world. Light fades. The temperature remains close to the freezing point of seawater, and the seal moves through the darkness searching for food. When it returns to the surface, it emerges through the same harsh environment where it began. The transition between ice and ocean is part of everyday life for these animals. The leopard seal has a very different reputation. It is one of Antarctica's major predators. With its powerful jaws and long body, it can hunt penguins, fish, and other seals. Its name comes from the spotted pattern across its coat. Unlike some gentler-looking Antarctic animals, leopard seals are highly effective hunters. They often patrol near ice edges. The boundary between sea and ice becomes a hunting ground. Penguins entering the water must pass through this dangerous zone. For the leopard seal, it is an opportunity. For the penguin, it is a moment of risk. The Antarctic ecosystem contains both peaceful and violent moments. From a distance, the landscape can appear serene, but beneath the surface, survival is constantly taking place. Animals hunt, animals flee, animals reproduce, animals migrate, and energy moves from one organism to another. Nature can be beautiful without being gentle. Crab-eater seals are another remarkable Antarctic species. Despite their name, they do not primarily eat crabs. In fact, their diet consists largely of Antarctic krill. Their teeth are specially adapted for filtering small prey from seawater. They can capture krill efficiently, making them one of the most abundant seal species in the Antarctic region. Their name is therefore somewhat misleading. There are very few true crabs available to them as a major food source. Instead, they are closely connected to the same tiny crustaceans that support whales, penguins, and many fish. Again, the importance of krill becomes apparent. A tiny animal can influence the lives of enormous numbers of larger creatures. The Antarctic ecosystem is built on these hidden connections. The Antarctic continent also has something unusual that many people don't immediately associate with such a frozen environment. Waterfalls. In the McMurdo Dry Valleys, there is a famous feature known as blood falls. The name sounds dramatic, but its color has a natural explanation. Water rich in iron emerges from beneath a glacier. When the iron comes into contact with oxygen, it oxidizes. The resulting reddish color can stain the ice. Against the surrounding white landscape, the water can appear deep red. It looks almost as though the glacier itself is bleeding. But the phenomenon is geological and chemical rather than mysterious. The water comes from a salty, subglacial environment. It contains dissolved minerals and iron. When the water reaches the surface, chemical reactions change its appearance. Blood falls is another reminder that Antarctica contains surprising environments hidden within the ice. The continent may appear monochromatic from far away, but up close, it can contain red, blue, gray, black, and countless subtle shades. The McMurdo Dry Valleys themselves are among the strangest landscapes on Earth. They are extremely dry. Large areas contain almost no permanent snow cover. Mountains surround broad valleys. Wind strips moisture from the environment. Temperatures can be extremely cold, and yet microorganisms survive in protected environments. Some researchers consider the dry valleys valuable analogs for studying possible environments on Mars. The comparison is not because Antarctica is identical to Mars. It isn't. Earth has liquid water, an active atmosphere, and abundant life. But the dry valleys demonstrate that life can persist under remarkably harsh conditions. Studying how microorganisms survive there can help scientists understand the limits of habitability. If life can survive in extreme cold, extreme dryness, darkness, and nutrient-poor environments on Earth, perhaps similar principles could help us recognize life elsewhere. Antarctica therefore becomes more than a place to study Earth's climate. It can also serve as a natural laboratory for astrobiology. And so our journey across Antarctica continues. Beneath the ice are mountains. Within the ice are ancient bubbles of air. Below the ice are hidden lakes. Around the ice are oceans filled with krill. Above the ice are stars and auroras. Along the coast are penguins and seals. Far below the surface, volcanic heat still rises from Earth's interior. And beneath all of these modern wonders is a geological history stretching back hundreds of millions of years. Antarctica is not simply a frozen continent. It is a record of Earth, a record written in ice, a record written in stone, a record written in the movement of glaciers and oceans. And tonight, you don't need to memorize any of it. You can simply let the story continue. The wind moves gently over the snow. The distant mountains remain beneath their white covering. Somewhere beneath the ice, ancient water rests in darkness. Somewhere far offshore, a whale moves through the Southern Ocean. A penguin stands quietly on the sea ice. Above them, stars shine through the polar night. And slowly, very slowly, Antarctica continues its journey through time. For millions of years, the continent has remained here through darkness and sunlight, warmth and cold, geological upheaval and quiet seasons. And for tonight, we can simply stay here for a little while longer, listening, breathing, resting, as the frozen continent stretches quietly toward the horizon. And there is still so much more to discover. 100 Sleepy Facts About Antarctica, Part 2. As the quiet Antarctic wind continues across the frozen landscape, our journey moves deeper into a world where almost every surface holds a story. The farther we travel from the familiar world, the more Antarctica begins to feel less like a place and more like a different rhythm of Earth itself. There are no crowded roads here, no forests moving in the breeze, no warm rain falling against windows. Instead, there are enormous fields of ice, distant mountains, deep blue shadows, and an ocean that slowly moves beneath floating sheets of frozen water. And beneath all of this apparent stillness, Antarctica continues to change. Its glaciers flow, its ice shelves flex with the tides, its sea ice expands and retreats. Its winds carry snow across the surface. Its volcanoes release heat from deep within Earth. And beneath kilometers of ice, liquid water can move through hidden channels. So tonight, as you remain comfortable wherever you are, imagine the room around you becoming quieter. Let your breathing settle into a slow rhythm. And imagine that the sound of the outside world is gradually replaced by a gentle Antarctic wind. We will continue drifting across this extraordinary continent, allowing one discovery to lead naturally into another. There is nothing you need to remember. Just listen. One of the first things that becomes apparent when studying Antarctica is that its ice does not behave like a solid, unmoving object. A glacier may look like a frozen mountain range, but over long periods of time, it behaves more like an incredibly slow river. Gravity pulls the ice downhill. The immense pressure created by the weight of thousands of meters of ice causes it to deform. The ice can bend, stretch, fracture, and flow. This movement may be so slow that a person standing beside a glacier would never notice it. But satellites can detect the motion. Researchers can compare images taken months or years apart and watch the ice gradually shift. Some glaciers move only a few meters each year. Others can move hundreds or even thousands of meters annually. And certain glaciers can experience periods of much faster movement. These faster episodes are sometimes called glacier surges. The idea is fascinating because it reminds us that solid ice is not always truly still. Given enough time, even something that appears completely rigid can move. A mountain of ice can slowly travel toward the ocean. A crack can widen. A valley can change. And an entire landscape can transform without making a sound loud enough for humans to hear. At the edge of Antarctica, glaciers sometimes flow into the ocean. When the ice reaches the coast, it can become part of a floating ice shelf or eventually break away as an iceberg. This creates a remarkable transition. The same snow that fell high on the Antarctic interior may eventually become ice flowing slowly toward the coast. After traveling for years or centuries, it may reach the ocean. Part of it can remain attached to the continent. Another part may eventually separate. The iceberg then becomes independent. It begins drifting with ocean currents and winds. Some icebergs remain near Antarctica for long periods. Others travel farther north into the Southern Ocean. Eventually, warmer water and warmer air cause them to melt. The journey of a single piece of ice can therefore be incredibly long. Snow falls. Snow compresses. Ice flows. Ice reaches the coast. An iceberg breaks away. The iceberg drifts. It melts. And eventually, the water returns to the ocean. The same molecules of water may then become part of clouds, rain, sea ice, or another glacier. Water is constantly moving through Earth's systems. Antarctica simply stores a tremendous amount of it in frozen form. Some Antarctic ice is so old that it predates the existence of modern humans by an astonishing amount. Scientists have recovered ice more than 800,000 years old from deep Antarctic cores. Within those cores are layers of ancient snow compressed over immense spans of time. Each layer represents a period when snow fell and gradually became buried. The pressure increased. The snow grains changed. Air became trapped. Eventually, the material transformed into solid glacier ice. The result is an archive extending deep into Earth's climatic past. By studying these layers, scientists can reconstruct changes in atmospheric gases, temperature, volcanic activity, dust, and other environmental conditions. Some of the oldest ice, therefore, contains information about an Earth that existed hundreds of thousands of years before modern civilization. There were no airplanes, no electric lights, no modern cities, no written records. Yet Antarctica was quietly preserving atmospheric information. The continent became a natural recorder, and its recording process required no machines. Snow simply fell. Time passed. Pressure accumulated. And history became frozen. The tiny bubbles inside ancient ice are especially valuable. When snow falls, it contains small spaces between individual snow grains. As more snow accumulates, those spaces become compressed. Eventually, the snow transforms into dense ice. Some of the original air remains trapped. Those tiny bubbles can contain gases from the atmosphere of the time. Scientists can extract and analyze them. The bubbles may be microscopic, but they carry information about the ancient atmosphere. Imagine holding a piece of ice that formed hundreds of thousands of years ago. It may look ordinary. Perhaps it is clear or slightly cloudy. But inside it are tiny pockets of ancient air. That air once moved through a very different world. It passed over forests that no longer exist, across oceans whose temperatures were different, through atmospheres with different concentrations of greenhouse gases, over landscapes occupied by animals and plants that have long disappeared. The bubble is tiny. The history inside it is enormous. Antarctica also records volcanic eruptions. When volcanoes erupt, they can release ash and sulfur compounds into the atmosphere. Some of this material can eventually reach Antarctica. Even a volcano located thousands of kilometers away may leave a chemical signature in Antarctic snow. Over time, the volcanic material becomes buried. A thin layer remains inside the ice. Scientists can sometimes identify these layers and connect them with known eruptions. The ice therefore becomes a geological timeline. A layer of volcanic material marks a moment when something dramatic happened somewhere on Earth. Then snow covered it. More snow accumulated. The event became part of the frozen record. Centuries later, scientists can drill into the ice and discover the evidence. Antarctica remembers events that happened far beyond its own borders. Dust also travels across enormous distances and can become preserved in Antarctic ice. During dry periods elsewhere on Earth, winds can carry tiny mineral particles into the atmosphere. Some particles travel vast distances. Eventually, they settle onto snow and become incorporated into the ice sheet. Scientists can analyze these particles to learn about ancient environmental conditions. The dust can reveal information about deserts, wind patterns, atmospheric circulation, and even changes in vegetation. A microscopic grain of dust can therefore become a clue to an ancient landscape. It may have originated on another continent. It may have traveled through the atmosphere for thousands of kilometers. Then it landed quietly on Antarctic snow. Snow buried it. Ice preserved it. And much later, scientists discovered it. The journey of that tiny particle may have been almost as extraordinary as the journey of the continent itself. Antarctica's location also makes it an important part of Earth's atmospheric circulation. The continent sits at the bottom of the planet, surrounding the South Pole. Cold air forms over the high interior. It becomes dense. Winds transport energy and moisture around the continent. The surrounding Southern Ocean connects Antarctica to global circulation systems. What happens around Antarctica can influence weather and climate far beyond the continent. Ocean currents carry cold water northward. Atmospheric patterns move heat. Sea ice affects the exchange of energy between ocean and atmosphere. And the Southern Ocean absorbs significant amounts of heat and carbon dioxide from the atmosphere. Antarctica is therefore not an isolated frozen island. It is deeply connected to the rest of Earth's climate system. A change in one part of the system can influence another. The atmosphere does not recognize political borders. The ocean does not stop at coastlines in the way a road stops at a border. Everything is connected. The Southern Ocean itself is one of the world's most powerful ocean environments. It circles Antarctica and connects the Atlantic, Pacific, and Indian Oceans. The Antarctic circumpolar current flows around the continent. It is the only major ocean current that circles the planet without being blocked by a continent. This enormous current helps isolate Antarctica from warmer waters farther north. It moves continuously around the continent. The current also plays an important role in global ocean circulation. Cold Antarctic waters interact with deeper ocean layers. Water can sink. Water can rise. Nutrients can move upward. Carbon can be transported into the deep ocean. The Southern Ocean therefore acts as one of Earth's great circulation engines. Its waters are cold, energetic, and constantly moving. Even when the Antarctic surface appears quiet, the ocean beneath can be in motion. The Antarctic circumpolar current also helps maintain the distinctive climate of the continent. By circulating around Antarctica, it limits the direct movement of warmer surface waters toward the continent. This contributes to Antarctica's isolation. The continent is surrounded by a moving ocean barrier. It is not a physical wall. It is a dynamic system of currents. Water temperatures, winds, pressure patterns, and Earth's rotation all influence its movement. The current has existed in its modern form for millions of years, although its exact strength and characteristics have changed over geological time. Its formation was connected to the separation of Antarctica from other continents. As the passages around Antarctica opened, ocean water could circulate continuously around the continent. The ocean became part of the mechanism that helped Antarctica develop its modern polar climate. Another remarkable feature of Antarctica is its enormous elevation. The continent is not simply low-lying land covered with ice. Much of the Antarctic interior sits at considerable altitude because the ice sheet is so thick. The South Pole itself is located on a high plateau. At such elevations, temperatures can become extraordinarily low. The atmosphere is thin compared with sea level. The combination of altitude, latitude, dryness, and isolation creates some of the harshest conditions on Earth. Yet this environment is valuable for scientific research. Researchers can study atmospheric chemistry. Astronomers can observe the universe. Climate scientists can examine ancient ice. Physicists can use the clear, dry atmosphere for specialized experiments. The harshness of Antarctica creates opportunities that are difficult to reproduce elsewhere. The very characteristics that make the continent difficult for humans can make it scientifically useful. The South Pole itself has a fascinating relationship with time. At the geographic South Pole, all lines of longitude meet. This means the conventional concept of time zones becomes somewhat arbitrary. Researchers working at the South Pole generally use a practical time standard rather than relying on a naturally obvious local solar time. After all, when the sun remains above the horizon for months and then disappears for months, ordinary daily time-keeping becomes less meaningful. Imagine looking at a clock and then looking outside. For much of the year, the sun's position does not behave as it would in Toronto, London, Tokyo, or almost anywhere else. The polar environment challenges everyday assumptions. Day and night, morning and evening, sunrise and sunset. All of these concepts become stretched. At the pole, the planet itself seems to move through time differently. Of course, Earth's rotation remains exactly what it is, but our experience of that rotation changes dramatically. Antarctic research stations provide small islands of human activity within this enormous landscape. Scientists and support workers live in specialized facilities designed to withstand extreme conditions. Some stations operate year-round. Others are occupied primarily during the Antarctic summer. Inside, people can work, eat, sleep, communicate, conduct experiments, and maintain equipment. Outside, the environment may be brutally cold. The contrast can be striking. A person can be sitting inside a warm research building while only a few meters away the wind is sweeping across the snow. The station becomes a small artificial ecosystem. Power must be generated. Food must be transported or stored. Water must be produced or treated. Waste must be carefully managed. Equipment must be maintained. Communication systems must remain functional. In such an isolated environment, ordinary conveniences become significant. A warm cup of tea can feel wonderful. A working heater can become essential. A reliable radio can connect an isolated station with the outside world. Antarctica teaches people to appreciate simple things. One of the most famous research stations is McMurdo Station. Located on Ross Island, it is one of the largest scientific communities in Antarctica. It serves as an important base for research and logistics. During the Antarctic summer, activity increases significantly. Aircraft arrive. Ships deliver supplies. Researchers travel into the field. Scientific equipment is transported across the ice. And temporary communities develop around research operations. Yet even at a large station, the surrounding landscape remains enormous. Walk far enough away, and human infrastructure quickly disappears. Beyond the buildings are mountains, glaciers, sea ice, and ocean. The contrast between human activity and the surrounding wilderness is immense. A small group of people can be surrounded by a continent larger than Europe. It is difficult to imagine a stronger reminder of scale. Antarctic research stations also experience unusual seasonal rhythms. During the summer, there can be almost continuous daylight in many areas. Researchers may work long hours because darkness does not naturally signal the end of the day. During winter, the opposite happens. The sun disappears. Temperatures drop. Many stations become much more isolated. The number of people may decrease. Aircraft operations become extremely limited in some locations. Travel becomes difficult. The station's inhabitants may spend long periods inside. This creates psychological and logistical challenges. Human beings evolved in environments with regular cycles of daylight and darkness. Antarctica can disrupt those cycles. Artificial lighting, carefully planned schedules, exercise, social interaction, and routines become important. Even sleep can become unusual when the sun does not behave normally. A person may wake up in the middle of the day and see complete darkness outside, or they may step outside at midnight and find the sun shining across the horizon. The continent forces people to separate their internal sense of time from the movement of the sun. The cold itself creates fascinating physical effects. At very low temperatures, water behaves differently from how we normally experience it. Snow crystals can form intricate structures. Ice can become extremely brittle. Metals contract. Lubricants become thick. Batteries perform differently. Mechanical systems that work perfectly in warmer environments may fail. Even simple tasks can become complicated. A small mistake in clothing can matter. Exposed skin can lose heat rapidly. Breathing cold air can feel harsh. And condensation can freeze onto surfaces. Researchers therefore use specialized equipment designed for polar conditions. Vehicles, clothing, shelters, scientific instruments, and communication systems all have to function in extreme environments. Antarctica is not forgiving toward poorly designed equipment. Everything must be carefully planned. Snow itself can behave in surprisingly different ways. Fresh snow is often light and powdery, but as it accumulates, pressure changes its structure. Wind can compact it. Temperature changes can alter its crystals. Repeated cycles of melting and freezing can create harder surfaces. Over long periods, the snow gradually transforms into firn and eventually glacier ice. Firn is an intermediate stage between snow and dense glacial ice. It consists of partially compacted snow that has survived at least one season and continues to become denser. Eventually, enough pressure removes most of the air spaces. The material becomes solid glacier ice. This transformation can take decades or longer, depending on local conditions. The snow that falls today may therefore begin a journey that lasts far beyond a human lifetime. It may eventually become part of a glacier. The glacier may flow for centuries. And eventually, the ice may reach the ocean. A single snowflake can become part of a process that unfolds over enormous spans of time. Antarctica's snow can also be transported by wind. In some regions, strong winds move snow across the surface and deposit it elsewhere. This can create dunes made entirely of snow. Snow dunes may form when wind repeatedly transports and accumulates snow in particular locations. They can resemble desert dunes, but their material is frozen water. The shapes shift with the wind. The surface becomes patterned. Ridges and hollows develop. From above, the landscape can resemble a frozen desert. This is another reason Antarctica is sometimes called a polar desert. It combines two environments that seem contradictory to the imagination: a desert and a continent dominated by ice. But both descriptions are accurate. The continent contains enormous quantities of frozen water while receiving very little precipitation in much of its interior. The Antarctic plateau can be so dry that the sky appears extraordinarily clear. Cloud formation is limited in some regions. Moisture is scarce, and the air is extremely cold. This combination creates a landscape where visibility can extend for enormous distances. On a clear day, mountains may be visible far beyond what would be expected in a more humid environment. There is little atmospheric haze. The horizon can appear incredibly sharp. The result is a strange sense of openness. The landscape seems to have no end. The sky seems enormous, and the distance between objects becomes difficult to judge. This vastness can produce a sense of calm. There is nothing demanding your attention. No flashing signs, no advertisements, no traffic, no buildings filling the horizon. Only space. Antarctica is also one of the few places on Earth where you can experience what scientists call katabatic cloud effects and blowing snow conditions on an enormous scale. When winds become strong enough, snow can be lifted from the surface and carried through the air. The ground can disappear behind a veil of white. The sky can blend into the horizon. Visibility can become extremely poor. These conditions are sometimes called whiteouts. A whiteout is not necessarily a snowstorm. It can occur when light is scattered by snow and clouds so evenly that the landscape loses contrast. The horizon disappears. Shadows vanish. Depth becomes difficult to perceive. Everything becomes white. For someone unfamiliar with the environment, it can be disorienting. The world loses its edges. A flat surface can look like a wall. A small slope can appear invisible. This is why Antarctic travel requires careful navigation and specialized equipment. The continent can erase its own landmarks. The lack of visible landmarks is one reason GPS and modern navigation systems are so important in Antarctica. Researchers can use satellite positioning to track their locations. Aircraft can navigate across enormous featureless areas. Vehicles can follow carefully planned routes. Scientific teams can locate remote field sites. But technology is not the only navigation tool. Researchers also study maps, satellite imagery, weather conditions, terrain, and traditional surveying methods. Antarctic navigation requires understanding the environment. A route that looks safe on a map may become dangerous if a crevasse develops. A snow bridge may cover a hidden crack. A weather system may arrive unexpectedly. The continent is constantly changing, so navigation is never simply about knowing where you are. It is also about understanding what the landscape is doing. Crevasses are among the most dangerous features of glaciers. They form when flowing ice is stretched. The surface can crack. Some crevasses are narrow. Others can be enormous. They may be hidden beneath snow. A layer of snow can create a bridge over a deep crack, making the surface appear safe. This is why Antarctic field teams use careful procedures when traveling across glaciated terrain. They may travel roped together. They may use specialized vehicles. They may examine satellite imagery. They may probe suspicious areas. The danger is not always visible. A perfectly smooth white surface may conceal a deep fracture. The hidden landscape is one of Antarctica's defining characteristics. So much of what matters is beneath the surface, beneath the ice, beneath the snow, beneath the ocean, and sometimes beneath the appearance of calm. Yet for all its dangers, Antarctica can also be incredibly peaceful. There are places where the silence is extraordinary. Without traffic, forests, insects, or large human populations, the background sound can become extremely low. Researchers have described moments when the environment feels almost completely silent. The silence isn't absolute. Wind may move, ice may crack, snow may shift, animals may call. But compared with a city, the difference is profound. The human brain is accustomed to constant background noise. Air conditioners, cars, phones, people, machines, electrical systems. Antarctica can remove much of that. The result can feel almost surreal. A person may suddenly notice their own breathing, their footsteps, the movement of clothing, the sound of wind. Small sounds become noticeable because the larger background disappears. For a few moments, the continent can feel like the world has been muted. Even the ice can make sounds. Glaciers can crack under pressure. Ice shelves can fracture. Sea ice can expand and contract with changing temperatures. When water freezes, its structure changes. When sea ice moves against itself, it can create grinding and popping sounds. Sometimes cracks travel through frozen surfaces with sudden noises. A massive ice shelf may make deep booming sounds as it responds to tides and stress. These sounds can travel through the ice and water. Scientists can record them. They can use seismic instruments to monitor movement. The frozen continent, therefore, has its own acoustic landscape. It is not silent. It simply speaks in frequencies and sounds that are often unfamiliar to humans. The ocean beneath sea ice can also be surprisingly active. Fish move through the darkness. Seals hunt. Krill gather. Currents flow. Water circulates beneath floating ice. Even when the surface appears completely frozen, the ecosystem beneath continues functioning. Sea ice creates a boundary between two worlds. Above it is frozen air. Below it is liquid seawater. Some animals move between both environments. Penguins enter the water through openings in the ice. Seals maintain breathing holes. Fish swim beneath. Algae grow in association with the underside of the ice. The boundary is therefore not an empty wall. It is a living interface. Antarctic fish have developed some of the strangest adaptations in the animal kingdom. Certain Antarctic fishes belong to a group known as notothenioids. Many have evolved special adaptations that allow them to survive in extremely cold seawater. Some produce antifreeze proteins. These proteins help prevent ice crystals from growing inside their body fluids. Without such adaptations, the freezing point of their body fluids could become a serious problem. The ocean around Antarctica is cold enough that ordinary physiological systems would struggle. But evolution has produced solutions. The fish have developed proteins that interfere with the growth of ice crystals. In effect, their bodies contain a biological defense against freezing. It is a remarkable example of evolution responding to environmental pressure. Cold creates a problem. Biology finds a solution. And over generations, that solution becomes part of the species. Antifreeze proteins are especially fascinating because they demonstrate that the word antifreeze does not have to refer to a chemical poured into an engine. Nature has its own antifreeze systems. The proteins bind to tiny ice crystals and prevent them from growing. This allows certain fish to survive in water that is below the normal freezing point of fresh water. The surrounding ocean remains liquid because seawater contains salt, but the fish themselves still need protection. Their body fluids are not simply seawater. Without specialized adaptations, ice formation could damage cells and tissues. Antifreeze proteins provide protection. This is one of the many ways Antarctic animals have evolved around the unusual chemistry of their environment. Some Antarctic fish also have unusual blood characteristics. Certain species have reduced levels of hemoglobin compared with most other vertebrates. The reason relates partly to the oxygen-rich nature of cold water. Cold water can hold more dissolved oxygen than warm water. This allows some Antarctic fish to survive with physiological systems that would be difficult to support in warmer environments. Their bodies have adapted to a very specific ecological niche. They are not simply ordinary fish living in cold water. Their entire physiology reflects the environment. Their blood, their metabolism, their proteins, their body structure, their behavior, all have been shaped by millions of years of evolution. The cold Antarctic Ocean can therefore be thought of as an evolutionary laboratory. Species that could not cope with the environment disappeared. Those that possessed useful traits survived and reproduced. Over enormous spans of time, specialized adaptations accumulated. The result is an ecosystem filled with organisms that seem almost designed for the cold. But there was no designer required. Natural selection can gradually shape populations. Small variations occur. Environmental pressures favor certain traits. Those traits become more common. Generations pass. Eventually, an animal can become highly specialized. Antarctica provides some of the clearest examples of this process. And yet the continent is not entirely without plants. Most terrestrial plant life is concentrated in relatively mild coastal regions, especially around the Antarctic Peninsula. There are mosses, there are lichens, there are microscopic algae, there are a few flowering plants. These plants are highly adapted to the short growing season. They must make use of brief periods when conditions are suitable. During summer, sunlight becomes abundant. Temperatures can rise enough for biological activity. Snow melts in certain areas. Liquid water becomes available. Plants can grow. Then winter returns. Darkness settles. Temperatures fall. The growing season ends. The cycle repeats. The plants do not need to dominate the landscape. They simply need to survive. In Antarctica, survival itself is a remarkable achievement. The Antarctic Peninsula supports some of the continent's most recognizable flowering plants. Two native vascular plants grow there, Antarctic hairgrass and Antarctic pearlwort. Compared with forests or grasslands elsewhere, their presence is tiny, but their existence is scientifically significant. They demonstrate that even on a continent dominated by ice, flowering plants can survive. The plants take advantage of relatively mild microclimates. They grow where conditions are favorable. They tolerate cold. They survive seasonal darkness. And they reproduce during the short summer. The landscape around them may contain enormous glaciers and snow-covered mountains. Yet beneath your feet, a tiny flowering plant may be quietly growing. It is a reminder that Antarctica is not completely lifeless. Life is simply concentrated in the places where the environment allows it. The continent's microbial life is even more diverse than its visible vegetation. Microorganisms can live inside rocks. Some inhabit salty environments. Some survive in extremely cold soils. Others exist within ice. These organisms are difficult to see without microscopes, but they are essential to Antarctic ecosystems. They break down organic material. They participate in nutrient cycles. They interact with minerals. They influence soil chemistry, and they provide clues about the limits of life. Some microorganisms can enter dormant states when conditions become unfavorable. When water becomes available or temperatures rise slightly, activity can resume. This ability to wait is one of the great survival strategies of Antarctic life. Instead of fighting the environment continuously, organisms can slow down. They conserve energy. They endure. And when conditions improve, they become active again. The concept of dormancy is especially important in polar ecosystems. Winter can create months of darkness. Food becomes scarce. Water freezes. Temperatures fall. For some organisms, continuing normal metabolism would be impossible. Instead, they reduce activity. Their biological processes slow dramatically. They wait for better conditions. This strategy can be found in many forms throughout nature, but Antarctica pushes it toward extremes. Life must sometimes endure long periods of environmental stress before favorable conditions return. The ability to pause can be as important as the ability to grow. As we continue across this frozen continent, it becomes clear that Antarctica is not defined simply by cold. It is defined by extremes. Extreme dryness, extreme seasonal darkness, extreme daylight, extreme winds, extreme isolation, extreme distances, extreme geological history, and extreme biological adaptations. Yet within these extremes, there is also an unexpected beauty. The continent does not need forests to be alive. It does not need cities to be important. It does not need warm temperatures to support remarkable ecosystems. It simply operates according to its own rules. Snow falls. Ice forms. Glaciers move. The ocean circulates. Krill gather. Whales arrive. Penguins breed. Auroras glow. Volcanoes release heat. And beneath everything, Earth continues turning. Imagine now that night has fully settled over the Antarctic interior. The sun has disappeared below the horizon. The landscape is dark. The snow reflects a faint amount of starlight. Above you, the southern lights begin to appear. At first, perhaps only a faint green glow. Then a brighter ribbon. It stretches across the sky. It moves slowly. The colors shift. The stars remain behind it. Below, the ice extends toward the horizon. There is no city nearby, no road, no familiar sound, only the wind. Far away, a research station glows softly against the darkness. Somewhere beneath the ice, ancient air remains trapped in frozen layers. Somewhere below that, geological structures have been waiting for millions of years. And beneath everything, Earth's warmth still rises from the deep interior. Antarctica is cold, but the planet beneath it is not. The frozen surface is only a thin expression of a much warmer Earth below. And perhaps that is one of the most beautiful things about this continent. It looks still. It looks frozen. It looks almost timeless. But underneath the surface, everything is moving. Ice flows, water circulates, rock changes, heat rises, life adapts. The planet never truly stops. So, as you begin to drift towards sleep, imagine the Antarctic wind becoming softer. The aurora slowly fades. The stars remain. The mountains become silhouettes. The ocean continues moving beneath the sea ice. A distant seal disappears into dark water. Penguins rest together on the frozen surface. And far inland, thousands of meters of ancient ice quietly preserve the memory of Earth's atmosphere. Nothing needs to happen quickly. Antarctica has never been a place of hurry. Its story is written in centuries. Its landscapes change over millennia. Its rocks remember millions of years. Its oldest ice carries memories from hundreds of thousands of years ago. And tonight, you can simply rest beside that enormous sense of time. Let the world become quiet. Let your thoughts slow. Let the frozen continent stretch endlessly through your imagination. there is still much more waiting beneath the ice. More hidden lakes, more ancient landscapes, more extraordinary animals, more strange weather, more geological mysteries, more stories preserved in snow and stone. And when we return, our journey will continue deeper into the secrets of Antarctica. For now, breathe slowly, relax, and let the cold, quiet landscape carry you gently towards sleep. The Antarctic night is deep now. Far above the frozen continent, the stars stretch across the darkness in a sky almost untouched by artificial light. The wind moves gently over the ice. Somewhere in the distance, a glacier is slowly flowing toward the sea. Below the surface, ancient water rests in darkness. And beneath that water, beneath kilometers of frozen material, the rock of Antarctica continues its slow geological journey. There is something comforting about realizing how slowly this landscape changes. A human life can feel long when measured from one birthday to the next, but Antarctica measures time differently. A glacier may need centuries to move through a valley. A mountain may take millions of years to rise and erode. Snow can become ice and preserve atmospheric history for hundreds of thousands of years. The continent invites us to think in a slower way. So tonight, there is no need to hurry. Let your breathing become steady. Let your body become comfortable. And allow the frozen landscape to unfold gradually in your imagination. We will continue exploring Antarctica, moving from the hidden world beneath its ice toward the strange creatures, ancient landscapes, and powerful natural forces that have shaped this remarkable continent. One of Antarctica's greatest secrets lies beneath the enormous ice sheet. Scientists have discovered that the bedrock beneath the ice is not simply dry and frozen everywhere. There are extensive systems of water. Some water collects in lakes. Some moves through channels. Some exists as thin films beneath glaciers. This hidden water can influence the movement of ice above it. When water exists between a glacier and the bedrock, it can reduce friction. The ice may slide more easily. In this way, water hidden beneath kilometers of ice can affect what happens at the surface. A glacier that appears completely frozen may therefore be partly supported by a layer of water moving far below. This is one of the reasons scientists study the base of the Antarctic ice sheet so carefully. The hidden boundary between ice and rock is incredibly important. It is where the enormous weight of the ice meets the solid continent. And sometimes, between those two worlds, there is liquid water. The pressure at the bottom of the Antarctic ice sheet is enormous. Imagine standing beneath a mountain made of ice. Layer after layer is pressing downward. Snow that fell long ago is buried beneath newer snow. Over time, the weight accumulates. The deeper you go, the greater the pressure becomes. This pressure changes the physical properties of ice. At sufficient depths, the ice behaves differently from the snow and surface ice above it. It can deform more easily. It can slowly flow. It can become part of enormous underground systems. The ice sheet is therefore not a solid block in the ordinary sense. It is a vast, slowly moving body. Its surface may appear smooth and permanent. Its interior is constantly responding to gravity and pressure, and its base interacts with the land and water beneath it. There are also areas where the ice sheet becomes remarkably thin. Along parts of the coast, ice can flow through narrow channels between mountains. These channels can guide glaciers toward the ocean. Some valleys buried beneath the ice are enormous. Scientists can use radar to map them. The radar sends signals through the ice. Those signals reflect from different surfaces. By analyzing the returning signals, researchers can reconstruct the shape of the hidden landscape. The technology is extraordinary because it allows humans to see without actually seeing. There may be no window, no camera, no exposed rock, only kilometers of ice. Yet beneath it, mountains and valleys become visible through careful measurement. It is almost like using sound to imagine a landscape hidden behind a wall. One of the most spectacular hidden structures is the network of subglacial valleys beneath West Antarctica. Some valleys extend for hundreds of kilometers. They can guide the movement of water beneath the ice. They can influence where glaciers flow. And they reveal that the Antarctic landscape beneath the ice is far more dramatic than the surface suggests. If you could somehow remove the ice without changing the land beneath it, you would see a continent of enormous geological complexity. Some regions would contain mountain ranges. Others would contain deep basins. There would be valleys carved by ancient rivers and glaciers. There would be areas below present sea level. And there would be landscapes that have not seen open air for immense periods of time. The ice hides an entire world. West Antarctica and East Antarctica are also very different. East Antarctica contains a massive, high, relatively stable ice sheet. West Antarctica is lower and contains several regions where ice rests on bedrock below sea level. This makes the West Antarctic ice sheet particularly sensitive to interactions between ocean water and ice. Warm ocean water can enter beneath floating ice shelves. When it reaches the underside of ice, it can contribute to melting. The process is difficult to observe directly because the critical interactions occur beneath floating ice. Scientists therefore combine satellite observations, ocean measurements, aircraft surveys, computer models, and field research. The goal is to understand how the system changes. The Antarctic ice sheet is not simply responding to air temperature. The ocean matters enormously. Wind patterns matter. Ocean currents matter. The shape of the seafloor matters. The thickness and structure of ice shelves matter. Everything interacts. The ocean beneath an ice shelf can be dark. There is no direct sunlight. Yet in some locations, life has been found beneath floating ice shelves. This is one of the more surprising discoveries in Antarctic research. Scientists have observed organisms living in environments that receive little or no sunlight. The ecosystems are extremely limited compared with open ocean environments. But their existence demonstrates that life can persist even when ordinary sources of energy are scarce. In some places, nutrients may be carried by currents. Organic material may sink from more productive waters. Chemical energy may support certain microorganisms. The details vary between environments, but the basic lesson is profound. Life does not always need sunlight directly. On Earth, organisms have evolved ways of surviving using different energy sources. Antarctica continues to reveal how flexible life can be. Deep beneath the ocean, some microorganisms can obtain energy through chemical reactions. This phenomenon is not unique to Antarctica. Similar systems exist around the world. But Antarctic environments provide opportunities to study how life functions under cold, dark, and nutrient-poor conditions. These organisms may seem insignificant compared with penguins and whales. Yet microorganisms perform fundamental roles. They transform chemicals. They cycle nutrients. They support food webs. They influence the chemistry of their environments. Without microscopic life, the larger Antarctic ecosystem could not function. The continent's most visible animals are only the upper layers of a much deeper biological system. The Antarctic food web begins with organisms that are almost invisible. Phytoplankton drift near the surface of the Southern Ocean. They capture sunlight. They use carbon dioxide and nutrients to build organic matter. Then they become food. Krill consume them. Fish consume krill. Penguins consume fish and krill. Seals consume fish and penguins in some cases. Whales consume enormous quantities of krill. Seabirds feed on fish and other marine organisms. The energy travels upward through the ecosystem. Eventually, organisms die. Their remains sink. Microorganisms break them down. Nutrients return to the environment. The cycle begins again. This constant movement of matter and energy allows the ecosystem to continue. Even in the extreme Antarctic environment, the basic principles of ecology remain. Krill deserve another moment of attention because their role is so enormous. Antarctic krill are small, but their populations can be immense. Large swarms can occupy huge areas of ocean. When conditions are favorable, concentrations of krill become feeding grounds for whales, seals, penguins, and birds. Their abundance depends on the productivity of the Southern Ocean. Phytoplankton are especially important. When sunlight returns during the Antarctic summer, microscopic plant-like organisms can multiply. Krill feed on this productivity. The ocean becomes a seasonal buffet. Whales arrive. Penguins travel. Seals hunt. Birds gather. The entire ecosystem responds to the increase in available energy. Antarctica's summer is therefore not simply a season of warmer weather. It is a biological transformation. The ocean comes alive. Some whales travel to Antarctica from remarkably distant regions. Humpback whales are especially famous for long migrations. They spend part of the year in warmer waters where they breed and give birth. Then they travel toward polar feeding grounds. The journey can cover thousands of kilometers. Young whales must learn the route. Adults may return repeatedly to the same feeding regions. The migration connects ecosystems across the planet. A whale feeding near Antarctica is part of a life cycle that may also include tropical or subtropical waters. This means the fate of Antarctic ecosystems can affect animals that spend part of their lives far away. The same whale can experience dramatically different environments during one year. Warm water, cold water, tropical sunlight, polar summer, different food sources, different predators, different habitats. Its body carries it between worlds. Humpback whales also produce complex sounds. In the Antarctic environment, these sounds can travel through the ocean over considerable distances. The underwater world is acoustically very different from the world above. Sound travels efficiently through water. Whales can communicate across distances that would be difficult for visual signals. Their songs and calls can form part of the seasonal soundscape of the Southern Ocean. Imagine being beneath the sea ice. The surface above is frozen. The water is dark. And somewhere in the distance, a whale calls. The sound travels through the water. You cannot see the animal, but you can hear evidence that something enormous is moving through the darkness. The Antarctic Ocean has its own language of sound. Seals also use sound beneath the ice. Weddell seals are particularly vocal. Researchers have recorded whistles, trills, and other calls beneath Antarctic sea ice. The sounds can be surprisingly complex. For a seal living in an environment where visibility may be poor, sound becomes an important form of communication. The underwater world may be dark for long periods. A seal cannot always rely on sight. Sound can travel through the water. It can help animals locate one another. It can help establish territory. It can support social behavior. The frozen surface, therefore, does not make the environment silent. Beneath the ice, it can be filled with sound. Weddell seals are among the deepest diving seals in the Antarctic region. They can remain underwater for extended periods. Their bodies are designed to store and manage oxygen efficiently. Before diving, they can increase the amount of oxygen available in their blood and muscles. During the dive, their heart rate can slow. Blood flow becomes carefully controlled. Less critical tissues receive reduced circulation. More oxygen is directed toward essential organs. These adaptations allow the seal to remain underwater far longer than a human could without equipment. The animal enters the dark ocean beneath the ice as naturally as a human walks into a room. For the seal, the freezing water is home. A Weddell seal may also use its teeth to maintain breathing holes in sea ice. As ice thickens, openings can become difficult to maintain. The seal scrapes and bites at the ice. It must keep access to air. A breathing hole is more than a convenient opening. It is a lifeline. Without access to the surface, the seal cannot breathe. The animal may therefore spend considerable effort maintaining these openings. In an environment where the surface freezes around you, something as simple as a hole in the ice becomes essential. The difference between life and death can be a few centimeters of open water. Penguins face a similar relationship with the boundary between ice and ocean. For many penguins, the sea provides food. The ice provides resting areas and breeding habitat. The animals repeatedly cross between these environments. They may spend hours swimming underwater. Then they return to the ice. The transition is constant. For humans, entering water near freezing would be a serious physical challenge. For penguins, it is ordinary life. Their feathers provide insulation. Their bodies store energy. Their streamlined shapes reduce drag, and their flippers allow powerful movement through the water. Penguins are birds, but their bodies have become highly specialized for swimming. Their wings no longer function primarily as tools for flight through the air. Instead, they act as underwater propulsion systems. Evolution has transformed the basic structure of a bird's wing into a remarkably effective underwater flipper. Emperor penguins can dive surprisingly deep. Some individuals have been recorded reaching depths of more than 500 meters. At those depths, the pressure is enormous. Light is greatly reduced. The water remains extremely cold, and the penguin must carefully manage its oxygen. The ability to dive so deeply allows emperor penguins to reach prey unavailable closer to the surface. Their bodies can withstand pressure changes. Their bones and respiratory systems have characteristics that support diving. Their muscles store oxygen. Their metabolism can adjust, and their behavior is coordinated with the availability of prey. A bird that cannot fly through the air becomes a remarkable underwater hunter. The penguin is a reminder that evolution does not follow one simple direction. Some birds became better at flying. Penguins became better at swimming. Emperor penguins also have an unusual relationship with winter. Their breeding cycle is timed so that chicks can develop during the Antarctic winter. This is risky. Winter brings darkness. Temperatures fall. Winds increase. Sea ice expands. Food can become difficult to access. Yet the timing allows chicks to become independent around the beginning of the warmer season, when food becomes more available. The entire breeding cycle is therefore synchronized with the Antarctic environment. Egg laying, incubation, hatching, chick growth, feather development, independence. Everything must happen at the appropriate time. If timing fails, survival becomes more difficult. In Antarctica, seasonal timing can determine whether an animal thrives or struggles. The emperor penguin's body is also exceptionally well insulated. Its feathers are densely packed. The birds have layers of feathers that trap air. Their bodies store fat. Their legs and feet are adapted to reduce heat loss. Blood vessels can regulate heat exchange. The result is a bird capable of surviving conditions that would be dangerous for most animals. The penguin does not simply tolerate the cold. It has been shaped by the cold. Its entire body reflects the environment. The black and white coloring of penguins also has a useful function. From above, the dark back can blend with the darker ocean. From below, the pale belly can blend with the bright surface of the water. This type of coloration is known as countershading. It can make an animal more difficult to detect. A predator looking upward may see a pale underside against the bright surface. A predator looking downward may see a dark back against deeper water. The penguin's colors are therefore not merely attractive. They are part of an evolutionary strategy. The Antarctic environment also supports enormous seabird colonies. Albatrosses, petrels, skuas, and other birds travel across the Southern Ocean. Some species spend much of their lives at sea. Albatrosses are especially remarkable because of their ability to fly enormous distances. Their long wings allow them to glide using wind energy. Instead of constantly flapping, they can use dynamic soaring. They move through gradients of wind speed to gain energy. This allows them to travel vast distances while using relatively little muscular effort. Some albatross species have extraordinarily large wingspans. They can remain at sea for long periods. Their lives are connected to the ocean rather than to land. The Southern Ocean can be incredibly rough. Strong winds generate large waves. The Antarctic circumpolar current moves continuously around the continent. Storm systems can develop rapidly. For ships, the waters can be challenging. Yet seabirds can navigate these conditions with remarkable skill. They can soar over waves. They can glide for long periods. They can land on the water and rest. Their bodies are adapted to marine life. Some species can drink seawater because specialized glands remove excess salt. This is another example of adaptation. The ocean contains plenty of water, but seawater is too salty for most terrestrial animals to drink safely. Seabirds have evolved mechanisms to deal with the salt. The excess is excreted through specialized salt glands. The bird can therefore use an environment that would be problematic for many other animals. Antarctic skuas provide another example of life adapting to the polar environment. They are opportunistic predators and scavengers. They may feed on fish, eggs, chicks, carrion, and other available food. They can live in areas where resources are seasonal. During the breeding season, they become strongly territorial. They defend nesting areas. They interact with penguin colonies. They may steal food. Their behavior is flexible. In an environment where food availability changes rapidly, flexibility is valuable. An animal that can eat several kinds of food may survive when one source becomes scarce. The relationship between penguins and skuas can therefore become complicated. Penguins must protect their eggs and chicks. Skuas may attempt to take them. Adult penguins defend their nests. Colonies become noisy and active. The scene is very different from the silent Antarctic interior. Thousands of birds may gather in a relatively small area. Calls echo. Wings move. Parents search for chicks. Predators patrol the edges. The colony becomes one of the busiest biological places on the continent. This is another important contrast. Antarctica is not uniformly quiet. Some areas are among the most active wildlife environments on Earth. Penguin colonies can contain thousands or even hundreds of thousands of individuals. From a distance, The colony may appear like a dark patch against the snow. As you approach, it becomes a moving mass of birds. Each individual has its own behavior, yet the colony functions collectively. Penguins recognize calls. Parents identify chicks. Individuals navigate through crowds. The density provides certain advantages. There is warmth, protection, access to breeding partners, and safety through numbers. But it also creates competition. Space is limited. Food must be found. Predators remain nearby. The colony is both a community and a survival environment. Penguins can also travel considerable distances across sea ice. Emperor penguins may walk many kilometers between breeding colonies and feeding areas. Their bodies are not built for speed on land. They waddle. They sometimes slide on their bellies, pushing with their feet and flippers. This behavior, often called tobogganing, can make travel across snow more efficient. The penguin lies on its belly and uses its flippers and feet to move forward. On a smooth surface, sliding can require less energy than walking. Again, evolution has produced behaviors suited to the environment. The same bird that swims efficiently underwater has also developed a practical way of traveling across ice. The Antarctic landscape also contains vast mountain ranges. The Transantarctic Mountains are among the most important. They stretch across the continent and separate major geographic regions. Some peaks rise dramatically above the ice. Others are partly buried. The mountains influence the movement of glaciers and air. They can create valleys where snow behaves differently. They can also expose ancient rock. In certain places, the mountains are almost free of ice. These exposed regions are valuable to geologists because they provide direct access to the underlying rocks. Instead of drilling through kilometers of ice, researchers can simply study the exposed surface. The rocks reveal the geological history of Antarctica. Minerals, fossils, faults, ancient volcanic material, metamorphic structures, all become part of the story. One of the most remarkable features of the Transantarctic Mountains is their extreme dryness in certain regions. The McMurdo Dry valleys lie near the mountains. Some valleys receive so little precipitation that they resemble terrestrial deserts. Strong winds can remove snow. Cold conditions prevent significant melting. The landscape contains exposed rock, gravel, and ice. There are no forests, almost no visible vegetation. Yet microbial communities survive in protected environments. The dry valleys are therefore an excellent example of how life can exist at the edge of habitability. The dry valleys also contain ancient ice. Some ice deposits may have survived for extremely long periods. They can preserve environmental information. The surrounding landscape contains minerals and sediments that reveal past conditions. Scientists use these clues to reconstruct climate history. The valleys are like a natural laboratory where geological, atmospheric, and biological processes can be observed together. They also provide an environment for testing instruments designed for extreme conditions. If a rover, sensor, or scientific instrument can function reliably in the dry valleys, researchers gain useful information about how it might operate in other harsh environments. This is one reason Antarctica has been used as an analog for Mars. The analogy is not perfect. Mars is much colder in many regions. Its atmosphere is extremely thin. Its surface chemistry is different. There is no stable liquid water flowing freely across the surface today. But both environments contain extreme cold, dryness, isolation, and landscapes shaped by ice and wind. Antarctic research can therefore help scientists understand how geological and biological processes operate under harsh conditions. It can also help test equipment before sending it into space. Researchers can practice remote operations. They can study how humans cope with isolation. They can test autonomous instruments. They can examine how microorganisms survive under stress. Antarctica becomes a kind of training ground for planetary science. Even the color of Antarctic snow can tell scientists something. Fresh snow is generally bright because it reflects much of the incoming sunlight. But dust, algae, microorganisms, and other materials can change its appearance. In some regions, snow may develop subtle pink, red, green, or orange tones because of microorganisms. These organisms contain pigments that protect them from intense sunlight. The phenomenon is sometimes called snow algae. To a casual observer, the color may seem strange. But under a microscope, the cause becomes clear. Tiny organisms are living within or on the snow. The frozen surface becomes a habitat. Again, what looks empty from a distance may be full of life at microscopic scales. Antarctic microorganisms can also survive intense ultraviolet radiation. The atmosphere over the continent has unusual chemistry, and seasonal ozone depletion has historically allowed more ultraviolet radiation to reach the surface during certain periods. Organisms exposed to strong ultraviolet radiation can experience cellular damage. Some have protective pigments. Others have efficient DNA repair mechanisms. Their survival provides researchers with clues about how life responds to radiation stress. This has implications beyond Antarctica. Radiation is one of the challenges humans and organisms would face on other planets. Understanding natural protection mechanisms can help scientists study the broader limits of life. The Antarctic ozone hole is one of the best-known atmospheric phenomena associated with the continent. It is not a literal hole in the atmosphere. Rather, it is a region where ozone concentrations in the stratosphere become unusually low during certain times of the year. The phenomenon became especially prominent during the 20th century due to human-made chemicals such as chlorofluorocarbons. These chemicals could reach the stratosphere, where sunlight initiated chemical reactions that destroyed ozone. The Antarctic atmosphere provided conditions that allowed the process to become especially pronounced. International action eventually reduced the production of many ozone-depleting substances. The ozone layer is now expected to recover gradually over coming decades, although the process is slow. Antarctica therefore became central to one of the most important examples of international environmental cooperation. The story of the ozone layer also demonstrates how interconnected Earth systems are. Chemicals released far from Antarctica could eventually influence atmospheric chemistry above the continent. The sun's ultraviolet radiation triggered reactions. Stratospheric temperatures affected the chemistry. Polar clouds provided surfaces for reactions. And atmospheric circulation transported gases. A problem could therefore begin thousands of kilometers away and become visible over the South Pole. Earth's atmosphere is a single connected system. Antarctic clouds can also behave differently from clouds in warmer regions. The extremely cold atmosphere allows ice crystals to form under conditions that are rare elsewhere. Polar stratospheric clouds can become important in atmospheric chemistry. These clouds form at very high altitudes and extremely low temperatures. They provide surfaces where chemical reactions can occur. During the Antarctic winter, the stratosphere can become cold enough for them to develop. Then, when sunlight returns in spring, chemical reactions accelerate. This contributes to the seasonal cycle of ozone depletion. The sky above Antarctica is therefore not merely a beautiful backdrop. It is an active chemical environment. The return of sunlight in Antarctic spring is especially important. After months of darkness, sunlight begins to reach the atmosphere again. Photochemical reactions accelerate. The ozone chemistry changes. The surface begins receiving increasing amounts of solar energy. Sea ice starts its seasonal transition. Wildlife becomes more active. The continent slowly moves towards summer. The return of sunlight is not a single dramatic event everywhere. It happens gradually. Near the poles, the sun approaches the horizon. The sky begins to brighten. Then daylight becomes longer. Eventually, the sun remains above the horizon for extended periods. The continent emerges from darkness. For humans living at Antarctic stations, the return of sunlight can have a powerful psychological effect. After months of darkness, seeing the sun again can feel like an event. The light changes the appearance of everything. Snow becomes brighter. Mountains become visible. Shadows return. The landscape feels larger. The darkness that had surrounded the station for months begins to retreat. For wildlife, the return of sunlight is equally important. Phytoplankton begin responding to increased light. Sea ice begins seasonal changes. Breeding cycles continue. Food availability changes. The entire ecosystem follows the rhythm of the sun. And now, as our journey moves deeper into the Antarctic summer, imagine the horizon slowly brightening. The darkness becomes blue. The blue becomes pale gold. The mountains emerge from shadow. Snow begins reflecting the light. The ocean catches the first glow. Far away, a penguin colony becomes visible. Birds begin calling. A seal rests beside a breathing hole. The world wakes slowly. Not suddenly, not noisily, but gradually. The same continent that endured months of darkness now enters a season of nearly endless light. Antarctic summer is a season of extraordinary biological activity. The sunlight may remain above the horizon for long periods. The ocean becomes more productive. Migratory animals arrive. Penguin colonies become active. Seals feed. Whales gather. Seabirds return. The continent becomes busier. Yet even during summer, much of Antarctica remains intensely cold. The interior is still dominated by ice. The difference is that sunlight is now available for longer periods. Energy enters the system. Life responds. The contrast between Antarctic winter and summer is one of the most dramatic seasonal transitions on Earth. In winter, sea ice expands. Darkness dominates. Temperatures fall. Many animals leave the region. In summer, sunlight returns. Sea ice retreats in many areas. Food becomes abundant. Migratory animals arrive. The same landscape can therefore feel like two different worlds depending on the season. A bay that is frozen solid in winter may become open water in summer. A coastline that appears empty may become crowded with animals. A research station that feels isolated in winter may become busy with aircraft and ships in summer. Antarctica changes with the seasons more dramatically than almost anywhere else. One of the most beautiful seasonal changes occurs when ice begins breaking apart. Sea ice fractures. Open water appears. Leads form between sheets of ice. These openings become important for wildlife. Seals can breathe. Penguins can enter the ocean. Birds can feed. Whales can reach the surface. The boundary between ice and water becomes fragmented. From above, it can resemble a giant mosaic. White ice, dark blue water, turquoise channels, shadows, and moving animals. The geometry changes constantly. Wind pushes the ice. Currents move it. Temperature alters its structure. The ocean gradually reclaims areas that were frozen during winter. Sea ice also plays an important role in reflecting sunlight. Bright ice reflects a significant portion of incoming solar energy back towards space. Dark ocean water absorbs much more. This means that when sea ice melts and exposes darker water, the surface can absorb more solar energy. That energy can contribute to further warming of the exposed water. This is part of a feedback process known as the ice albedo effect. Albedo simply refers to how reflective a surface is. Snow and ice have high albedo. Dark ocean water has much lower albedo. The contrast is important because the Earth's climate system responds not only to temperature, but also to how surfaces interact with sunlight. Antarctica provides one of the largest examples of this relationship. The same principle applies to snow. Fresh, clean snow can reflect a large amount of sunlight. But if snow becomes darker due to dust, soot, or other particles, its reflectivity decreases. More solar energy is absorbed. The surface can warm. The snow may melt more quickly under suitable conditions. This is why researchers study the composition of Antarctic snow. Tiny particles can influence the physical properties of enormous surfaces. A small amount of dark material spread across snow can have effects far beyond its size. Again, Antarctica shows how small things can influence enormous systems. Antarctic glaciers also interact with the ocean through fresh water. When ice melts or calves into the ocean, fresh water enters the marine system. Fresh water is less dense than seawater. Changes in salinity can therefore influence how water moves. The Southern Ocean is part of a global circulation system in which water sinks and rises according to differences in temperature and density. Antarctic processes can affect these movements. The ocean around Antarctica is therefore not merely receiving meltwater. It is participating in a much larger planetary circulation. Water that begins as Antarctic snow may eventually influence ocean chemistry and circulation far beyond the continent. The deep ocean around Antarctica is also important because cold, dense water can sink. When seawater becomes very cold and salty, it can become dense enough to descend into the deep ocean. This process contributes to the formation of Antarctic bottom water. That deep water can spread across the ocean floor into other ocean basins. In this way, Antarctica helps drive part of Earth's deep ocean circulation. A snowflake falling on the continent can eventually become part of a global ocean system. That is an extraordinary journey. Snow becomes ice. Ice eventually reaches the ocean. Water becomes cold and dense. It sinks. Then it moves through the deep ocean. Eventually, it may rise elsewhere. The planetary water cycle is much more complex than rain falling into rivers. Deep ocean circulation can take centuries to complete. Water moving through the abyss may travel slowly. A parcel of water that sinks near Antarctica can remain in the deep ocean for a very long time before returning toward the surface. The ocean therefore contains memories of its own. Different water masses carry different temperatures, salinities, dissolved gases, and chemical signatures. Oceanographers can identify them. They can trace where water originated. They can estimate how long it has been below the surface. Antarctica plays a major role in this enormous system. The continent is connected to the deep ocean through cold, dense water. This connection between Antarctica and the global ocean is one reason scientists pay close attention to changes around the continent. A change in Antarctic winds can influence ocean currents. A change in sea ice can affect salinity. A change in ice melt can add fresh water. A change in ocean circulation can influence heat transport. And changes in the ocean can influence ice shelves. The system contains feedback loops. One part affects another. The continent cannot be understood in isolation. To understand Antarctica, scientists must study the atmosphere, ocean, ice, land, and biology together. And so our quiet journey continues. The Antarctic summer light now stretches across the horizon. The ice glows. The ocean moves. Whales rise to breathe. Penguins gather along the shore. Tiny phytoplankton drift beneath the surface. Far below, cold water sinks into the deep ocean. Above the continent, clouds move slowly through the polar sky. And beneath the ice, ancient landscapes remain hidden. The continent is enormous, but the connections within it are even larger. Everything touches something else. The snow influences the ice. The ice influences the ocean. The ocean influences the atmosphere. The atmosphere influences the ice. The sun influences the ocean. The ocean feeds the krill. The krill feed the whales. And the entire system moves together. Tonight, you can let that interconnectedness become part of the quiet. There is no need to hold on to every detail. Just imagine the frozen continent beneath the stars. Imagine a glacier flowing almost imperceptibly. Imagine ancient air trapped inside blue ice. Imagine a seal moving through dark water. Imagine a whale calling beneath the sea. Imagine penguins resting together against the cold. Imagine the ocean carrying Antarctic water toward distant parts of the planet. And imagine the ice slowly preserving another layer of Earth's history. Time passes differently here. A snowfall becomes a layer. A layer becomes ice. Ice becomes a glacier. A glacier becomes an iceberg. An iceberg becomes seawater. The water enters the ocean. The ocean carries it away. Nothing is truly lost. It simply changes form. The wind becomes softer now. The Antarctic horizon fades into darkness. The last light disappears from the mountains. The Southern Ocean continues its endless movement. And beneath the frozen surface, hidden water flows through ancient valleys. The continent rests, but it is never completely still. There is movement everywhere. Slow movement, quiet movement, almost invisible movement. And perhaps that is what makes Antarctica such a peaceful place to imagine before sleep. Nothing here needs to happen quickly. Everything is part of a much longer story. A story written over hundreds of thousands, millions, and billions of years. And we are only visiting one small moment of it. For now, let yourself become still. Let the Antarctic night surround the imagination. Let the stars remain overhead. And as your thoughts grow quieter, remember that beneath the ice is an entire hidden world still waiting to be explored. There are ancient mountains, buried rivers, subglacial lakes, strange organisms, deep ocean currents, volcanic heat, ancient fossils, and landscapes that humans have only recently begun to understand. The journey will continue, slowly, quietly, across the frozen edge of our planet. The Antarctic night continues, quiet and immense. Far above the continent, stars shine through air so cold and dry that the sky can appear unusually clear. Below them, an endless white landscape stretches toward distant mountains. There are places here where you can travel for hours without seeing another person. Places where the horizon seems to continue forever. Places where the only movement comes from wind, drifting snow, flowing ice, or the slow passage of clouds. And yet, Antarctica is not empty. Beneath the snow are ancient rocks. Beneath the ice are lakes and rivers. Around the coastline are some of Earth's richest marine ecosystems. And hidden inside the frozen landscape are clues to climates that existed long before human beings walked across the planet. Tonight, we will continue drifting through these layers. We will explore some of Antarctica's deepest geological history, its strange hidden rivers, its unusual ice formations, and the remarkable ways that animals survive along the frozen edge of the Southern Ocean. You don't have to remember where one discovery ends and another begins. Just allow the story to move naturally. Imagine the cold landscape far away. Imagine the stars. Imagine the soft sound of wind crossing the ice. And let us continue. Long before Antarctica became covered by its enormous ice sheet, rivers flowed across parts of the continent. These ancient rivers carved valleys through the landscape. Some of those valleys still exist beneath the ice. Scientists can identify them through radar mapping and geological evidence. The modern Antarctic ice sheet hides these ancient river systems. But the land remembers where water once flowed. A valley carved by a river can remain visible in the underlying rock long after the river disappears. Later, glaciers may occupy the same valley. The direction of ancient drainage can influence modern ice movement. This means Antarctica contains landscapes shaped by water from climates that were dramatically different from today. The continent's modern frozen appearance can hide a much warmer past. There were periods when Antarctica had flowing rivers, wetlands, forests, and lakes. During those times, the continent was positioned differently relative to the rest of the world, and global temperatures were higher. Its high-latitude location still meant long periods of darkness and prolonged summer daylight. Yet plants adapted. Forests existed. Rivers carried sediment. Lakes collected water. Animals moved through the landscape. The fossil record preserves fragments of these ecosystems. A piece of fossilized wood can tell us that trees once grew where glaciers now dominate. A layer of ancient pollen can reveal what kinds of plants lived there. A fossil leaf can provide clues about temperature and rainfall. A rock can preserve the chemistry of an ancient environment. The frozen continent is therefore also an archive of a green continent. Antarctica's geological history stretches back more than 3 billion years. Some rocks on the continent are incredibly ancient. They formed when Earth itself was much younger. At that time, the planet looked completely different. Continents were smaller and arranged differently. The atmosphere had a very different composition. Life was largely microscopic. Oceans covered huge portions of the planet. Volcanic activity was widespread. Over geological time, continents grew and collided. Rock was melted and transformed. Mountains formed and eroded. New crust developed. Old crust disappeared. Antarctica participated in these processes. The rocks beneath its ice contain evidence of this ancient Earth. Some Antarctic rocks formed through metamorphism. Metamorphic rocks are rocks that have been changed by heat, pressure, or chemical processes without completely melting. A rock that begins in one form can become something entirely different after spending millions of years deep within Earth's crust. Pressure compresses minerals. Heat changes their structure. Fluids can move through cracks. Eventually, the rock rises toward the surface or becomes exposed through erosion. In Antarctica, ancient metamorphic rocks can be found in exposed mountain regions. They provide evidence of the immense forces that shaped the continent. The landscape above may be covered in snow, but the rocks beneath it have experienced temperatures and pressures far beyond anything humans encounter at the surface. The Antarctic continent is also part of the Earth's crustal system known as the Antarctic plate. Tectonic plates move slowly across the planet. Their movement is driven by processes occurring deep within Earth. The movement is incredibly slow compared with everyday life. A plate may move only a few centimeters each year, but over millions of years, those centimeters accumulate. Continents can travel thousands of kilometers. Oceans can open. Mountains can form. Land masses can separate. Antarctica's present position is the result of this enormous geological journey. It did not simply appear at the South Pole. It traveled there. The separation of Antarctica from Australia and South America played an important role in the development of its modern environment. As the continents separated, ocean passages opened. The Southern Ocean became increasingly connected around Antarctica. The Antarctic Circumpolar Current developed. This ocean circulation helped isolate the continent from warmer waters. Over geological time, Antarctica became progressively more isolated. The climate cooled. Ice sheets expanded. The continent transformed. A place that once contained forests gradually became dominated by ice. This transition did not happen overnight. It unfolded over millions of years. The continent slowly entered a new climatic era. The first permanent large-scale Antarctic ice sheets developed millions of years ago. Their growth was influenced by declining temperatures and changes in atmospheric composition. Once large ice sheets formed, they began influencing the climate themselves. Bright snow and ice reflected sunlight. The continent became even more reflective. The ice sheet grew. The surface remained cold. Snow accumulated, and a self-reinforcing system developed. The frozen continent became increasingly capable of maintaining its own cold environment. This relationship between ice and climate is one of the most interesting aspects of Antarctica. Ice reflects sunlight. That reflection reduces the amount of solar energy absorbed by the surface. The colder surface encourages continued ice persistence. This is an example of a positive feedback. It does not mean positive in the everyday sense of good. It means a process that reinforces itself. When a system changes in one direction, the feedback can amplify that change. In Antarctica, the presence of large areas of bright ice affects how the continent interacts with sunlight. The frozen landscape therefore influences its own environment. The opposite can happen when dark surfaces replace bright ice. Dark ocean water absorbs more solar energy. When sea ice retreats, more dark water becomes exposed. That water can absorb sunlight. The additional energy can influence local temperatures and ice formation. This is why scientists pay attention to changes in sea ice extent. Sea ice is not just a frozen surface. It is part of the climate system. It influences sunlight, atmosphere, ocean circulation, ecosystems, and heat exchange. Antarctica also contains one of the largest deserts on Earth by area. The entire interior is technically a polar desert, but the McMurdo Dry Valleys are among the most extreme desert environments. Some parts receive almost no precipitation. Snow can be removed by strong winds. Cold temperatures prevent significant liquid water from remaining on the surface. The result is a landscape of rock and ice. It can resemble a photograph from another planet. Brown mountains, gray gravel, white snowfields, blue ice, dark shadows. There are no trees, no flowing rivers, almost no visible signs of life. And yet microorganisms exist in hidden niches. Some Antarctic microorganisms live inside rocks. This may sound strange, but rocks can provide protection from the extreme environment. A tiny organism can occupy microscopic spaces within the mineral structure. The rock shields it from ultraviolet radiation. It can reduce exposure to wind. It can help retain small amounts of moisture. For a microorganism, a rock can become a shelter. Life does not always require a rich soil or a warm ocean. Sometimes a microscopic crack is enough. This discovery has expanded our understanding of where life can survive. Endolithic organisms are microorganisms that live within rock. They have been found in Antarctic environments where conditions at the surface are extremely harsh. Inside rock, conditions can be slightly more stable. Light may penetrate enough for certain organisms to photosynthesize. Moisture can remain trapped. Temperatures can fluctuate less dramatically. The rock becomes a tiny ecosystem. From the outside, the stone looks completely lifeless. Inside, microscopic organisms may be carrying out biological processes. This is one of the most beautiful reminders that appearances can be misleading. A landscape can look empty while containing life invisible to the naked eye. Antarctica's microorganisms also help scientists study the limits of photosynthesis. Photosynthesis normally requires light, water, carbon dioxide, and suitable temperatures. Antarctic environments can provide only small amounts of these resources. Yet some organisms have adapted to very low light levels. They can make use of brief periods of favorable conditions. They can slow down when conditions become unfavorable, and they can protect themselves from environmental stress. Their existence demonstrates how flexible biological systems can become. The Antarctic summer provides a brief window of opportunity. Sunlight becomes almost continuous. Temperatures rise slightly. Snow and ice melt in certain places. Liquid water becomes available. Microorganisms become active. Plants grow. Animals feed. The ecosystem takes advantage of every available moment. Then winter returns. Darkness grows. Temperatures fall. Water freezes. Many organisms reduce their activity. The annual cycle repeats. Life in Antarctica is therefore strongly seasonal. The summer sunlight can be particularly intense because the sun remains above the horizon for long periods. Even though the sun stays relatively low in the sky, the total duration of sunlight is extraordinary. Snow reflects much of the incoming radiation. This can create a bright environment that is uncomfortable without eye protection. Polar researchers often use specialized sunglasses or goggles. Snow blindness can occur when intense ultraviolet radiation reflects from snow and damages the eyes. The condition can be painful. This is another example of how a landscape that appears gentle can contain environmental hazards. The bright white surface is beautiful, but it also reflects sunlight efficiently. The whiteness of Antarctica comes largely from the interaction between snow, ice, and light. Snow contains countless tiny ice crystals. Each crystal can scatter incoming light. When many crystals are present together, the scattered light appears white. Ice can appear blue when it becomes dense and absorbs more of the red wavelengths. So the same substance can appear white or blue depending on its structure and the way light travels through it. Antarctica therefore contains a natural palette created by physics. White snow, blue glacier ice, dark ocean, black rock, golden sunlight, green aurora, red mineral stains. The continent may look monochromatic from a distance. Up close, it contains remarkable colors. Glacial blue is particularly beautiful because it often indicates dense ice. Fresh snow contains many air spaces. Those spaces scatter light in many directions. Dense glacier ice contains fewer bubbles. Light can travel farther into the ice. Certain wavelengths are absorbed more strongly. Blue wavelengths remain visible. The result can be intense blue ice. The deeper and denser the ice, the more striking the color can become. A wall of ancient glacier ice may therefore glow blue from within. Some Antarctic ice is exposed at the surface for extremely long periods. Blue ice areas can form where strong winds remove snow or where ice flows upward from deeper layers. These areas are particularly valuable for scientists. They can expose ancient ice without requiring deep drilling. In some blue ice regions, meteorites accumulate. This makes Antarctica one of the best places on Earth to search for meteorites. The reason meteorites are easier to find in Antarctica is surprisingly simple. Dark rocks stand out against white ice. If a meteorite lands in an ordinary environment, it may disappear among soil, vegetation, rocks, and human structures. On an Antarctic ice field, a dark meteorite can be remarkably visible. Over time, ice movement can concentrate meteorites in certain areas. Wind can remove snow. Glacial processes can expose old meteorites. Researchers can then collect them. This has made Antarctica a treasure house for planetary scientists. Thousands of meteorites have been recovered from Antarctic ice. Some originated from asteroids. Some are fragments of the moon. A small number came from Mars. The idea is extraordinary. A piece of another world can fall through Earth's atmosphere and become buried in Antarctic ice. Then, years or decades later, a scientist can walk across the frozen surface and pick it up. A meteorite may have traveled through space for millions of years. It may have survived impact, ejection, interplanetary travel, atmospheric entry, and landing. Then it becomes part of a frozen Antarctic collection. Martian meteorites are especially valuable. They are pieces of Mars that were blasted away from the Martian surface by enormous impacts. Some fragments eventually entered space. Over long periods, their trajectories intersected with Earth. They survived atmospheric entry and landed on our planet. Scientists can analyze them directly in laboratories. Antarctica has provided many important samples because its cold, dry conditions can preserve meteorites remarkably well. The continent therefore becomes a natural collection site for material from space. Some meteorites found in Antarctica are extremely old. They can contain minerals that formed early in the history of the solar system. By studying their chemical composition, scientists can learn about the conditions that existed when planets were forming. Meteorites can contain tiny grains older than the solar system itself. These pre-solar grains formed around ancient stars before the material became part of our sun and planets. A tiny grain inside an Antarctic meteorite may therefore be older than Earth, older than the sun, older than the planets. It is almost impossible to imagine the journey. A microscopic grain formed around an ancient star. It survived the destruction of that stellar environment. It became part of the cloud from which the solar system formed. It became embedded in a rock. That rock traveled through space. Eventually, it landed on Earth. And then, in the cold of Antarctica, it was preserved. Meteorite research also helps scientists understand the moon. Some Antarctic meteorites are lunar fragments. They were ejected from the moon by impacts. Eventually, some reached Earth. Because the moon lacks a thick atmosphere and active plate tectonics, its rocks preserve a long record of impacts. Lunar meteorites provide additional samples from different parts of the moon. Antarctica becomes a place where pieces of Earth's closest planetary neighbor can be found naturally. The same frozen landscape that preserves ancient terrestrial ice can preserve objects from outer space. That is one of Antarctica's most extraordinary combinations. The continent is simultaneously an archive of Earth and a collection point for material from beyond Earth. Its ice contains ancient atmospheric gases. Its rocks contain fossils. Its surface contains meteorites. Its skies reveal astronomical phenomena. Its dry valleys resemble planetary landscapes. And its research stations support experiments designed to understand the universe. Antarctica sits at the intersection of Earth science and space science. The search for meteorites requires patience. Researchers often travel across broad ice fields. They examine the surface for dark objects. The terrain may look almost identical in every direction. The work can be repetitive, but each unusual rock may contain something valuable. A meteorite may be only a few centimeters across, yet inside it could be evidence of planetary formation. Scientists carefully record its location. They protect it from contamination. Then it is transported to laboratories for analysis. The journey from Antarctic ice to a scientific laboratory can take a tiny piece of space material from complete isolation to detailed examination under microscopes and sophisticated instruments. Antarctica also receives cosmic particles constantly. High-energy particles from space enter Earth's atmosphere. Some reach the surface. Others interact with atmospheric molecules and produce secondary particles. The Antarctic environment can be useful for studying these phenomena because of its high elevation and low atmospheric moisture. Scientists have built detectors designed to observe particles that are difficult to detect elsewhere. Some experiments use enormous balloons. Others use detectors buried deep in ice. The continent becomes a giant natural laboratory for particle physics. One of the most famous Antarctic particle detectors is buried deep within the ice at the South Pole. The experiment is designed to detect neutrinos. Neutrinos are tiny particles that interact extremely weakly with matter. They can pass through enormous amounts of material without being stopped. Billions of neutrinos pass through your body every second. You do not feel them. They pass through Earth. They pass through buildings. They pass through ice. They pass through almost everything. Detecting them is therefore extraordinarily difficult. But Antarctica provides a huge amount of transparent, ancient ice that can be used as a detector. The Ice Cube Neutrino Observatory uses the Antarctic ice itself as part of its detection system. Thousands of light sensors are embedded deep within the ice. When a neutrino interacts with matter, it can produce a charged particle. That particle can create a faint flash of blue light known as Cherenkov radiation. The sensors detect the light. From the timing and pattern of those flashes, scientists can infer information about the original neutrino. The experiment turns a huge volume of Antarctic ice into a particle detector. This is one of the most extraordinary scientific uses of the continent. The ice is not merely something to study. It becomes the instrument. Neutrinos can originate from violent events in the universe. Supernova explosions can produce enormous numbers. Some come from the sun. Others may originate from active galaxies and other energetic cosmic sources. Because neutrinos interact so weakly, they can travel through regions that block ordinary light. They can carry information from deep inside astrophysical events. A particle produced far away in the universe can travel across space and eventually interact inside Antarctic ice. A detector buried beneath the South Pole can therefore provide information about events occurring millions or billions of light years away. The frozen continent becomes a window into the distant universe. This is one of the strangest contrasts in Antarctica. On the surface, everything seems slow. Ice moves slowly. Snow accumulates slowly. Mountains change slowly. But beneath the surface, scientists can detect particles traveling through the planet at enormous speeds. The continent becomes both ancient and modern. Ancient ice, ancient rocks, ancient fossils, and cutting-edge physics. The Antarctic sky is also valuable for studying cosmic microwave background radiation. The cosmic microwave background is faint radiation left over from the early universe. It fills space almost uniformly. By studying tiny variations in this radiation, scientists can learn about the early universe. Certain Antarctic locations provide favorable conditions for microwave astronomy. The air is extremely dry. There is little water vapor. Water vapor can interfere with observations at certain wavelengths. The high plateau is therefore valuable for astronomical experiments. The same dryness that makes Antarctica a desert also helps astronomers observe the universe. The South Pole can be one of the clearest places on Earth for certain types of astronomy. There are no large cities nearby. Artificial light is almost non-existent. The air is dry. The polar night provides long periods of darkness. Telescopes can operate continuously for extended periods. Instead of observing only a few hours each night, researchers can sometimes monitor astronomical targets for much longer stretches. This is especially useful for studying objects whose brightness changes over time. The sky becomes a laboratory. During the long polar night, the stars seem to dominate the landscape. There is no sunset every evening. The sun simply remains below the horizon. The darkness continues. The Milky Way can stretch across the sky. Stars appear more prominent because there are no city lights nearby. The horizon becomes difficult to distinguish. The ground and sky merge into darkness. A person standing there might feel as though they are floating beneath the universe. The earth remains beneath their feet. But visually, the boundaries disappear. Auroras can interrupt that darkness. The southern lights can form ribbons and curtains. Their brightness changes. Sometimes they are faint. Sometimes they become intense. The colors are produced by different atmospheric gases and the energies involved. Oxygen can produce green and red emissions. Nitrogen contributes to other colors. The altitude of the interaction also matters. The aurora is therefore not one single color-producing mechanism. It is a complex interaction between solar particles, Earth's magnetic field, and atmospheric chemistry. The Earth's magnetic field guides charged particles toward the polar regions. The field itself is generated deep within Earth. Moving molten metal in the outer core creates electric currents. Those currents produce the global magnetic field. The magnetic field extends far into space. It forms a protective region called the magnetosphere. When solar particles interact with the magnetosphere, some energy is transferred into the upper atmosphere. Auroras result. This means a glowing curtain of light over Antarctica is ultimately connected to molten metal moving thousands of kilometers beneath Earth's surface. The deep Earth, the atmosphere, the sun, and the polar sky are all connected. Solar activity changes over time. The sun goes through an approximately 11-year cycle of activity. During more active periods, solar flares and coronal mass ejections can become more frequent. These events can send large amounts of charged particles toward Earth. When they interact with the magnetosphere, auroras can become more widespread and intense. Antarctica is one of the best places to observe the southern lights. The polar night provides darkness. The location provides favorable magnetic geometry, and the absence of light pollution makes the aurora easier to see. The sun itself is also an important part of Antarctica's climate story. During summer, the continent receives prolonged sunlight, but the sun remains relatively low in the sky. Its energy is spread across a larger surface area compared with sunlight arriving more directly. Snow and ice reflect much of the radiation. The result is a complex balance. Antarctica receives sunlight during summer, but remains cold over much of the continent. The angle of the sun matters. The surface properties matter. The atmosphere matters. The duration of daylight matters. Climate is not determined by sunlight alone. It is determined by how energy enters, moves through, and leaves the system. The polar atmosphere can also create unusual halos around the sun. Ice crystals suspended in the air can refract sunlight. A bright ring may appear around the sun. There may be arcs above or below it. Bright spots can appear to either side. These phenomena can look almost supernatural, but they are simple consequences of light interacting with ice crystals. Antarctica provides many opportunities to observe them because ice crystals are abundant in the cold atmosphere. The sky becomes another frozen surface. Sometimes the sun can appear distorted near the horizon. Temperature differences in the atmosphere can bend light. This can produce mirages. Distant objects may appear stretched, inverted, or displaced. In a landscape with few visual landmarks, these effects can be especially striking. A mountain can appear taller. A distant object can seem to float. The horizon can become distorted. The cold atmosphere creates conditions for unusual optical effects. Antarctica can therefore make ordinary physics look extraordinary. The phenomenon known as the Fata Morgana can occur in polar regions. It is a complex form of mirage created by layers of air at different temperatures. Light bends as it passes through these layers. Distant objects can appear above their true position. They may seem elongated. Multiple images can appear. A ship may look as though it is floating above the horizon. An iceberg can appear dramatically taller than it really is. The landscape becomes an optical illusion. In Antarctica, where visibility can extend for enormous distances, these effects can create especially surreal scenes. Even the horizon itself can behave strangely. Snow and ice can reflect light upward. Atmospheric layers can bend light. Distant features can appear closer or farther away. The absence of familiar objects makes judging scale difficult. A small iceberg can look enormous. A mountain many kilometers away can appear almost within reach. The Antarctic landscape challenges human perception. Our brains evolved to judge distances using familiar visual cues. Trees, buildings, roads, people, animals. In Antarctica, many of those cues disappear. The brain has less information to work with. Distance becomes uncertain. This is one reason Antarctic explorers historically faced such difficulty. Before modern satellite navigation, mapping a continent this large was incredibly challenging. Explorers relied on compasses, sextants, astronomical observations, dead reckoning, and careful surveying. The weather could erase landmarks. Snow could cover tracks. Blizzards could prevent visibility. The cold could damage equipment. Supplies were limited, and rescue could be extremely difficult. Yet explorers crossed vast portions of the continent. Their journeys expanded humanity's knowledge of Earth's geography. One of the most famous explorers associated with Antarctica was Roald Amundsen. He led the first successful expedition to reach the geographic South Pole in 1911. His expedition carefully planned for the environment. Experience in polar travel, efficient equipment, Appropriate clothing, sled dogs, and careful logistics contributed to the success. The journey was not simply a race. It was an enormous logistical challenge. Food had to be transported. Shelter had to be established. Routes had to be chosen. Weather had to be managed. Every kilogram mattered. In an environment where supplies cannot easily be replaced, preparation becomes essential. Robert Falcon Scott's expedition also reached the South Pole, arriving shortly after Amundsen. The return journey became tragic. Scott and his companions died during the expedition. Their story remains one of the most famous and heartbreaking episodes in polar exploration. The Antarctic environment can be beautiful, but it is also dangerous. The cold does not care about ambition. Distance does not care about determination. A small failure in planning can become catastrophic. Modern Antarctic research benefits enormously from technologies and logistical systems that earlier explorers did not have. Aircraft, satellites, GPS, modern clothing, advanced weather forecasting, emergency communications, specialized vehicles. Yet the environment itself remains powerful. The history of Antarctic exploration is therefore a story of human endurance. People entered an environment almost completely unfamiliar to them. They faced extreme cold. They traveled across glaciers. They mapped coastlines. They collected rocks and fossils. They studied animals. They measured weather. They crossed enormous distances. And they gradually transformed Antarctica from a blank space on maps into a continent understood through science. But much remains unknown. The deeper ice, the hidden lakes, the subglacial ecosystems, the buried mountains, the deep ocean, the future behavior of ice shelves, all continue to be studied. Antarctica is also governed differently from ordinary continents. The Antarctic Treaty System establishes a framework for peaceful scientific cooperation. The original Antarctic Treaty was signed in 1959 and entered into force in 1961. It set aside Antarctica for peaceful purposes and scientific cooperation. Military activities are restricted. Scientific research is encouraged. The continent is not owned as a normal sovereign territory in the way most land is. The treaty system has become one of the most important examples of international cooperation. Countries with very different political interests can operate research stations on the same continent. Scientists share information. Research teams collaborate. Environmental rules govern many activities. The Antarctic environment becomes a place where cooperation is more important than competition. The Antarctic Treaty also prohibits nuclear explosions and the disposal of radioactive waste in Antarctica. The goal is to protect the continent as a place for peaceful scientific research. This makes Antarctica unusual. Most continents contain cities, borders, military bases, highways, industries, farms, and large permanent populations. Antarctica has none of these on the same scale. Its human presence is primarily scientific and logistical. The continent remains one of the few places where large areas are almost completely free of permanent human development. There is no native permanent human population in Antarctica. People live there temporarily for scientific, logistical, or support purposes. The number of people changes dramatically with the seasons. Summer brings more researchers and support workers. Winter brings fewer people. The population may fall to only a few thousand across the entire continent during winter. Compared with the enormous area of Antarctica, that is an extraordinarily small number. Imagine a continent larger than Europe with only a few thousand people scattered among research stations. The sense of isolation is enormous. Antarctica is also larger than most people imagine. It is larger than Europe. It is larger than Australia. Its area changes slightly depending on how ice shelves and seasonal sea ice are measured, but the continent itself covers roughly 14 million square kilometers. The scale is difficult to visualize. You could place enormous numbers of cities inside its area. Yet almost the entire continent is covered by ice. Its interior contains some of the least accessible terrain on Earth. The distances between research stations can be enormous. Aircraft and specialized vehicles are essential. The Antarctic coastline is also much longer than it might appear on a simple map. Ice shelves can extend outward. Glaciers reach the ocean. Peninsulas stretch into surrounding seas. Islands surround parts of the continent. The coastline changes seasonally as sea ice forms and melts. A map of Antarctica is therefore not completely static. Its visible boundaries shift. Ice advances. Ice retreats. Icebergs break away. Sea ice forms. The continent interacts dynamically with the surrounding ocean. Some Antarctic islands are volcanic. The South Shetland Islands, for example, contain volcanic features. Deception Island is particularly famous because it is an active volcanic island shaped like a flooded caldera. The island's horseshoe shape creates a sheltered harbor. Inside, volcanic geology meets Antarctic climate. Black volcanic rock contrasts with white snow. Warm geothermal areas can exist amid freezing conditions. The island is a reminder that Antarctica contains fire as well as ice. Deception Island has experienced volcanic eruptions in modern history. Scientists monitor volcanic activity there. The combination of volcanoes, glaciers, ocean, and wildlife creates an unusual environment. In some places, geothermal heat can warm the ground. Snow may melt around heated areas. Steam can rise. The contrast is dramatic. A person can stand in a landscape dominated by freezing air and snow while geological heat emerges from beneath the ground. Antarctica's apparent contradictions continue. The continent also contains geothermal heat beneath glaciers. Volcanic regions are one source. But even outside volcanic areas, Earth constantly releases internal heat. The planet's interior remains hot because of its formation, radioactive decay, and other processes. That heat moves slowly toward the surface. Under thick ice, it can contribute to basal melting. This is one reason liquid water can exist beneath the ice even when the surface temperature is far below freezing. Antarctica is frozen from above, but it is warmed from below. Between those two influences lies the complex behavior of the ice sheet. The ice itself can insulate the bedrock. A thick layer of ice reduces the rate at which heat escapes. This helps maintain warmer conditions beneath the ice compared with the surface. The result can be an environment where liquid water survives beneath a frozen exterior. It is a little like placing a blanket over something warm. The surface may be extremely cold, but heat beneath the blanket remains trapped more effectively. Antarctica's ice acts as an enormous insulating layer. This hidden warmth has important consequences for glaciers. Where basal water exists, glaciers may slide more easily. Where the bed is frozen solid, movement can be slower. The difference can influence the speed at which ice flows toward the coast. Scientists therefore study basal conditions carefully. A glacier's surface speed can provide clues, but understanding why it moves requires knowledge of what happens underneath. The hidden world determines the visible movement. And so, once again, Antarctica reminds us not to trust appearances. A smooth white surface can conceal a mountain range. A frozen lake can hide liquid water beneath it. A quiet glacier can be flowing. A lifeless rock can contain microorganisms. A tiny meteorite can contain material older than Earth. A dark Antarctic sky can contain particles arriving from distant galaxies. A frozen continent can influence oceans around the planet. Everything is more complicated beneath the surface. Now imagine the Antarctic sky becoming darker. The final light disappears. The mountains become shadows. A thin ribbon of aurora begins to glow. The snow beneath you reflects a faint green light. There is no sound of traffic, no voices, only wind. Far away, a penguin colony settles for the night. A seal rests beside a breathing hole. A whale moves beneath dark water. Deep beneath the ice, a neutrino passes through without stopping. Older than any human civilization, the ice remains. And somewhere inside it, a tiny bubble of ancient atmosphere waits patiently. It has been waiting for hundreds of thousands of years. It does not know that one day humans will drill into the ice and study it. It simply remains there, preserved, quiet, still. The idea of ancient air trapped inside ice is perhaps one of the most peaceful images Antarctica offers. Imagine a snowflake falling long ago. It lands on the Antarctic surface. More snow falls. The snow is buried. The pressure increases. The air between the grains becomes trapped. Eventually, the snow becomes ice. The bubble becomes sealed. Then the years pass. Hundreds, thousands, tens of thousands, hundreds of thousands. The bubble remains. The world above changes. Animals evolve. Civilizations rise. Languages appear. Cities grow. People cross oceans. Technology transforms the planet. And the tiny bubble remains inside the ice, waiting. When scientists eventually release that ancient air, they can measure its composition. They can determine the concentration of carbon dioxide. They can measure methane. They can examine other gases. These measurements reveal how Earth's atmosphere changed over time. The ice becomes a timeline. Each layer adds another piece. Scientists can compare atmospheric gases with temperature indicators. They can identify cycles. They can see relationships between greenhouse gases and climate. Antarctica, therefore, gives humanity something incredibly rare. A record of the atmosphere before modern instruments existed. The deepest ice contains the oldest chapters. The surface represents recent years. Go deeper and the layers become older. The process is not perfectly uniform. Ice can deform. Layers can become compressed. Flow can distort them. But in many regions, the sequence remains remarkably useful. Scientists can reconstruct ancient climate conditions. They can identify periods of warming and cooling. They can study volcanic eruptions. They can examine atmospheric dust. They can observe changes in greenhouse gases. The ice is one of the most important climate archives on Earth. And perhaps that is where we can leave this part of our journey. Not at the edge of Antarctica, but deep inside its memory. Imagine yourself surrounded by blue ice. The walls are quiet. The air is still. The surface world feels impossibly far away. Every layer around you represents time. Every bubble carries a fragment of atmosphere. Every grain of dust has a history. Every crystal was once part of snowfall. And somewhere above, under a distant polar sky, the present continues. The wind moves. The aurora glows. The stars remain. The ocean circulates. The penguins rest. The seals breathe. The whales travel. The glaciers flow. And Antarctica continues to preserve its ancient story. You can let yourself become quiet now. There is nowhere else you need to be. Let the frozen blue darkness surround your imagination. Let the slow movement of the glaciers become a kind of rhythm. Let the ancient ice remind you that some stories do not need to be rushed. Some stories take thousands of years to unfold, and Antarctica is still telling its story, slowly, silently, one layer at a time. The ancient air trapped inside the ice has brought us deeper into Antarctica's memory. But the deeper we travel, the more we discover that the ice is not simply a frozen archive. It is also a moving world. The layers we have been following are slowly compressed, stretched, folded, and carried toward the coast. Somewhere beneath them, water moves through hidden channels. Above them, wind reshapes the surface. And beyond the edge of the continent, the Southern Ocean waits. So let us continue exactly where our journey left off, without returning to the beginning. The ancient bubbles remain sealed around us. The blue walls of ice surround us. And now, slowly, we will follow that ice toward the hidden landscapes beneath it. The deeper layers of an ice sheet do not remain perfectly flat forever. As more snow accumulates above them, their weight increases. The pressure compresses the older ice. Tiny spaces between snow crystals gradually disappear. The individual grains become joined together. Snow becomes firn. Firn becomes dense glacial ice. And eventually, the ancient layers become so compressed that they behave very differently from the fresh snow lying on the surface. The deeper ice can slowly deform. It bends. It stretches. It flows. The old atmosphere trapped inside it travels with the ice. So even the ancient bubbles we imagined earlier are not completely motionless. They are slowly carried through the frozen interior. Imagine following one of those bubbles. It begins near the surface. Fresh snow surrounds it. More snow arrives. The bubble becomes buried. Years pass. The pressure increases. The snow becomes denser. The bubble becomes smaller. Eventually, the surrounding material becomes solid ice. Then the ice begins its incredibly slow journey toward the coast. The bubble moves with it. Perhaps it travels only a few meters during an entire year. Perhaps it travels much farther in a faster-flowing region. But over thousands of years, the distance becomes enormous. The ancient atmosphere is slowly carried through the continent. The movement of Antarctic ice is influenced by gravity. The ice sheet is elevated above the surrounding ocean. Gravity constantly pulls it toward lower elevations. The ice does not need to melt in order to move. Solid ice can deform under enormous pressure. At depth, the individual ice crystals slowly change shape. They slide and rotate. The structure of the ice adjusts. The entire mass behaves almost like an extremely slow river. From the surface, it looks frozen and permanent. Deep below, it is flowing. The speed of this movement is different from one region to another. Some parts of the interior move extremely slowly. Other areas move much faster. Ice streams can carry ice toward the coast at speeds measured in hundreds of meters per year. Certain glaciers can move even faster during periods of acceleration. The difference may seem small when viewed from a distance, but over decades, it becomes enormous. A glacier that moves several hundred meters each year can travel several kilometers during a human lifetime. Scientists can measure this movement using satellites. A satellite can photograph the same region repeatedly. By comparing images, researchers can identify subtle changes. Surface features move. Crevasses shift. Snow patterns change position. GPS instruments can measure movement directly. Radar can also track ice motion through clouds and darkness. Modern technology allows scientists to watch Antarctica move from space. The continent that once seemed impossibly inaccessible can now be monitored continuously. Radar is especially valuable because much of Antarctica is hidden beneath ice. Radar waves can travel through ice. They can reflect from boundaries beneath the surface. Scientists can use these signals to map the bedrock. They can identify buried mountains, deep valleys, basins, subglacial lakes, and channels. The radar does not simply tell scientists how thick the ice is. It can reveal an entire hidden continent underneath it. When the first detailed maps of Antarctica's subglacial landscape began to emerge, scientists discovered something remarkable. The bedrock beneath the ice is not flat. There are enormous mountains hidden beneath kilometers of ice. There are deep valleys. There are broad basins. There are ancient landscapes that have not seen sunlight for millions of years. The ice has covered an entire world. Some buried mountains are comparable in scale to mountains visible above the ice. They form ranges beneath the surface. One of the most famous hidden mountain systems is the Adverts subglacial mountains. They are located deep within East Antarctica. The mountains were discovered through geophysical surveys. They are remarkable because they lie beneath a huge thickness of ice. From the surface, there may be no obvious sign that a mountain range exists below. You could stand on a flat frozen plain while an enormous mountain rises beneath your feet. The Adverts mountains are especially interesting because they appear to be extremely ancient. Their exact history is complex. Scientists believe the range may have formed through ancient tectonic processes and later experienced substantial erosion and geological change. The mountains are now buried beneath ice, yet their shape remains detectable through radar and gravity measurements. A landscape that has been hidden for millions of years can still be reconstructed. The ice above these mountains can be several kilometers thick. Imagine standing on a perfectly smooth snowfield. You look around. Nothing appears unusual. The horizon is flat. There are no cliffs, no visible peaks, no valleys. But beneath your feet lies a rugged mountain landscape. The ice has erased the visible topography. The surface is almost like a blanket laid over an entire mountain range. The ice also fills ancient valleys. Some of these valleys may once have carried rivers. Others may have been carved by glaciers. Some may contain water today. The hidden topography influences how modern ice flows. A valley can guide ice. A ridge can slow it. A basin can collect water. The ancient landscape beneath the ice still controls the modern landscape above it. This is one reason scientists care so much about bedrock mapping. To understand how Antarctica's ice behaves, they need to know what is underneath. A glacier flowing over smooth bedrock behaves differently from one moving through a deep valley. Water at the base can change friction. Rock type can influence movement. Subglacial sediments can provide lubrication. The hidden landscape becomes part of the equation. And beneath some of these valleys are lakes. Thousands of meters of ice can separate the surface from liquid water. These are subglacial lakes. They are one of the strangest environments on Earth. A lake can exist beneath an ice sheet, while the surface temperature above remains far below freezing. The reason is a combination of pressure, geothermal heat, and insulation from the overlying ice. The enormous pressure of the ice lowers the melting point slightly. Heat from Earth's interior rises from below. The thick ice slows the escape of that heat. Together, these factors can allow water to remain liquid. One of the most famous subglacial lakes is Lake Vostok. It lies beneath several kilometers of Antarctic ice. The lake is enormous. It has been sealed from the surface for an extraordinarily long time. Scientists have detected evidence of liquid water using radar and other geophysical techniques. The lake is part of a much larger network of water beneath the ice. It is not simply an isolated pocket. It can be connected to other subglacial environments through channels and changing water pressures. The water beneath Antarctica can move. This is perhaps one of the strangest discoveries. A continent covered by kilometers of ice can contain a hidden hydrological system. Water flows beneath glaciers. Lakes fill. Lakes drain. Channels connect. Pressure changes. The system can reorganize. The surface may remain completely frozen, but beneath it, water is moving. Some subglacial lakes can fill and drain. Scientists have observed changes in surface elevation above them. When water moves into or out of a lake, the ice above can rise or sink slightly. Satellites can detect these subtle changes. A lake may fill over years, then drain, then refill. The process can influence ice movement. The entire event may happen without any visible sign at the surface. Subglacial water can also act as a lubricant. Imagine trying to slide a heavy object across a dry surface. There is friction. Now imagine placing a thin layer of water underneath. The object may move more easily. Something similar can happen beneath glaciers. Water can reduce friction between ice and bedrock. This can allow ice to flow faster. The effect depends on pressure, water volume, bedrock structure, and many other factors. But the principle is important. A small amount of hidden water can influence the movement of an enormous mass of ice. The water beneath Antarctica is not necessarily pure. It can contain dissolved minerals. It can interact with rocks. It can carry sediment. It can contain microorganisms. The water may have been isolated from the surface for long periods, although the degree of isolation varies between different systems. Scientists are extremely interested in the possibility of life in these environments. Microbial life does not require sunlight in every ecosystem. On the surface, plants and algae often capture energy from sunlight. But deep underground and beneath ice, microorganisms can use chemical reactions. They can obtain energy from minerals. They can use compounds containing iron, sulfur, hydrogen, or other elements. These processes are called chemosynthesis or chemolithotrophy in various contexts. The exact biology varies, but the broader lesson is important. Life can exist without direct sunlight. This has implications far beyond Antarctica. Europa, one of Jupiter's moons, is believed to contain a global ocean beneath an icy shell. Enceladus, a moon of Saturn, also has evidence of a subsurface ocean. Scientists wonder whether environments beneath extraterrestrial ice could potentially support microbial life. Antarctica provides a natural laboratory for studying some of the physical and biological conditions that might exist in such places. The frozen continent becomes a model for worlds beyond Earth. Antarctica's subglacial lakes are not all the same. Some are enormous. Others are small. Some may remain isolated for long periods. Others may connect through drainage systems. The network changes as ice pressure changes. Water can move through channels. A lake may suddenly lose water. Another may receive it. The system behaves somewhat like a hidden plumbing network, except the pipes are beneath kilometers of ice. Imagine a vast frozen landscape at night. The surface is completely silent. There is no visible river, no lake, no rainfall. Yet beneath your feet, water is slowly flowing through a dark, hidden channel. It moves under enormous pressure. It carries minerals. It touches ancient rock. It may encounter microorganisms. It eventually reaches another basin. Above it, the ice remains frozen. The surface gives no clue. Some subglacial channels may be carved or maintained by flowing water. The relationship between ice and water can become complex. Water can melt ice. Ice can redirect water. Pressure can close channels. Heat can reopen them. The system can change over time. Scientists are still working to understand the full network. Antarctica, therefore, has something resembling a hidden river system. It is not a conventional river system like those found on the surface. There are no sunny riverbanks, no trees, no visible current. Instead, water moves through darkness beneath the ice. The river may be completely sealed from the atmosphere. Its ceiling is ice. Its floor is rock or sediment. Its surroundings are under immense pressure. It is a river hidden inside a continent. The bed beneath Antarctic ice can also contain sediment. Sediment is material produced through erosion. Glaciers grind against rock. They scrape. They crush. They transport fragments. The resulting material can accumulate beneath the ice. This sediment can be extremely fine. Glacial flour is a term often used for very fine rock particles produced by glacial grinding. When water eventually carries such sediment toward the ocean, it can affect the color of the water. The material can remain suspended for long periods. Glacial erosion is incredibly powerful. A glacier may move slowly, but it carries enormous weight. Rocks trapped beneath the ice act like grinding tools. They scrape against bedrock. They polish surfaces. They carve grooves. They deepen valleys. They reshape mountains. Over millions of years, glaciers can dramatically alter landscapes. Slow movement does not mean weak movement. Some Antarctic mountains have been shaped by repeated glaciation. Ice moves through valleys. It widens them. It deepens them. It can create U-shaped valleys. It can remove rock from steep slopes. The mountains that remain are therefore partly sculptures created by ice. The sculptor moves extremely slowly, but it never stops. Glacial erosion can also create hanging valleys. A smaller glacier once joins a larger one. The smaller glacier may carve a shallower valley. The larger glacier cuts deeper. After the ice retreats, the smaller valley can remain elevated above the main valley. In other regions of the world, waterfalls may form there. Antarctica's frozen environment can preserve similar geological structures beneath the ice. The ice also protects some landscapes from erosion. A thick ice sheet can act as a blanket. If the bed is frozen, erosion may be relatively limited. This helps preserve ancient surfaces. Some areas beneath East Antarctica may have remained remarkably stable for very long periods. The ice does not always destroy the landscape. Sometimes it protects it. There may be ancient valleys beneath Antarctica that have not experienced surface weathering for millions of years. No rain falls on them. No rivers flow openly across them. No plants grow there. No wind directly scours the rock. The ice above seals the environment. The result is a kind of geological time capsule. The contrast between East and West Antarctica is important. East Antarctica is generally higher and contains an enormous, relatively stable ice sheet. West Antarctica is lower and contains several major ice basins whose beds lie below sea level. This difference influences their behavior. The West Antarctic ice sheet is especially sensitive to changes at its margins and beneath floating ice shelves. The geometry of the bedrock and ocean makes some regions particularly important for understanding future ice loss. Much of West Antarctica sits on bedrock that lies below sea level. This is called a marine-based ice sheet. Its ice rests on a bed that is below the ocean surface. The geometry creates special vulnerabilities. If relatively warm seawater reaches the underside of floating ice and causes thinning, the grounding line can migrate inland. The grounding line is where ice transitions from resting on bedrock to floating. Its position matters enormously. A grounding line is not always visible from the surface. It can lie beneath hundreds of meters of ice. Scientists use radar, satellite measurements, ocean observations, and other techniques to map it. As the grounding line moves, the amount of floating and grounded ice can change. This can influence ice flow. The hidden boundary becomes one of the most important lines in Antarctic science. One of the most studied regions is the Amundsen Sea sector of West Antarctica. Several major glaciers drain ice toward the ocean there. Among them is Thwaites Glacier. Thwaites is enormous. It covers an area comparable to a large country or region. Scientists pay close attention to it because its grounding zone interacts with ocean water and because its position is important to the stability of the surrounding ice sheet. Thwaites Glacier has sometimes been called the Doomsday Glacier in popular media. The nickname is dramatic. The actual scientific story is more complicated. Thwaites is not expected to suddenly collapse and raise sea levels overnight. Changes in the glacier occur over much longer timescales. Scientists are concerned because continued retreat could contribute substantially to long-term sea level rise and could influence neighboring ice. The glacier is therefore important, but it is not a switch waiting to flip. Warm ocean water can reach the underside of Antarctic ice shelves. This is one of the major mechanisms scientists investigate. The word warm is relative. Water may still be close to freezing by ordinary human standards. But compared with the temperature at which the surrounding ice melts, a small difference can matter. A fraction of a degree can have consequences when applied over enormous areas for long periods. Ocean heat can therefore attack ice from below. The surface may remain cold. Snow may continue falling. The sky may be clear. But beneath the ice, ocean water can slowly remove ice. This creates a strange imbalance. From above, Antarctica may look frozen and stable. From below, the ocean can be quietly changing it. The Southern Ocean is not uniformly cold. Different water masses exist at different depths. Some deep water is warmer than the water at the surface. Currents can carry it toward continental shelves. Under certain conditions, that water can reach the underside of ice shelves. The exact pathways depend on seafloor shape, winds, tides, and ocean circulation. The underwater landscape matters just as much as the surface landscape. Scientists deploy instruments beneath ice shelves to measure these conditions. Robotic vehicles can travel through the ocean beneath floating ice. They can carry cameras, temperature sensors, salinity sensors, current meters, sonar. The resulting images reveal an environment humans almost never see directly. The underside of an ice shelf can contain ridges, channels, sediment, and unusual biological communities. It is an underwater world hidden beneath another world. Some organisms live beneath ice shelves. The discovery of unexpected communities beneath thick Antarctic ice has surprised researchers. In places far from open sunlight, animals can survive using food transported by currents or produced elsewhere. Sponges and other organisms may attach themselves to rock. Their existence demonstrates that ecosystems can persist in extremely isolated environments. Life can survive in places that seem almost completely disconnected from the surface. The absence of sunlight does not necessarily mean the absence of food. Ocean currents transport organic material. Particles can sink from surface waters. Marine snow drifts downward. Tiny organisms feed on it. Larger organisms feed on them. A food web can develop. It may be sparse. It may be slow, but it can exist. Marine snow is one of the quiet processes of the ocean. It is made of tiny particles, dead organisms, waste, mucus, mineral particles, fragments of organic material. They sink slowly through the water column. The particles can resemble snowflakes drifting through the deep ocean. Hence the name. Marine snow connects the surface ocean to the deep sea. Imagine descending through the Antarctic Ocean. At the surface, sunlight still exists. Below you, the water becomes darker. Then darker still. Tiny particles drift past. Some look like snow. There is no wind, no sound that you can hear, only the slow movement of water. Eventually, the sunlight disappears completely. The particles continue falling. Some may take days. Some may take weeks. Some may travel much longer before reaching the seafloor. The deep ocean beneath Antarctica is cold and dark. Pressure increases with depth. Every 10 meters of seawater adds roughly 1 atmosphere of pressure. At several thousand meters depth, the pressure becomes enormous. Yet deep-sea organisms survive there continuously. Their bodies are adapted to the pressure. Their membranes function differently. Their enzymes work at low temperatures. Their metabolism is suited to limited food. Life has adapted to conditions that would be lethal to humans without protection. Antarctic deep-sea organisms can be surprisingly slow-moving. Cold temperatures reduce metabolic rates. Food may be scarce. There is little reason to waste energy. Many organisms conserve energy carefully. Some wait for food to arrive. Others move slowly across the seafloor. The deep Antarctic Ocean is not empty. It is simply quiet. Sea spiders crawl across the bottom. Sea stars move slowly. Worms burrow through sediment. Crustaceans search for food. Sponges filter water. Fish move through the darkness. Jellyfish drift above. And microorganisms recycle the material that reaches the bottom. Every organism plays a small role. Together, they form an ecosystem. Antarctica's seafloor also contains unusual geological features. There are submarine volcanoes, hydrothermal systems, deep trenches, ridges, sediment plains. The continent continues beneath the ocean. The visible land is only part of the Antarctic geological system. Much of the surrounding seafloor is equally important. Hydrothermal vents can support ecosystems without sunlight. Hot water emerges from beneath the seafloor. It carries dissolved minerals. Microorganisms use chemical energy from these compounds. Other organisms feed on the microorganisms. This creates food webs independent of sunlight. Although hydrothermal ecosystems are not unique to Antarctica, they illustrate another way life can flourish in darkness. The ocean around Antarctica also contains underwater mountains. Seamounts rise from the deep ocean floor. They can influence currents. Water moving around them becomes turbulent. Nutrients can be brought upward. Marine life may concentrate around them. A seemingly empty part of the ocean can therefore become a biological hotspot because of a mountain hidden beneath the surface. The Antarctic coastline is constantly shaped by tides. Ocean water rises and falls. The movement of tides flexes floating ice. Ice shelves can move slightly up and down. Cracks may open and close. Tidal forces can propagate beneath ice. The moon is therefore influencing Antarctic ice from hundreds of thousands of kilometers away. The moon's gravity raises tides in Earth's oceans. Those tides travel around the Antarctic coastline. In some places, tidal motion can influence how seawater moves beneath ice shelves. The relationship between tides and ice can be subtle, but scientists can detect it. Ice may rise and fall. Water pressure changes. Floating platforms flex. The frozen continent is connected to the moon through gravity. Even the Earth's rotation matters. The planet spins continuously. This creates the Coriolis effect. Large-scale ocean currents and atmospheric systems are influenced by it. The Southern Ocean circulation is therefore shaped by Earth's rotation as well as wind, temperature, salinity, and geography. A current moving around Antarctica is part of a planetary scale system. And this brings us back to the enormous Antarctic circumpolar current. Water can travel around Antarctica without encountering a continent that blocks its path. The current connects the world's major ocean basins. It transports heat. It moves nutrients. It carries organisms. It influences atmospheric interactions. It helps isolate Antarctica. In a sense, the continent sits inside a giant moving ring of water. That ring of water also separates Antarctica from warmer regions. Before the modern Southern Ocean circulation developed, warmer waters could reach the continent more easily. As ocean gateways opened and circulation strengthened, Antarctica became increasingly isolated. The cold environment intensified. Ice expanded. The modern Antarctic climate gradually emerged. The ocean helped create the frozen continent we know today. Yet the continent still interacts with the ocean constantly. Glaciers deliver fresh water. Icebergs carry sediment. Sea ice removes and returns salt. Phytoplankton absorb carbon dioxide. Whales move nutrients. Winds transfer energy. Currents transport heat. The boundary between land and sea is not a wall. It is a constantly changing exchange zone. Now imagine the same glacier we followed earlier reaching the coast. The ancient ice has spent thousands of years moving. The surface has changed. The layers have compressed. The trapped air has traveled. The glacier reaches the ocean. Part of it remains grounded. Part of it begins to float. The ice shelf stretches outward. The glacier has become part of the sea. The moment a glacier begins floating is not a dramatic event. There may be no visible boundary. The ice simply becomes buoyant. The ocean begins supporting its weight. The glacier continues flowing. Tides lift it. Waves influence the front. Currents move beneath it. The ice shelf becomes an enormous floating extension of the continent. Eventually, the front of the ice shelf advances. It grows. Cracks develop. A fracture may begin far inland. It slowly extends, perhaps for years, perhaps for decades. Eventually, the crack reaches the edge. A huge piece separates. An iceberg is born. The event may be called calving. From the continent's perspective, it is simply another stage in the journey of ice. Snow became firn. Firn became ice. Ice flowed. Ice floated. Then ice became an iceberg. The iceberg drifts away. Perhaps it carries ancient bubbles. Perhaps it contains dust from a distant desert. Perhaps sediment is trapped inside. Perhaps its blue interior has not seen sunlight for thousands of years. It becomes part of the Southern Ocean. A piece of the continent is now traveling freely. The iceberg may encounter penguins. A seal may rest upon it. A seabird may land on its surface. Krill may gather around its underwater edges. As the iceberg melts, fresh water enters the ocean. Nutrients are released. Sediment sinks. The iceberg becomes part of the ecosystem. Eventually, the last fragment disappears, and the water that once formed the iceberg joins the ocean. It may evaporate. Clouds may carry some of it elsewhere. Eventually, precipitation may return it to Antarctica. Snow falls. The cycle begins again. Water leaves the continent. Water enters the ocean. Water evaporates. Clouds move. Snow returns. Ice accumulates. The Antarctic water cycle continues. Some of that moisture can travel thousands of kilometers before falling as snow. Storm systems bring moisture toward Antarctica. Air rises, cools, water vapor condenses, snow forms. The flakes descend. They land on the ice sheet. Another layer begins. The journey from ocean to cloud to snow to glacier continues. Antarctica is therefore not isolated from the global water cycle. The continent may be extremely dry, but it still participates in atmospheric circulation. Moisture comes from the surrounding ocean. Winds transport it. Storms carry it. Snow falls. Ice stores the water. Eventually, some of that ice returns to the ocean. The cycle may take centuries. The Antarctic ice sheet is therefore a gigantic water reservoir. It stores water in frozen form. The reservoir is constantly gaining and losing mass. Snowfall adds ice. Surface melting can remove ice in some regions. Sublimation removes water vapor. Glaciers transport ice toward the ocean. Ice shelves calve. Basal melting can remove ice from below. The balance between these processes determines whether a region gains or loses ice over time. Scientists call this the ice sheet's mass balance. If more mass is added than lost, the ice sheet gains mass. If more is lost than added, it loses mass. The balance can vary from year to year. Weather affects snowfall. Ocean conditions affect melting. Winds affect snow transport. Ice flow affects discharge. The system is complex. A single year's snowfall does not tell the whole story. Scientists therefore monitor the continent over many years. Satellites are crucial for this work. Some satellites measure changes in ice elevation. Others measure gravity. Some track surface movement. Others observe temperature and surface conditions. Radar satellites can operate through darkness and clouds. Together, these technologies allow researchers to watch Antarctica from orbit. The continent that once required months of dangerous travel to study can now be observed repeatedly from space. Gravity measurements are especially fascinating. Mass changes Earth's gravitational field. If a region gains or loses enormous amounts of ice, the local gravity field changes slightly. Satellites can detect these changes. By analyzing them, scientists can estimate changes in ice mass. The measurements are incredibly subtle, but the signal is there. The movement of an entire ice sheet can be detected by measuring gravity from orbit. The ice sheet can also influence Earth's rotation and gravitational field. A massive redistribution of water changes the planet slightly. When ice melts and water enters the ocean, mass is redistributed. The effect on Earth's rotation is tiny but measurable with sensitive instruments. This means Antarctic ice is connected not only to sea level, but also to the physical behavior of the planet. The continent is enormous enough that changes within it can have planetary consequences. A little snowfall here, a little melting there, a glacier speeding up, an ice shelf thinning. Each event becomes part of a global system. The scale of Antarctica is difficult to appreciate until you realize how far its influence extends. And yet, tonight, we do not need to think about all of that at once. We can return to the quiet image of the ice. Imagine the ancient bubble again. It has traveled through the continent. It has moved with the glacier. It has passed over mountains hidden beneath kilometers of ice. It has crossed valleys. It has approached the coast. Now it rests inside floating ice. The ocean moves beneath it. The iceberg drifts slowly. The sun sets. The sky becomes dark. Stars appear. Perhaps the iceberg will survive for years. perhaps decades. Its edges will slowly change. Wind will sculpt the surface. Waves will erode the base. Warm currents will melt it. Cracks will form. Pieces will break away. Eventually, the ancient air will return to the atmosphere. The journey of that tiny bubble will finally end. But the water will continue. Nothing in Antarctica truly disappears. Snow becomes ice. Ice becomes ocean. Ocean becomes vapor. Vapor becomes snow. Rock becomes sediment. Sediment becomes part of the seafloor. Nutrients move through food webs. Carbon moves between atmosphere, ocean, ice, and life. Everything is connected. Everything is moving, even when the landscape appears still. And now, as we continue drifting through this part of the story, the hidden rivers beneath the ice begin to fade into the darkness. The mountains remain buried. The lakes remain sealed. The ocean continues moving. The ice continues flowing. And the Antarctic night stretches quietly across the continent. There is no need to hurry toward the next discovery. For this continent, time itself moves slowly. A glacier can spend thousands of years traveling toward the sea. An ancient mountain can remain hidden beneath ice for millions of years. A bubble of atmosphere can wait hundreds of thousands of years before someone finally opens it. And beneath the darkness, the hidden water continues its patient journey. Slowly, quietly, always moving. The hidden water beneath the ice is still moving as our journey continues. Somewhere beneath the enormous frozen surface, a lake slowly fills. A narrow channel carries water toward another basin. Above it, kilometers of ice remain almost perfectly still. And while this hidden world moves in darkness, the surface of Antarctica begins to change with the seasons. The long polar night gradually gives way to returning light. The horizon brightens. The sun approaches. And with that returning sunlight comes one of the most extraordinary seasonal transformations on Earth. Because Antarctica is not always the silent white landscape we imagine. For part of the year, the surrounding ocean becomes crowded with life. Ice begins to retreat. Light returns to the water. Microscopic organisms awaken. Krill gather. Penguins return. Seals begin to feed. And whales arrive from distant oceans. So, continuing from where we left off, let us follow the movement of that life around the frozen continent. The seasonal cycle of Antarctica is closely connected to sunlight. Near the South Pole, the sun can remain below the horizon for months during winter. Then, as Earth continues its journey around the sun, daylight slowly returns. The change is gradual. At first, the sun barely appears. Then daylight lasts longer. Eventually, the sun remains above the horizon for an extended period. The difference between winter and summer can feel like the difference between two worlds. At the South Pole itself, there is essentially one sunrise and one sunset each year. The sun rises around the beginning of spring. It circles around the horizon. For months, it gradually climbs higher. Then it begins to descend. Eventually, it disappears again. One sunrise, one sunset, an entire year compressed into one enormous cycle of light and darkness. The sun does not simply rise and set normally at the pole. Instead, around the time of the equinox, it appears to move almost sideways along the horizon. For a while, the sun seems to circle the observer rather than traveling dramatically upward and downward. The sky becomes a slow-moving clock. Hours pass. The sun changes position, but it never behaves quite like it does at lower latitudes. The Antarctic summer brings almost continuous daylight to large parts of the continent. At the South Pole, the sun remains above the horizon for roughly half the year. This creates an unusual environment for living organisms. During summer, there is almost no traditional nighttime. The sky may become slightly darker near the horizon, but the sun remains present. For animals and microorganisms, this prolonged sunlight creates an enormous seasonal opportunity. The ocean responds quickly to returning light. Phytoplankton begin to grow. These microscopic organisms use sunlight to convert carbon dioxide and water into organic matter. They form the foundation of much of the Southern Ocean food web. A tiny bloom of phytoplankton can eventually support enormous populations of krill. And those krill can support fish, penguins, seals, seabirds, and whales. The entire ecosystem can begin with microscopic organisms responding to sunlight. Phytoplankton are incredibly small. Many are only a few micrometers across. Yet during large blooms, their total biomass becomes enormous. They can change the color of the ocean. From above, satellites can sometimes detect these blooms as broad patches of green or blue-green water. A biological event occurring at microscopic scales can become visible from hundreds of kilometers above Earth. The growth of phytoplankton depends on several things. Sunlight is essential for photosynthesis. Nutrients are also necessary. The Southern Ocean contains large amounts of nutrients such as nitrate and phosphate. Iron can be more limiting in some regions. When the right combination of light, nutrients, temperature, and water mixing occurs, phytoplankton can multiply rapidly. The ocean suddenly becomes biologically active. Iron is particularly interesting. Tiny quantities can have enormous effects. Some Antarctic waters contain plenty of major nutrients, but relatively little available iron. Dust from continents can supply iron. Glacial runoff can contribute minerals. Upwelling can bring nutrients from deeper waters. When iron becomes available, certain phytoplankton may grow more rapidly. A trace element can influence an entire ecosystem. The Southern Ocean is constantly mixing. Winds push surface water. Storms disturb the upper ocean. Currents transport water. Cold water sinks. Deep water rises. This vertical movement can bring nutrients toward the surface. The result is a constantly changing chemical environment. The ocean is not a layered glass of still water. It is a living, moving system. When phytoplankton grow, something remarkable happens. Carbon dioxide is removed from the water during photosynthesis. Some of the resulting organic matter becomes food. Tiny organisms eat the phytoplankton. Larger organisms eat them. Some organic material eventually sinks. Carbon can therefore move from the surface toward the deep ocean. This is part of the biological carbon pump. The sinking material is sometimes called marine snow. We encountered it earlier in our journey. Now imagine it during the Antarctic summer. Near the surface, sunlight fills the water. Phytoplankton multiply. Tiny animals graze on them. Waste particles and fragments begin drifting downward. Slowly they fall. A gentle snowfall takes place beneath the waves. But this snow is biological. Some marine snow is consumed before it reaches the deep ocean. Bacteria break it down. Small animals feed on it. Larger organisms consume those animals. The material is recycled, but some continues downward. Eventually, organic carbon can reach deeper waters. The ocean becomes a giant transport system. Krill are among the most important animals in this system. Antarctic krill are small crustaceans. They resemble tiny shrimp. Yet enormous populations can form. They are a critical food source for many Antarctic predators. Whales eat them. Seals eat them. Penguins eat them. Fish eat them. Birds eat them. Krill connect microscopic producers to some of the largest animals on Earth. A krill may begin life as a tiny larva. It develops through several stages. As it grows, its body changes. Eventually, it becomes part of the enormous adult population. Krill can gather in dense swarms. These swarms may extend for kilometers. From the surface, they may be invisible. But underwater, the water can be filled with millions of tiny animals. Krill swarms are not randomly distributed. They respond to food availability, ocean currents, temperature, sea ice, predators, depth, light. The animals move vertically through the water column. During the day, many remain deeper. At night, they can rise toward the surface to feed. This daily movement is called vertical migration. In Antarctica, the cycle can become complicated because summer daylight may last almost continuously. The usual distinction between day and night becomes blurred. Krill still respond to changes in light intensity. They can move through the water according to the brightness of their environment. Even under continuous summer sunlight, their behavior remains linked to the daily rhythm of illumination. Krill also have an unusual ability to reduce their metabolism. During periods when food is scarce, they can slow down. This helps them conserve energy. Some Antarctic krill can survive periods of limited food availability. Their life cycle is adapted to the extreme seasonality of the polar environment. Summer provides abundant food. Winter is much more difficult. Survival requires careful energy management. Sea ice becomes important during winter. Krill can feed on algae associated with the underside of sea ice. When open water phytoplankton production declines, sea ice communities provide another source of food. The ice is therefore not simply frozen ocean. It can become a living surface. Under Antarctic sea ice, tiny algae attach themselves to the ice. They occupy channels and spaces within the frozen structure. The ice contains microscopic habitats. Water flows through tiny pathways. Nutrients are exchanged. Microorganisms grow. Krill can graze on this material. The frozen surface becomes the foundation of a winter food source. When spring returns, the sea ice begins to retreat. Light penetrates more easily into the upper ocean. Phytoplankton bloom. Krill feed. Predators arrive. The ecosystem becomes increasingly active. The seasonal retreat of ice, therefore, triggers a cascade of biological events. One physical change creates many biological responses. Penguins are among the most visible animals participating in this cycle. Different species have different relationships with sea ice. Emperor penguins are especially associated with the Antarctic interior and sea ice. They breed during the Antarctic winter. This makes their life cycle extraordinary. While much of the continent becomes colder and darker, emperor penguins move into some of the harshest conditions on Earth to reproduce. The emperor penguin breeding cycle begins after adults gather at colonies. They travel across sea ice. The journey can take many days. Eventually, they reach traditional breeding areas. There, eggs are laid. The female transfers the egg to the male. The transfer must be extremely careful. The egg cannot remain exposed to the freezing surface for long. The male emperor penguin balances the egg on his feet. A fold of warm skin covers it. The female then travels toward the ocean. She leaves the colony to feed. The male remains behind. He may fast for weeks. He stands among thousands of other males. The colony becomes a landscape of tightly packed bodies. The Antarctic winter arrives. Temperatures fall dramatically. Winds become intense. Darkness surrounds the colony. The males turn their bodies inward. They huddle together. The outer birds experience colder conditions. The inner birds remain warmer. Over time, they rotate positions. Birds from the outside move inward. Birds from the center move outward. The entire colony behaves almost like a living thermal system. The huddle is one of the most remarkable examples of cooperative behavior in the animal world. Thousands of penguins reduce heat loss by standing close together. The configuration changes continuously. Individual birds do not simply remain in one position. They gradually shift. The huddle moves. It compresses. It expands. And somehow, through countless small movements, the colony maintains a remarkable degree of organization. The males may endure temperatures far below freezing. They cannot leave the egg. They cannot build a nest from vegetation because almost none exists. They simply protect the egg with their bodies. Their survival depends on stored energy and cooperation. Eventually, the egg hatches. The timing is crucial. The chick emerges while the father may have nearly exhausted his energy reserves. But the mother eventually returns from the ocean. She arrives carrying food. The chick can begin receiving nourishment. The father can finally leave. He has survived the winter. The emperor penguin colony then begins another phase. Parents alternate between feeding trips and caring for the chick. The chick grows. Its feathers change. Eventually, young penguins become more independent. The colony's summer environment becomes increasingly favorable. Food is available. Daylight is abundant. Sea ice begins to change. Penguins are superb swimmers. Their wings have evolved into flippers. Underwater, they can move rapidly. They use their bodies like streamlined torpedoes. Their feathers provide insulation. Their dense bodies help them dive. Their ability to swim is central to their survival. On land, they appear somewhat awkward. Underwater, they are completely different. Penguins can also leap from the water. They may use a behavior known as porpoising. They repeatedly break the surface while swimming rapidly. This may help reduce drag in certain circumstances. It can also allow them to breathe while maintaining speed. Watching a group of penguins porpoise across the ocean can look almost like a sequence of small black and white waves. Some penguins can dive surprisingly deep. Emperor penguins are among the deepest diving birds. They can descend to hundreds of meters. Their bodies tolerate pressure that would be dangerous for humans. Their oxygen stores are carefully managed. They slow their heart rates. They conserve oxygen. They remain underwater while searching for prey. At depth, sunlight becomes weak. The penguins navigate through darkness. Their prey may include fish, squid, and krill. They use their vision to locate food. When they return toward the surface, they must manage their oxygen reserves carefully. Their entire dive is an exercise in energy management. Penguins also have dense bones compared with many flying birds. This reduces buoyancy. A flying bird benefits from lightweight bones. A diving penguin benefits from a body that can sink efficiently. Evolution has reshaped the same basic skeletal system for a completely different lifestyle. Penguin feathers are another remarkable adaptation. Their feathers are short and densely packed. They form a protective layer against cold water. Penguins also have a layer of body fat beneath the skin. Together, feathers and fat help reduce heat loss. But insulation creates another challenge. A penguin can overheat during activity. The body therefore needs ways to regulate temperature. Penguins can release heat through less insulated areas of the body. Their feet and flippers can participate in heat exchange. Blood vessels can change how much warm blood reaches the extremities. The body constantly balances heat conservation and heat loss. In Antarctica, staying warm is essential. But controlling temperature is equally important. Seals face similar challenges. Several species live around Antarctica. The leopard seal is one of the most powerful predators. It has a long body, large jaws, and distinctive spotted markings. It can hunt fish, penguins, and other seals. It is also capable of feeding on krill. Its diet is remarkably flexible. Leopard seals often rest on sea ice. They can remain still for long periods. The surface may be white. The seal's body becomes part of the landscape. When prey approaches, it can move rapidly. Its large jaws are particularly effective against penguins. The predator-prey relationship around Antarctic ice can be intense. Weddell seals have a different reputation. They are among the southernmost breeding mammals. They can live and reproduce in areas surrounded by sea ice. Their bodies are adapted to diving and cold. They have thick layers of blubber. Their blood and muscles store oxygen. They can remain underwater for long periods. Weddell seals can also maintain breathing holes in sea ice. They use their teeth to keep holes open. The ice constantly tries to freeze shut. The seal repeatedly scrapes and bites the edges. Over time, its teeth can become worn. Yet these breathing holes are essential. Without access to air, the seal could not survive beneath the ice. Imagine a Weddell seal beneath the winter sea ice. The world above is frozen. The water below is dark. The seal moves through the cold ocean. It hunts. It swims. Then it returns to a small opening in the ice. It surfaces. Breath enters its lungs. Then it disappears again beneath the frozen ceiling. The seal's whiskers are extremely sensitive. They can detect disturbances in the water. A moving fish creates a trail. The whiskers can sense these tiny changes. Even in dark water, the seal can gain information about nearby movement. Its face becomes a sensory instrument. Crab-eater seals have another fascinating adaptation. Despite their name, they do not primarily eat crabs. Their main food is Antarctic krill. Their teeth are specially adapted for filtering krill from seawater. They can take in water and use their teeth to strain out prey. The name crab-eater is therefore somewhat misleading. Crab-eater seals are among the most abundant seals in Antarctica. Their population is closely connected to krill availability. When krill are abundant, they have access to enormous quantities of food. The seal can consume large amounts of tiny prey. Once again, microscopic organisms support large predators. Raw seals are less commonly seen. They live mainly in areas of pack ice. They have large eyes. Their bodies are compact. They can dive deeply. Because they are difficult to observe, much of their behavior remains mysterious. They spend much of their lives in remote waters. The Antarctic fur seal has a different evolutionary story. It was once hunted almost to extinction for its fur. Commercial sealing dramatically reduced populations. After protection was introduced, some colonies recovered. This is an important reminder that Antarctic wildlife is not invulnerable simply because the environment is remote. Human activity has reached even the ends of the Earth. Whales also return to Antarctic waters during the productive season. Many migrate toward warmer regions during parts of the year. They breed in lower latitudes. Then they travel toward the polar waters to feed. The journey can cover thousands of kilometers. Their migration follows the seasonal availability of food. Humpback whales are among the most visible visitors. They can gather in Antarctic waters where krill are abundant. A single whale can consume enormous quantities of food. When many whales arrive, the ocean becomes a feeding ground. Their presence transforms the scale of the ecosystem. Humpback whales also produce complex songs. Their songs are most strongly associated with breeding behavior in other regions. In Antarctic feeding grounds, Whales can communicate using various sounds. The ocean carries sound extremely well. A whale can produce a call that travels through the water. Another whale may detect it from far away. Whale communication can be mysterious. Some sounds travel enormous distances. The ocean becomes a giant acoustic environment. Humans can hear only a small portion of the sounds produced by marine animals. Hydrophones allow scientists to listen. They can detect whales even when the animals are hidden beneath the surface. The ocean can reveal animals through sound when sight is impossible. Blue whales also visit Antarctic waters. They are the largest animals known to have existed on Earth. Their bodies can reach extraordinary lengths. Their hearts are enormous. Their tongues can weigh as much as an elephant in some comparisons. Yet their food consists largely of tiny krill. The largest animal on the planet feeds on one of the smallest important animals in the Antarctic food web. This is one of Antarctica's most beautiful contradictions. A whale weighing many tons can depend on tiny crustaceans. A penguin can depend on krill. A seal can depend on krill. Fish can depend on krill. And krill depend heavily on microscopic organisms. At the foundation are creatures so small that an individual one can disappear between your fingertips. The entire food web rises from microscopic life. Orcas also hunt in Antarctic waters. Different populations have different diets. Some specialize in fish. Others hunt marine mammals. Some can prey on seals resting on ice. Their intelligence and coordinated behavior make them formidable predators. Orcas can work together. They may coordinate movements. They can create waves. In some regions, groups have been observed using waves to wash seals from ice floes. The behavior requires timing and cooperation. A group of whales can transform the ocean into a hunting strategy. The Antarctic ecosystem, therefore, contains layers of intelligence. A penguin searches for krill. A seal searches for fish or penguins. An orca searches for seals. A whale searches for krill. Tiny organisms search for chemical resources. Every animal occupies a particular place in the system, and every layer depends on the physical environment. The return of sunlight changes all of these relationships. More light produces more phytoplankton. More phytoplankton support more krill. More krill support more predators. Predators arrive. Breeding begins. Feeding increases. The summer ecosystem becomes intensely active. Yet winter eventually returns. The sun begins to sink lower. Sea ice expands. The ocean becomes darker. Phytoplankton production decreases. Krill change their behavior. Some animals migrate. Others remain. Penguins endure the cold. Seals hunt beneath the ice. The ecosystem contracts. Then the cycle begins again. Antarctica is therefore governed by rhythm. Light and darkness. Freezing and melting. Growth and scarcity. Arrival and departure. Expansion and retreat. The continent does not remain biologically identical throughout the year. It pulses. The entire ecosystem breathes with the seasons. And now, as we continue drifting through the Antarctic night, imagine the summer ocean slowly becoming darker again. The whales have begun their journeys. The penguin colonies become quieter. Sea ice expands across the water. Tiny organisms settle beneath the frozen surface. The wind moves over the ice. The sun sinks lower, and the continent prepares for another long winter. But beneath the ice, the hidden water continues to move. The subglacial lakes remain. The ancient mountains remain buried. The glaciers continue their slow journey. And deep below the ocean surface, creatures continue moving through the darkness. Nothing has truly stopped. The rhythm simply changes. the Antarctic world becomes quieter, slower, darker, and deeper. The darkness beneath the Antarctic ice is still around us. We have followed water through hidden channels, watched glaciers move toward the sea, and watched the summer ocean fill with krill, penguins, seals, and whales. Now the season is beginning to turn again. The light is fading. Sea ice is expanding. The animals are adjusting. And beyond the familiar coastline, Antarctica is about to reveal another side of itself. A continent of deserts, strange valleys, ancient rocks, hidden volcanoes, and places where almost nothing seems alive. Yet even there, life has found a way. As winter approaches, the sea around Antarctica begins to freeze outward from the coast. The process starts in many places at once. Tiny ice crystals form on the ocean surface. They collide. They join together. A thin layer develops. Wind pushes pieces together. Waves break them apart. The frozen fragments gradually become larger. Eventually, broad fields of sea ice spread across the Southern Ocean. Sea ice can transform the appearance of Antarctica. During summer, large areas of ocean may be open. During winter, the coastline can become surrounded by enormous expanses of floating ice. The continent appears to grow, but this is not new land. It is frozen seawater. The distinction is important. Sea ice is generally much thinner than the Antarctic ice sheet. Its thickness varies depending on location, season, snow cover, wind, ocean currents, and how long the ice has survived. Some sea ice remains for more than 1 year. Other ice melts during the summer and reforms during the next winter. This seasonal cycle creates one of the largest annual transformations on the planet. As the sea freezes, salt is largely excluded from the ice crystals. The remaining seawater becomes saltier. That denser water can sink. This process contributes to the formation of Antarctic bottom water. Deep beneath the ocean surface, dense Antarctic water can travel outward into the global ocean. The freezing of a thin layer at the surface can therefore help influence waters thousands of meters below. Antarctic bottom water is among the coldest and densest major water masses in the world's oceans. It forms in certain regions around Antarctica where very cold, salty water becomes dense enough to sink. Once it reaches the deep ocean, it can spread far beyond Antarctica. Its journey can continue for years, decades, or longer. A drop of Antarctic water can eventually become part of the deep ocean far away from the continent. The deep ocean is therefore connected to Antarctica. Even if you are thousands of kilometers away, some of the water beneath you may have been influenced by processes near the Antarctic coast. The ocean is a global system. Water moves, heat moves, salt moves, nutrients move, carbon moves. Antarctica participates in all of it. The formation of dense water also helps drive large-scale ocean circulation. It is one part of a complicated system involving sinking and rising water, winds, temperature differences, and salinity. Scientists sometimes describe these movements as part of the global overturning circulation. It is not a simple conveyor belt. The real system contains many branches, eddies, mixing zones, and timescales. But the basic idea remains fascinating. Water can begin near Antarctica and eventually influence distant parts of the ocean. Meanwhile, the expanding sea ice changes the habitat around the continent. Some animals use it as a platform. Some feed around its edges. Some live beneath it. Some avoid it. For penguins, seals, and microorganisms, the annual expansion and retreat of sea ice can determine where food is available. Emperor penguins are particularly dependent on stable sea ice during their breeding season. They need a platform that remains intact long enough for chicks to develop. If the ice disappears too early, young penguins may enter the ocean before their feathers are ready. The timing of sea ice breakup can therefore become extremely important. Other penguin species prefer different environments. Adelie penguins are closely associated with sea ice and open water, but can also breed on exposed rocky coastlines. Their colonies can be enormous. During the breeding season, thousands of birds gather. The landscape becomes filled with calls, movement, and activity. Adelie penguins build nests from small stones. A single pebble can become valuable. Penguins may collect stones from the surrounding ground. They arrange them into small nests. Competition over stones can occur. A bird may steal a particularly useful pebble from a neighboring nest. What seems like an insignificant piece of rock becomes important to reproduction. The nests keep eggs slightly elevated from the cold ground. They can also help with drainage. In a landscape where snow and meltwater may occur during warmer periods, elevation can make a difference. The simple stone nest is a small example of how animals modify their environment. Adelie penguins are also highly efficient swimmers. They pursue krill and fish. Their bodies are streamlined. Their feathers create a dense waterproof layer. Their flippers provide propulsion. Their feet act as steering surfaces. Underwater, the bird becomes a completely different creature from the waddling animals seen on land. Penguins also have remarkable control over their feathers. They spend considerable time preening. Oil from a gland near the base of the tail helps waterproof the feathers. The penguin spreads the oil across its plumage. This reduces water penetration. Without effective waterproofing, cold seawater would rapidly remove body heat. Waterproof feathers are essential because water conducts heat much more efficiently than air. A penguin's body must maintain its internal temperature while moving through extremely cold water. Dense feathers and insulating fat work together. The animal becomes a highly efficient biological diving suit. The Antarctic environment also has some of the world's driest places. This may sound strange because Antarctica contains enormous quantities of ice. But dryness refers to precipitation, not simply the amount of frozen water already stored. Some regions receive extremely little snowfall. The McMurdo Dry Valleys are among the most famous examples. They contain broad valleys with almost no permanent surface ice. The dry valleys are often described as one of the closest terrestrial analogs to Mars. The landscape contains exposed rock. The atmosphere is extremely dry. Temperatures are harsh. Liquid water is scarce. Vegetation is almost absent. Strong winds can remove snow. The valleys appear otherworldly. The dry valleys are not completely lifeless. Microorganisms survive in protected environments. Some live inside rocks. Others occupy tiny amounts of moisture in soil. Certain organisms can survive in places where liquid water is available only briefly. Life does not need a lush environment to exist. Sometimes it only needs a microscopic refuge. Endolithic organisms are microorganisms that live within rocks. The rock provides protection from harsh environmental conditions. Tiny cracks and spaces can hold moisture. Light may penetrate slightly into translucent minerals. Some microorganisms can use this limited energy. The rock becomes a shelter. From the outside, it looks completely barren. Inside, microscopic life may exist. This is one of the most extraordinary ideas in Antarctic biology. A stone lying on the ground can appear completely dead, yet inside that stone may be a microscopic ecosystem. The organisms remain protected from wind. They avoid some of the extreme temperature changes at the surface. They use tiny amounts of water. Their lives proceed extremely slowly. Some Antarctic microorganisms can enter dormant states. When conditions become too dry or too cold, biological activity decreases dramatically. The organism essentially waits. When water becomes available again, activity can resume. This ability to survive extreme dryness is one reason Antarctic microbes are studied by astrobiologists. Mars is also extremely dry. Its surface contains frozen water. Some regions show evidence of ancient flowing water. Modern liquid water is difficult to maintain at the surface. Scientists therefore study Antarctic dry environments as analogs. They ask how life survives when water is scarce. They study how microorganisms protect themselves. They investigate how biological activity leaves traces. These lessons may help guide future exploration of Mars. Antarctica has another connection to Mars. Both environments contain polar ice. Both experience extreme seasonal changes. Both have strong winds. Both contain barren landscapes. Both can experience temperatures far below the freezing point of water. But Antarctica is not Mars. Earth's atmosphere is different. Earth has abundant liquid water in the ocean. Earth has a protective magnetic field. Earth supports a rich biosphere. The similarities are useful, but the differences are enormous. The McMurdo Dry valleys contain unusual geological formations. Streams can appear temporarily during warmer periods. Glacial meltwater flows through certain valleys. Some streams may exist only for short periods each year. The water can feed small lakes. These lakes may remain covered by ice for much of the year. Antarctic lakes can be extremely unusual. Some are permanently covered by thick ice. Sunlight can penetrate through the upper ice. Microorganisms may grow beneath it. The water below can remain liquid. In some lakes, the chemistry becomes highly unusual. Salt concentrations can be high. Some lakes contain water much salter than seawater. One famous example is Don Juan Pond. It is a hypersaline pond in the McMurdo Dry valleys. Its extremely high salt concentration allows water to remain liquid at temperatures well below the normal freezing point of freshwater. The pond can appear shallow and unremarkable, but chemically, it is extraordinary. Salt changes the freezing point of water. The more dissolved material there is, the lower the temperature at which freezing occurs. This is why salt is used to melt ice on roads. In highly saline environments, the effect becomes much stronger. Antarctic hypersaline ponds demonstrate how chemistry can keep water liquid under extreme conditions. Other Antarctic lakes are much larger. Lake Vita is another unusual lake in the dry valleys. It is covered by thick ice. The water beneath is extremely salty. Microbial life has been detected in its environment. The organisms survive in conditions that seem almost impossible. They have adapted to cold, darkness, and high salinity. The water beneath Antarctic lake ice can remain isolated for long periods. The ice cover reduces exchange with the atmosphere. Chemical conditions can become very different from those at the surface. Oxygen may be limited. Salinity can increase. Different microbial communities can develop. Each lake becomes its own small laboratory. Some Antarctic lakes are colored red. One of the most famous examples is Blood Falls. The name sounds dramatic, but the phenomenon has a natural explanation. Water emerging from beneath the Taylor Glacier contains high concentrations of dissolved iron. When the iron-rich water reaches the surface and contacts oxygen, the iron oxidizes. The resulting reddish color stains the ice. Blood Falls is connected to a hidden subglacial water system. Briny water moves beneath the glacier. It eventually emerges through a fissure. The water is extremely cold and salty. When it reaches the surface, the iron reacts with oxygen. A red stain appears against the white ice. The contrast is extraordinary. The water at Blood Falls is not actually blood. Its color comes from chemistry. Iron compounds are responsible for the reddish appearance. It is another example of how Antarctic landscapes can look mysterious while having perfectly natural physical explanations. The Taylor Glacier is part of the McMurdo Dry Valleys. It flows slowly through a landscape almost completely different from the classic image of Antarctica. There are no endless white plains here. Instead, there are exposed rocks, mountains, dry valleys, and scattered glaciers. The continent contains many different environments. Antarctica is not uniformly white. Its rocks can be dark. Its mountains can be brown, black, or reddish. Its glaciers can appear blue. Its snow can become gray with dust. Its ice can become almost transparent. The colors of Antarctica depend on geology, light, ice structure, and weather. Blue ice areas are particularly fascinating. Strong winds can remove snow from the surface. Ice that has accumulated over long periods can become exposed. This old ice may be intensely blue. Blue ice fields can contain ancient atmospheric information. They can also expose meteorites that have fallen onto Antarctica. Antarctica is one of the best places on Earth to find meteorites. This seems surprising. You might expect meteorites to be easier to find in deserts. But Antarctica has several advantages. Dark meteorites stand out against bright snow and ice. The dry environment helps preserve them. And moving ice can concentrate meteorites in particular regions. A meteorite can fall onto the Antarctic ice. It becomes buried. The ice slowly moves. Eventually, the meteorite may be brought back toward the surface in a blue ice area. Wind removes surrounding snow. The dark rock becomes visible. Scientists can then collect it. Some Antarctic meteorites originated on the Moon. Others came from Mars. Many came from asteroids. Each meteorite is a fragment of another world. A small dark stone lying on a frozen Antarctic plain may have traveled through space for millions or billions of years before landing on Earth. Martian meteorites are especially valuable. They contain chemical and mineral evidence from Mars. Scientists can study them without sending a spacecraft to collect rocks. Some contain gases trapped inside that match the composition of the Martian atmosphere measured by spacecraft. These rocks provide direct physical samples of another planet. Lunar meteorites can also be found. The Moon has been struck by impacts. Fragments of lunar rock can be blasted into space. Some eventually cross Earth's orbit. A few fall onto Antarctica. The continent becomes a natural collection site for material from the solar system. Antarctica also preserves meteorites because weathering is limited. In warmer, wetter regions, rocks can break down. Rain, plants, soil, chemical reactions. These processes can alter meteorites. In Antarctica, the cold and dryness slow many forms of weathering. A meteorite can remain recognizable for a very long time. Scientists organize expeditions to search for these extraterrestrial rocks. Teams travel across remote ice fields. They scan the surface carefully. A single unusual rock can be extremely valuable. The search may look simple, but the environment makes it difficult. Cold, wind, crevasses, remote terrain, limited visibility. The researchers must work carefully. Imagine walking across a vast blue ice field. There are no trees, no buildings, no roads, only mountains in the distance. The ground is frozen. The sky is enormous. And somewhere ahead lies a tiny rock that may have come from Mars. It has been waiting there silently, perhaps for thousands of years, perhaps longer. Meteorites are not the only things preserved by Antarctica. The ice can preserve volcanic ash, ancient atmospheric gases, dust, microorganisms, chemical traces, and even fragments of material transported from distant regions. The continent is a giant natural archive. Antarctica also contains active volcanoes. One of the most famous is Mount Erebus. It rises on Ross Island. Its summit reaches more than 3,700 meters above sea level. It is one of the southernmost active volcanoes on Earth. Snow and ice surround it, yet molten rock exists beneath. Mount Erebus has a persistent lava lake. Lava at the surface can remain molten for long periods. The lake glows beneath the Antarctic sky. Gas rises from the volcanic system. The surrounding landscape can be covered in snow, while liquid rock burns deep inside the crater. Fire and ice exist side by side. The lava lake can change over time. Crust forms on its surface. The crust breaks apart. Molten lava appears beneath. Gas bubbles rise. The surface shifts. Volcanic activity continues. It is an extraordinary contrast to the frozen environment surrounding the mountain. Mount Erebus is also a source of volcanic gases. The volcano releases compounds into the atmosphere. Scientists monitor these emissions. They can provide clues about the magma system below. Volcanic gases are part of Earth's natural cycles. Even in Antarctica, Earth's interior remains active. Volcanoes remind us that Antarctica is not geologically frozen. The continent may be covered by ice, but beneath that ice, Earth remains dynamic. Magma moves, faults shift, mountains rise, rock erodes. The planet is alive geologically. Antarctica also contains evidence of ancient volcanic activity. Ash layers can be preserved inside the ice. Rock formations record eruptions that occurred millions of years ago. Some volcanic landscapes are now completely covered. The continent's geological history extends far beyond the modern ice age. Before Antarctica became the frozen continent we know today, it was much different. It was once part of the supercontinent Gondwana. Gondwana included South America, Africa, India, Australia, Antarctica, and other landmasses. These continents were once joined. Over geological time, tectonic forces separated them. Antarctica therefore shares geological history with distant continents. Similar rock formations can be found across regions that are now separated by oceans. Fossils found in Antarctica also reveal connections with other continents. The rocks tell a story of movement. The continents themselves have traveled. Antarctica was not always covered in permanent ice. Millions of years ago, parts of the continent supported forests. The climate was dramatically warmer. Fossils reveal evidence of plants, leaves, wood, pollen, and other biological remains. The frozen continent once contained ecosystems that would look completely unfamiliar today. Coal deposits have also been found in Antarctica. Coal forms from accumulated plant material that is buried and transformed over geological time. Finding coal in Antarctica demonstrates that vegetation once grew there in significant quantities. The continent's current coldness is not permanent on geological timescales. Climate can change enormously. Continents can move. Oceans can open. Atmospheric composition can shift. Fossilized plants provide clues about ancient Antarctic climates. Scientists can identify species. They can study growth patterns. They can examine pollen. They can reconstruct ecosystems. A leaf preserved in Antarctic rock can tell a story from millions of years ago. Dinosaur fossils have also been discovered in Antarctica. This is another reminder that the continent was once much warmer. Dinosaurs lived there when Antarctica was part of Gondwana. Some species were adapted to polar conditions. They may have experienced long periods of darkness even in the ancient world. One famous Antarctic dinosaur is Cryolophosaurus. Its fossils were discovered on the continent. The name is associated with its distinctive crested skull. It lived during the early Jurassic. At that time, Antarctica was not the frozen desert we know today. The continent supported forests and flowing water. Other prehistoric animals lived there too. Antarctica has produced fossils of ancient reptiles, amphibians, and mammals. These discoveries help reconstruct ecosystems from periods when the continent was warmer. The modern ice hides a much older biological history. Some Antarctic fossils contain evidence of ancient forests. Tree-like plants once grew in regions that now experience extreme cold. The sunlight pattern was different. The atmosphere was different. The oceans were different. The continents were positioned differently. The world was fundamentally different. This ancient history also reminds us that Antarctica's current climate is only one chapter. The continent has experienced many climates: warm, temperate, cold, glaciated. It has been connected to other continents. It has been isolated. It has supported forests. Now it supports ice. Earth has never been static. The rocks beneath the ice preserve these transitions, layer by layer, mineral by mineral, fossil by fossil. Antarctica contains clues to ancient worlds that disappeared long before humans existed. And now, as our journey continues, imagine standing beneath the modern Antarctic night. The ancient forest is gone. The dinosaurs are gone. The warm rivers are gone. The land is covered in ice. But the rocks remember. The fossils remember. The mountains remember. The ice records the more recent climate. The continent carries multiple versions of Earth at once. Above the ice, stars shine with almost no artificial light. Antarctica has some of the darkest skies on Earth. There are very few cities, very few roads, almost no permanent human settlements outside research stations. Light pollution is minimal across vast areas. The night sky can therefore appear extraordinarily clear. The Milky Way can stretch across the sky. Thousands of stars become visible. The southern sky contains constellations that are difficult or impossible to see from northern latitudes. The stars seem especially sharp against the dark Antarctic atmosphere. The South Pole also offers a unique view of the sky. Because of Earth's rotation, stars appear to circle around the celestial South Pole. They do not rise and set in the familiar way seen at many other latitudes. Instead, many stars trace circular paths. The sky becomes a slow-moving wheel. The Southern Cross is one of the most famous southern constellations. It has been used for navigation for centuries. Its stars can help locate the direction toward the southern celestial pole. The constellation is relatively small but distinctive. The Magellanic Clouds are also visible from Antarctica. These are dwarf galaxies orbiting the Milky Way. They appear as faint patches of light in the southern sky. Unlike ordinary clouds, they are enormous collections of stars. Their light has traveled across intergalactic space before reaching Earth. From Antarctica, the sky therefore contains both familiar stars and distant galaxies. The frozen surface beneath you belongs to Earth. The light above you may have traveled thousands, millions, or hundreds of thousands of years. The continent becomes a quiet observatory. Antarctica is also an excellent location for certain astronomical observations because the air is extremely dry. Water vapor interferes with some types of infrared and microwave observations. The dry Antarctic atmosphere can provide unusually good conditions. High elevation sites can be especially valuable. The South Pole has hosted major astronomical instruments. Researchers study the cosmic microwave background. They observe the atmosphere of Earth. They examine distant astronomical sources. They search for subtle signals. The cold and dry environment can be an advantage. One remarkable instrument is the South Pole Telescope. It studies the universe using microwave wavelengths. Scientists can use observations of the cosmic microwave background to learn about the structure and history of the universe. The instrument sits in one of the most remote scientific environments on Earth. Another extraordinary experiment is IceCube. Instead of looking outward into space, it looks for particles passing through Earth. The detector is buried deep inside Antarctic ice. Thousands of optical sensors are distributed through the ice. They detect flashes of light produced when neutrinos interact with matter. Neutrinos are incredibly elusive particles. They have no electric charge. They interact extremely weakly with matter. Trillions pass through your body every second. You do not feel them. They pass through Earth. They pass through Antarctica. They pass through almost everything. The Antarctic ice becomes part of a gigantic particle detector. A neutrino can travel through Earth. Eventually, one may interact with an atom inside the ice. That interaction can produce charged particles. Those particles create faint flashes of blue light. Sensors detect the light. Scientists reconstruct the event. The idea is astonishing. A particle can begin its journey in a distant cosmic event. It travels through space. It reaches Earth. It passes through the planet. It enters Antarctic ice. And a tiny flash reveals its existence. The ice becomes a window into the universe. The same continent that preserves ancient air also detects particles from distant cosmic sources. The same ice that records Earth's climate can reveal information about black holes, supernovae, and other extreme objects. Antarctica is simultaneously a climate archive, biological laboratory, geological record, and astronomical observatory. And as the night grows deeper, all of these worlds seem to exist together. Above you, galaxies. Below you, ice. Deeper still, hidden water. Beneath that, ancient rock. Far away, whales move through dark oceans. On the surface, penguins huddle. Under the ice, microorganisms remain active. And inside the mountains, volcanic heat continues. The continent appears frozen, but nothing about it is truly motionless. The ice flows. The ocean circulates. The atmosphere moves. Volcanoes breathe. Water travels beneath the ice. Animals migrate. Microorganisms grow. Stars move across the sky. Earth itself continues turning. And perhaps that is the quietest lesson Antarctica offers. Stillness does not always mean nothing is happening. Sometimes the greatest movements are simply too slow for us to notice. A glacier moves a little. A mountain erodes a little. A continent shifts a little. A lake fills. A current travels. A species adapts. A layer of snow accumulates. And after thousands or millions of years, the small movements have created an entirely different world. So let the Antarctic night remain around you. The dry valleys become distant. The red water of blood falls disappears into the darkness. Mount Erebus glows faintly on the horizon. The hidden lakes remain beneath the ice. The meteorites rest quietly on blue ice fields. The ancient fossils remain locked in stone. And above everything, the southern stars continue their slow circular paths. Nothing needs to be rushed. Nothing needs to be solved. The continent can simply continue. Ice flowing, water moving, wind drifting, stars turning. And somewhere beneath the frozen surface, life remains quietly awake. The next part of our journey will take us deeper into the remarkable ways Antarctica interacts with the atmosphere, the climate, the surrounding oceans, and the rest of our planet. For now, the frozen continent grows quiet again, and beneath the long Antarctic darkness, the story continues. The Antarctic night has become almost completely still now. The hidden lakes remain beneath the ice. The ancient mountains remain buried. The blue ice fields quietly hold rocks that once traveled through space. The dry valleys stretch beneath a sky filled with stars. And far below the surface, the ice continues its incredibly slow journey toward the sea. We have traveled through Antarctica's hidden rivers. We have watched the ocean freeze and retreat. We have followed krill through the Southern Ocean and whales through the darkness. We have stood beside penguin colonies. We have looked into ancient rocks. We have listened to the silence of the polar night. But there is one final part of Antarctica's story to explore. It is the story of how this frozen continent connects to the entire planet. Because Antarctica may seem distant, it may seem isolated, it may seem like a world of its own, yet almost everything happening here has consequences somewhere else. And almost everything happening somewhere else eventually reaches Antarctica. The atmosphere above Antarctica is constantly moving. Even when the surface seems motionless, winds are crossing the continent. Some winds are created by differences in temperature and pressure. Others are shaped by the continent's enormous elevation. And some of the most famous Antarctic winds are katabatic winds. They begin when extremely cold, dense air forms over the high interior. The cold air becomes heavy. Gravity pulls it downhill. It begins sliding toward the coast. As it descends, it can accelerate. The result can be an extraordinarily powerful wind. In certain Antarctic valleys, katabatic winds can become intense enough to scour snow from the surface. They can carry ice crystals through the air. They can polish exposed rocks. They can make an already cold environment feel even more severe. These winds are part of the reason why some areas of Antarctica are so dry. Snow may fall, but powerful winds can remove it again. The Antarctic atmosphere is also extremely clean in many remote areas. There are almost no cities. Very little industrial activity occurs across the continent itself. The air can contain incredibly low concentrations of certain pollutants. This makes Antarctica valuable for atmospheric research. Scientists can examine chemicals that have traveled thousands of kilometers through the atmosphere. Pollution can reach Antarctica even though there are no major cities nearby. Particles and gases can travel through the atmosphere over enormous distances. Some originate from distant continents. Others come from natural sources. Volcanic gases can travel far. Smoke from fires can cross oceans. Dust can be carried by winds. The atmosphere has no borders. This means Antarctica can act like a recorder of global atmospheric conditions. Snow falls. Tiny particles become trapped. Gases are incorporated into the ice. Years pass. More snow arrives. Another layer forms. The atmosphere leaves a physical record. The deepest Antarctic ice contains information about hundreds of thousands of years of Earth's atmospheric history. Scientists drill ice cores. They remove long cylinders of ice. Each core contains layers accumulated over time. The deeper scientists go, the older the ice generally becomes. Inside those cores are tiny bubbles of ancient atmosphere. The bubbles are like miniature time capsules. They contain samples of air from the past. Scientists can measure gases such as carbon dioxide and methane. They can compare atmospheric composition with temperature indicators preserved in the ice. This allows researchers to reconstruct ancient climate conditions. The relationship between greenhouse gases and climate becomes visible across these ancient records. When greenhouse gas concentrations changed in the past, climate changed as well. The atmosphere and temperature are connected through physical processes that operate across the entire planet. Antarctic ice provides one of the clearest long-term records of this relationship. Ice cores can also contain dust. Dust is carried through the atmosphere. When conditions become especially dry in distant regions, more dust can enter the air. Winds transport it. Eventually, some of that dust reaches Antarctica. It falls onto the snow. It becomes buried. Thousands of years later, scientists can find it inside an ice core. The chemistry of the dust can reveal where it came from. Different rocks contain different minerals. Different regions produce distinctive chemical signatures. By studying those signatures, scientists can sometimes identify the source regions. A tiny particle buried in Antarctic ice can therefore reveal something about an ancient landscape thousands of kilometers away. Volcanic eruptions also leave signatures. Large eruptions inject sulfur-containing gases and ash into the atmosphere. Some of those materials travel around the planet. Eventually, they can reach Antarctica. The volcanic particles settle onto the snow. A thin chemical layer is preserved. Scientists can identify it inside ice cores. This creates a timeline of ancient eruptions. An eruption occurred. Particles entered the atmosphere. They traveled. They settled. Snow covered them. More snow accumulated. The event became a thin layer inside the ice. Thousands of years later, scientists can drill down and find it. The ice remembers volcanic explosions that no human witnessed. Some eruptions were enormous. Their atmospheric effects could temporarily influence climate. Sulfur compounds can form aerosols that reflect sunlight. This can produce short-term cooling. The effects vary depending on eruption size, location, atmospheric conditions, and chemical composition. Antarctic ice provides evidence that these events occurred. The snow itself also changes the record. Fresh snow is relatively loose. Air can move through it. As more snow accumulates, pressure increases. The snow becomes firm. The pores become smaller. Eventually, the material closes into solid ice. At that moment, the atmosphere inside becomes sealed. The depth at which bubbles become isolated varies. It depends on temperature, accumulation rate, and other conditions. In areas with high snowfall, the transition can happen relatively quickly. In extremely dry regions, it may occur much more slowly. The ice therefore records both climate and the processes that create the archive. Even the structure of individual ice crystals contains information. Crystals can grow and change shape. Pressure deforms them. Temperature influences them. Movement reorganizes them. The microscopic structure of the ice can reveal how the glacier has behaved. The ice sheet is also an enormous gravitational mass. Its weight presses down on Earth's crust. The bedrock beneath Antarctica is depressed by the enormous load. Where ice is removed, the crust can slowly rise. This process is called glacial isostatic adjustment. The ground responds to changes in the weight above it. This process happens very slowly. The crust does not suddenly spring upward when ice disappears. Instead, the solid Earth responds over years, decades, centuries, and longer periods. Some regions can rise by significant amounts over geological timescales. The planet itself slowly adjusts to changes in the ice. This means Antarctica influences the shape of the Earth. The ice presses downward. The crust responds. The gravitational field changes. The oceans respond. The entire planet participates. And there is another connection. Sea level. Antarctica contains an enormous amount of frozen freshwater. If all of the Antarctic ice sheet were eventually melted, global sea level would rise by many tens of meters. Such a transformation would take a very long time and is not something that happens suddenly. But the number illustrates the enormous amount of water stored in the continent. The ice sheet is essentially a gigantic reservoir. Instead of water flowing through rivers, much of it is locked into ice. Instead of occupying the ocean, it is stored on land. The difference between those two states affects global sea level. Sea level itself is not identical everywhere. Ocean circulation, temperature, salinity, gravity, wind, Earth's rotation, local land movement, all can influence regional sea level. So the effect of Antarctic ice loss is not distributed perfectly evenly around the world. The physical response is more complicated than simply adding water to a bathtub. The gravitational pull of Antarctica also matters. A massive ice sheet attracts nearby ocean water slightly. If ice mass decreases, the gravitational attraction changes. Water redistributes. This means that sea level changes near the source of melting can differ from changes farther away. The planet responds in a complex pattern. The ocean also absorbs heat. Most of the excess heat added to Earth's climate system is stored in the ocean. The Southern Ocean plays an especially important role. It surrounds Antarctica. It connects major ocean basins. It absorbs and transports heat. It also takes up carbon dioxide from the atmosphere. The Southern Ocean is therefore one of Earth's great climate regulators. Winds drive circulation. Water masses mix. Cold water sinks. Deep water rises. Carbon moves between atmosphere and ocean. Heat moves toward and away from Antarctica. The surrounding ocean acts like a giant planetary engine. The Antarctic circumpolar current is central to this system. It circles Antarctica continuously. It is the strongest ocean current that flows all the way around a continent without being blocked by land. Its flow connects the Atlantic, Pacific, and Indian Oceans. Water can travel around the continent while remaining within the Southern Ocean circulation. The current also acts as a barrier. It helps separate Antarctic waters from warmer subtropical waters. The boundary is not perfect. Warm water can still move southward in certain regions. But the circumpolar circulation is a major feature of Antarctic climate. The Southern Ocean also transports nutrients. Deep water rises toward the surface. It carries nutrients that have accumulated at depth. Phytoplankton use them. Krill feed on phytoplankton. Penguins feed on krill. Seals feed on krill and fish. Whales consume enormous quantities of krill. A vertical movement of water can therefore influence an entire food web. And some of the nutrients eventually travel beyond Antarctica. Migrating animals carry nutrients. Whales feed in Antarctic waters and later travel elsewhere. Their bodies move biological material across ocean basins. When whales excrete waste, they return nutrients to the water. When they die, their bodies sink. Marine ecosystems are connected by animal movement. Whales also transport carbon. Carbon captured by phytoplankton can enter krill. Krill enter whales. Some of that carbon becomes part of the whale's body. When a whale eventually dies and sinks, some carbon can be transported into the deep ocean. This is one part of the complex biological carbon cycle. The same cycle occurs on many scales. A microscopic organism captures carbon. A krill eats it. A whale eats the krill. The whale moves. The carbon moves. Eventually, some of that carbon can reach deep water. The smallest organisms and the largest animals become part of the same planetary process. Antarctic sea ice also influences the atmosphere. Bright ice reflects a large portion of incoming sunlight. Open ocean absorbs more sunlight. This difference is part of the surface energy balance. When sea ice changes, the amount of sunlight absorbed by the ocean can change as well. This is related to the ice albedo effect. Albedo describes how reflective a surface is. Snow and ice are highly reflective. Dark ocean water absorbs much more solar energy. So a change from bright ice to dark water can alter how much energy the surface absorbs. The effect can reinforce warming in certain circumstances. But Antarctica's climate system is far more complicated than one simple feedback. Clouds matter. Winds matter. Ocean currents matter. Snow cover matters. Ice thickness matters. Seasonal timing matters. The atmosphere matters. Scientists study all of these factors together. Antarctica also influences weather patterns far beyond the continent. The Southern Ocean interacts with the atmosphere. Strong winds circulate around Antarctica. Pressure systems move. Storms develop. The continent affects the position and behavior of atmospheric circulation. Changes in the Antarctic region can therefore have consequences for weather and climate elsewhere. The Southern Hemisphere's westerly winds are particularly important. They circle the planet around the mid to high southern latitudes. Their strength and position are influenced by temperature differences and atmospheric circulation. The Antarctic environment is deeply connected to this belt of wind. The ozone layer provides another important Antarctic story. High above the continent, in the stratosphere, ozone absorbs much of the sun's harmful ultraviolet radiation. Ozone is made of oxygen atoms. A molecule contains 3 oxygen atoms. It is chemically different from the oxygen we breathe. During the Antarctic spring, unusual chemical reactions can occur on polar stratospheric clouds. Certain chlorine-containing compounds can become chemically active. When sunlight returns after the dark winter, reactions can rapidly destroy ozone. This contributed to the development of the Antarctic ozone hole. The ozone hole is not a literal hole in the atmosphere. It is a region where ozone concentrations become much lower than usual. The phenomenon is seasonal. It develops primarily during the Antarctic spring. The extent and strength vary from year to year. Human-made chemicals played a major role. Chlorofluorocarbons and related compounds were once widely used in refrigeration, aerosols, and other applications. They can release chlorine in the stratosphere. That chlorine can participate in chemical reactions that destroy ozone. The international response became one of the major environmental successes of modern history. The Montreal Protocol restricted substances that damage the ozone layer. As atmospheric concentrations of many ozone-depleting substances decline, the ozone layer is expected to continue recovering over time. The recovery is slow because these chemicals can remain in the atmosphere for many years. Antarctica, therefore, contains a powerful environmental lesson. A global problem can be created far from the place where its effects become most visible. Chemicals produced and used around the world contributed to a dramatic atmospheric change over the polar continent. And coordinated international action can begin reversing that damage. The Antarctic atmosphere is also home to polar stratospheric clouds. These clouds form high in the atmosphere during the extremely cold winter. They are sometimes called nacreous clouds because of their beautiful appearance. They can display delicate colors when sunlight illuminates them. At ground level, Antarctica may appear colorless, but high above, the sky can become luminous. Clouds can glow pink, purple, orange, and green. Ice crystals scatter light. The atmosphere becomes part of the landscape. The sun itself behaves differently at high latitudes. During summer, it remains above the horizon for long periods. During winter, it disappears. But even during darkness, the atmosphere can glow. Auroras can appear. The southern lights are called the aurora australis. They are produced when charged particles from the sun interact with Earth's magnetic field and upper atmosphere. The particles excite gases. The gases emit light. The result can be curtains and arcs of green, red, purple, or other colors. Antarctica is one of the best places on Earth to observe auroras. The continent lies close to the southern magnetic environment. During strong solar activity, auroras can become spectacular. They may spread across enormous portions of the sky. Imagine standing outside a research station. The air is cold. The ground is covered with snow. There are no city lights. The stars are everywhere. Then, almost imperceptibly, a faint green glow appears. It stretches across the horizon. The glow brightens. A curtain of light begins to move. The colors shift. The sky seems alive. Auroras are not clouds. They are not reflections. They are not fires. They are interactions between the solar wind, Earth's magnetic field, and atmospheric gases. The light comes from high above, yet it can appear to hang directly over the frozen landscape. The sun is therefore connected to Antarctica in another way. Solar storms can affect Earth's magnetic environment. Strong events can produce bright auroras. They can also interfere with radio communications and satellites. Even a continent thousands of kilometers from most human activity remains connected to the activity of our star. The sun also provides the energy that drives Antarctic surface processes. Solar radiation warms the surface during summer. It powers photosynthesis in the ocean. It influences sea ice. It interacts with the atmosphere. Without sunlight, the seasonal Antarctic ecosystem would be completely different. Yet Antarctica is not simply a place receiving energy from the sun. It also loses enormous amounts of energy to space. The cold surface emits infrared radiation. During the long winter, there is no incoming sunlight for months. The continent becomes an extraordinary heat loss environment. This is part of why Antarctica is so cold. Its high elevation reduces atmospheric pressure. Its snow and ice reflect sunlight. Its winter darkness lasts for months. Its surrounding ocean and atmosphere create powerful circulation patterns. Many factors combine to create the extreme climate. The South Pole sits at an elevation of roughly 2,800 meters above sea level. But the ice surface there is even higher relative to the underlying bedrock. The high elevation contributes to the cold. Air becomes thinner with altitude. Temperatures generally decrease as elevation increases. Antarctica is therefore both a polar and high-altitude environment. The interior is also extremely dry. Cold air cannot hold as much water vapor as warm air. As a result, snowfall can be surprisingly limited. Some regions receive only a small amount of precipitation each year. Antarctica is technically a desert. It is the largest desert on Earth. That may sound contradictory. A desert covered by a gigantic ice sheet. But a desert is defined primarily by low precipitation. The Antarctic interior meets that definition. The snow that does fall can remain for extremely long periods because there is so little melting. Some snow may accumulate for centuries before becoming compressed into deep ice. The rate is slow, but time is abundant. A tiny amount of snow added every year becomes kilometers of ice after tens or hundreds of thousands of years. The Antarctic ice sheet therefore demonstrates the power of accumulation. Small changes repeated over enormous periods can create something immense. One snowflake means almost nothing. One winter means little. But thousands of winters create layers. Hundreds of thousands of winters create a continental ice sheet. This same principle appears throughout Antarctic science. One molecule, one grain of dust, one meteorite, one microorganism, one snowflake, one degree of temperature. Individually, each may seem insignificant. Together, over time, they can reshape an entire planet. And now, perhaps, we can begin to understand Antarctica differently. It is not simply a frozen place at the bottom of a map. It is an archive, a laboratory, a desert, an ocean boundary, a wildlife sanctuary, a geological record, an astronomical observatory, a climate engine, a biological ecosystem, a piece of another world hidden within our own. The continent also has no permanent native human population. People live there temporarily, primarily for scientific research and supporting operations. Research stations operate through the year in some locations. Others operate seasonally. Scientists arrive from many countries. They work together in an environment that belongs to no single nation. The Antarctic Treaty established a framework for peaceful scientific cooperation. The treaty entered into force in 1961. It established Antarctica as a region devoted to peaceful purposes and scientific cooperation. Military activity is restricted under the treaty system. Scientific observations and results are intended to be shared. This makes Antarctica unusual politically as well as physically. It is not simply another country. Its governance is based on an international treaty system. Many nations conduct research there. Scientists from different countries may work on the same questions. The continent becomes a place where international cooperation is essential. Research stations can become small communities. During winter, some stations may have only a limited number of people. The nearest city can be thousands of kilometers away. Supplies must be carefully planned. Food, fuel, medical equipment, scientific instruments, clothing, construction materials. Everything must be transported across enormous distances. During winter, some Antarctic stations become isolated. Aircraft cannot always operate. Ships cannot reach certain locations. Storms can prevent travel. The people living there must be prepared to remain for long periods. Yet scientific work continues. Instruments operate automatically. Weather stations record conditions. Telescopes observe the sky. Ice core projects continue. Seismic sensors listen to the ground. Ocean instruments record currents. Satellites pass overhead. Even when humans cannot travel, Antarctica continues to generate data. Seismometers can detect earthquakes beneath the continent. They can also detect distant earthquakes around the world. The vibrations travel through Earth. Sensitive instruments record them. Scientists can use seismic waves to study the structure of the planet. Ice itself can also produce sounds. Cracks form. Glaciers move. Ice shelves flex. Large fractures can generate seismic signals. The frozen continent is not silent to sensitive instruments. It is filled with vibrations. Glaciers can creak. Ice shelves can groan. Cracks can snap. Water can move through hidden channels. Wind can roar across the surface. The silence we imagine is largely a human perception. Antarctica has its own soundscape, and perhaps the strangest sound is the absence of ordinary sounds. There are no highways, no traffic, no constant machinery across most of the continent, no dense forests filled with insects, no cities, no crowds. There are enormous regions where natural sounds dominate. Wind, ice, water, birds, ocean. In summer, some coastal colonies can become surprisingly loud. Penguins call constantly, seals bark, birds fly overhead, waves break against ice, whales surface offshore. The Antarctic coast can become a busy biological environment. In winter, much of that activity disappears. Migrating animals leave. Sea ice expands. Darkness returns. The landscape becomes quieter. The contrast between seasons is extraordinary. Some animals remain active throughout the winter. Emperor penguins endure the darkness. Weddell seals continue hunting. Certain fish remain beneath the ice. Microorganisms continue functioning at extremely low temperatures. Life does not stop. It simply slows. Certain Antarctic fish have evolved antifreeze proteins. These molecules help prevent ice crystals from forming in their body fluids. The surrounding seawater can be below the normal freezing point of freshwater, yet the fish survive. Their blood chemistry is specially adapted. Ice fish have another remarkable adaptation. Some species lack hemoglobin in their blood. Their blood is unusually transparent. Because cold water contains relatively high amounts of dissolved oxygen, and because these fish have specialized physiological adaptations, they can survive without the typical red blood cell and hemoglobin system. The Antarctic ice fish are an extraordinary example of evolution. Their bodies adapted to a cold environment over long periods. They developed unusual circulation and oxygen transport strategies. What appears strange from a human perspective makes sense in the environment where they evolved. Antarctic fish also contribute to the food web. They feed on smaller organisms. They become food for seals, penguins, and other predators. Every adaptation exists within a larger ecological system. The Antarctic toothfish is another fascinating species. Despite its name, it is a fish rather than a true toothfish in the ordinary sense. It can grow large. It lives in deep, cold waters. Its body is adapted to the extreme Southern Ocean environment. Some Antarctic marine organisms grow extremely slowly. Cold temperatures reduce metabolism. A species that grows quickly in warmer water may require much longer in Antarctica. This can make populations vulnerable to disturbance. Recovery may take a long time. Antarctic ecosystems can therefore be resilient in some ways and fragile in others. Organisms have remarkable adaptations, but their slow growth can make recovery difficult. A disturbance that lasts only a short time for humans may represent a significant portion of an organism's life. The same principle applies to ice. A glacier can respond over decades or centuries. A human lifetime is short compared with many Antarctic processes. A change that seems gradual to us may be extremely rapid from the perspective of a glacier. Scientists therefore think in multiple timescales: hours, days, seasons, years, decades, centuries, millennia, millions of years. Antarctica contains processes operating across all of them simultaneously. A snowflake falls tonight. A glacier moves tomorrow. An iceberg calves next year. An ice core records centuries. A mountain erodes over millions of years. A continent moves over tens of millions of years. The same landscape contains all of these clocks. Perhaps that is why Antarctica feels timeless. Not because nothing changes, but because so many changes happen slowly. The mountains remain, the ice flows, the ocean circulates, the stars return, the seasons repeat, and the continent continues through time. There is also a quiet beauty in the fact that Antarctica does not need to be loud to be extraordinary. Its most important processes can be almost invisible. A gas molecule trapped in ice, a microorganism living inside rock, a current moving beneath an ice shelf, a glacier shifting by a few centimeters, a particle falling through the ocean, a neutrino passing through the planet. Tiny events become part of enormous stories. And now we can return one final time to the ice. Imagine a single snowflake falling through the Antarctic sky. It is tiny, almost weightless. It joins other flakes on the surface. The snow becomes deeper. Pressure increases. The grains become compact. The layer disappears beneath new snow. Years pass. The snow becomes firn. More years pass. It becomes ice. The ice moves. Slowly, quietly, almost imperceptibly. The ice eventually reaches a region where it begins to flow faster. It travels toward the coast. It passes above buried mountains. It crosses ancient valleys. It moves over hidden water. It approaches the ocean. Eventually, it becomes part of a floating ice shelf. The ocean rises and falls beneath it. Tides flex the shelf. Currents pass underneath. The ice slowly thins. A crack appears. It grows. A piece breaks away. The snowflake that once fell from the sky is now part of an iceberg. The iceberg drifts. Perhaps a seal climbs onto it. A seabird passes overhead. The iceberg slowly melts. The water joins the ocean. The ocean current carries it northward. The water eventually becomes part of another water mass. It may travel around the Southern Ocean. It may enter the deep ocean. It may eventually return toward the surface. At some point, that water evaporates. Water vapor rises. Winds carry it. Clouds form. The moisture travels again. Eventually, snow falls over Antarctica. A new snowflake begins another journey. The cycle continues. Nothing is wasted. Nothing is truly still. Water changes form. Ice moves. Air circulates. Carbon travels. Life feeds life. Heat moves. The planet turns. The sun rises and falls. The stars appear. And Antarctica remains part of everything. If you were to look at Earth from space, Antarctica would appear as a bright white shape surrounding the South Pole. But that view would hide almost everything we have discovered. You would not see the ancient air trapped inside the ice. You would not see the hidden lakes. You would not see the mountains underneath. You would not see the microorganisms inside rocks. You would not see the whales beneath the waves. You would not see the penguins beneath the stars. You would not see the neutrinos passing through the ice. You would simply see white. But now you know that the white surface is only the beginning. Beneath it is movement. Beneath it is water. Beneath it is geology. Around it is an enormous ocean. Above it is an atmosphere. Beyond it are stars. And inside it is a record of Earth's past. The Antarctic ice has witnessed changes that no human ever saw. It has survived thousands of winters. It has recorded volcanic eruptions. It has captured dust from distant continents. It has preserved ancient gases. It has watched glaciers advance and retreat. It has watched oceans change. It has watched life evolve. It has watched the planet turn. And yet every layer began with something simple. Snow. A tiny crystal of frozen water. One after another. Layer after layer. Season after season. Year after year. The immense Antarctic ice sheet is ultimately built from countless individual snowflakes. There is something peaceful about that thought. Something enormous can be created slowly. Something ancient can begin with something tiny. A single moment may seem insignificant, but repeated moments become history. A quiet snowfall can eventually become a glacier. A glacier can eventually shape a valley. A valley can become part of a continent's geological story, and a continent can influence the entire planet. So, as this journey comes toward its final quiet moments, imagine the Antarctic surface beneath the stars. The snow is smooth. The horizon is dark. There is no city nearby, no traffic, no bright lights, only the faint glow of the southern sky. Perhaps an aurora is moving above the horizon. Perhaps the wind is brushing across the snow. Perhaps somewhere far away, a penguin colony is settling into the darkness. Below the surface, the ice is still flowing, very slowly. The hidden water is still moving. The ancient rocks are still waiting. Deep beneath the ocean, currents are still traveling. The planet is still turning. The sun is still shining on the other side of Earth. And far above, the stars continue their silent paths. There is no need to rush toward another discovery. The story of Antarctica does not really have an ending, because Antarctica itself continues. The seasons will change. Sea ice will expand. Sea ice will retreat. Snow will fall. Glaciers will move. Icebergs will drift. Whales will migrate. Penguins will return. The Southern Ocean will circulate. Clouds will cross the sky. Auroras will appear. Stars will rise. And the ancient continent will continue keeping its secrets. Perhaps one day, scientists will discover another hidden lake, another ancient ecosystem, another meteorite, another piece of the geological past, another clue inside the ice. There is always more beneath the surface, because Antarctica is larger and deeper than it first appears. For now, though, we can simply leave the continent as we found it. Quiet, cold, vast, ancient, beautiful. The wind moves gently over the snow. The ice glows faintly beneath the moonlight. The mountains stand silently in the distance. The ocean rests beyond the coast, and the southern hemisphere's stars remain scattered across the darkness. Think about the enormous amount of time contained here. A snowflake that fell thousands of years ago may still exist as ice. A bubble of ancient atmosphere may still be sealed inside it. A grain of dust may still tell a story about a distant desert. A microscopic organism may still live within a tiny crack in a rock. A meteorite from another world may still rest quietly on the surface. And beneath all of it, the Earth itself continues to move. Antarctica teaches us that the planet is not a single landscape. It is a collection of connected systems. The atmosphere connects the sky to the ice. The ocean connects Antarctica to every major ocean basin. The ice connects the present to the past. The animals connect microscopic life to giant predators. The rocks connect the continent to ancient supercontinents. The stars connect Antarctica to the universe beyond Earth. Everything touches something else. And perhaps that is the final fact worth carrying with you tonight. Antarctica may be the most remote continent on Earth, but it is not separate from the rest of Earth. It is deeply connected to the planet. Its ice influences the oceans. Its oceans influence climate. Its climate influences atmospheric circulation. Its ecosystems move carbon and nutrients. Its ice preserves the history of the atmosphere. Its rocks preserve the history of life. Its skies reveal the universe. So the next time you imagine Antarctica, don't picture only an empty white desert. Picture the layers, the snow on top, the ancient ice beneath, the hidden lakes, the buried mountains, the flowing glaciers, the floating shelves, the deep ocean, the krill, the penguins, the seals, the whales, the microscopic organisms, the ancient fossils, the meteorites, the volcanoes, the stars, all existing together. And now, slowly, let the image become quieter. The details can fade. The names can fade. The numbers can fade. You don't need to remember every discovery. You don't need to remember every species. You don't need to remember every layer of ice. Just remember the feeling of standing beneath an enormous Antarctic sky. Cold air, soft snow, darkness, stars, silence, and beneath your feet, a continent moving almost too slowly to notice. The ice continues flowing. The ocean continues circulating. The earth continues turning. The stars continue shining. And somewhere beneath the surface, ancient water moves quietly through darkness. Perhaps it has been moving for thousands of years. Perhaps longer. It does not hurry. It simply continues. The same can be true of tonight. There is nowhere you need to rush. You can let the story become distant. You can let the Antarctic wind become softer. You can let the stars become dimmer. The frozen mountains can disappear into the darkness. The ocean can become quiet. The ice can become still in your imagination. And while Antarctica continues its ancient journey around the South Pole, you can simply rest. Snow falls softly across the continent. One crystal, then another, layer after layer, year after year. The ice grows. The glacier moves. The planet turns. Time passes. Quietly, slowly, peacefully. Far away from the Antarctic coast, the Southern Ocean continues its endless circulation. Deep water moves through darkness. Krill drift beneath the surface. Whales travel through the cold water. Penguins rest on the ice. Seals disappear beneath it. The continent remains surrounded by stars. The final light of the day has disappeared. The Antarctic horizon is dark. The snow reflects the faint light of the moon. A distant ridge rises against the sky. Nothing moves quickly. Nothing demands attention. The continent simply exists. Ancient, frozen, alive, and perhaps, after everything we have discovered, Antarctica's greatest mystery is not what is hidden beneath the ice. It is how much more remains unknown. There are places no human has ever stood. Water no human has ever seen directly. Microorganisms scientists have not yet identified. Ancient landscapes still buried beneath kilometers of ice. Ocean ecosystems hidden beneath floating shelves. Stories written in layers that have not yet been drilled. The continent still has secrets. But secrets do not need to be solved tonight. They can remain beneath the ice. The lakes can remain dark. The mountains can remain buried. The ancient air can remain sealed. The meteorites can remain quietly resting on the blue ice. The glaciers can continue their slow journey. The Southern Ocean can continue to move. And Antarctica can simply sleep beneath the stars. So, as our journey finally comes to a close, imagine the continent from above once again. A bright white world at the bottom of the planet, surrounded by dark blue ocean, wrapped in clouds, surrounded by the southern hemisphere's stars. And beneath that white surface is a story hundreds of thousands of years long. A story of snow, ice, water, rock, life, atmosphere, ocean, and time. The snowflake falls. The ice forms. The glacier moves. The iceberg drifts. The water returns. The cloud forms. The snow falls again. The cycle continues. Antarctica remains, quietly turning through another season, another year, another century, another chapter of Earth's long story. And somewhere beneath the frozen surface, A tiny bubble of ancient air remains trapped in the ice, waiting, silent, preserved, holding a breath from another time. The wind becomes softer. The stars become clearer. The ice stretches toward the horizon. And the final thought can simply be this: Earth is always moving, even when everything looks still. The Antarctic ice moves. The ocean moves. The atmosphere moves. The continents move. The planet moves. And tonight, you don't have to. You can simply rest. Let the Antarctic night become quiet. Let the cold blue landscape fade. Let the distant stars disappear slowly into darkness. And let the ancient continent continue its endless, peaceful journey without you. Good night.